only near the walls, right? Very few of the data points are going to be in that band of size epsilon near the walls, right? Most of them are going to be in the middle, correct? Well, guess what happens in high dimensions? In high dimensions, almost all the points are within that band epsilon of the walls. In high dimensions, if you have a uniform distribution over the hypercube, most of the points are close to one of the walls. For the same type of reason why the normal distribution's mass, goes outside. Because there's just so much volume near the walls, right? This is the thing that our intuition doesn't quite capture. In 3D, most of the volume is inside. It's not near the walls. But in high dimensions, there's a lot of volume near the walls. And think about what this means for nearest neighbor, right? For nearest neighbor, you don't want your points to be near the walls because on the other side of that wall, there's nothing. You can't classify those points well. So as long as all the points are safely in the middle, right, then you can probably classify them well. If your points are near the wall, things start to get dubious. And yet that's what's going to happen to almost everybody once you're in sufficiently high dimensions. Okay? So this is our second slightly disturbing example. Here's a third one, a hypergrid. Okay? So what is a hypergrid? Let's start with a grid of dimension 1. Okay? So this is just a line, x, and I'm going to put my points evenly spaced on it. Okay? Forgive my poor drawing. Okay? So let's say that this is discretized, right? So I'm kind of simplifying my life by discretizing my space. This should make life easier for nearest neighbor, right? Okay, very good. So let's suppose that this is my queer point over here, right? And who's my nearest neighbor?
There's a point to your left or right.
There's two, right? There's one to my left, and then there's one to my right, right? They're equally distant, and there's a tie between those two guys. Okay, so if I wanted to use nearest neighbor, I would have to break the tie between those two, right? But this doesn't sound so bad, okay? But you know where this is going, right? Now let's see what happens in 2D, right? Now in 2D, what I have is a grid like this, right? Right? Actually, let me draw one more. And now here's my x cubed, right? So who are my nearest neighbors now? If I want to find my nearest neighbor, who ties for nearest neighbors? 4 points, right? The one above, the one below, the one to the left, and the one to the right. Uh-oh, I'm getting a 4-way tie for nearest neighbor. This does not look good, right? What happens if I am now in a hypercube? How many, equally near neighbors am I going to have? I'm going to have one above, right, one below, one to the left, one to the right, one forward, and one backward, right? So here I had 2 nearest neighbors. Now I have 4, and now I have 6. So in D dimensions, how many, equally close nearest neighbors am I going to have? 2D. So if I'm in a 100-dimensional space, I have a 200-way tie for nearest neighbor. That doesn't look so good. Okay, you see the problem? The whole notion of nearest neighbor starts to become meaningless, basically. The whole notion of similarity and distance and, classifying the one that's closest, is like what? There's all these hundreds of points that are equally close to you. Right? If I have 100,000 dimensions, which, these days is not rare, I have a tie between 100,000 points. Bad news. Okay? So, 2 more quick examples, particularly relevant to machine learning, at least the first one. Let's say that I'm going to approximate a sphere by a cube. Okay? This, for example, is what's going to happen if my data lies in a sphere, and I'm going to learn that with a decision tree, right? I'm going to form a cube around that sphere, right? And this sounds reasonable, right? Well, a cube is a reasonably good approximation of the sphere, right? It's not exactly right, but it kind of captures what's going on, right? So let's see what happens in this case, right? So first of all, in 2D, right, here's my sphere, and here's my cube, right? And so let us shade in the area where we get things wrong, right? It's this area, right? And now let's do this in 3D, right? Now in 3D, now there's a cube, right? And the sphere is inside the cube, right? What has happened to the area where things go, to the volume where things go wrong? Has it gone up or down?
It's gone up.
It's gone up, right? And guess what happens if I go to a 4-dimensional hypercube? You know, these things are hard to visualize, but let's do the following, right? Let's represent this. Let's represent the sphere by just a circle in 2D, and let's represent the square by 4 points like this. Let's make it a star, and make the size of these points, these triangles, proportional to the volume of air. Okay, you get the idea? So what happens in very high dimensions? Can anybody guess? You can probably guess by now what's going to happen, right? I'm going to see something like this. There's this little tiny circle here, and then there's like these points of air like this. The volume where I'm accurate is dwarfed by the volume where I go wrong. In 2D, sure, my hyperplanes that my decision tree forms were a fine approximation. In 3D, still okay. In 100 dimensions, it's a terrible approximation. When I approximate that hypersphere as a hypercube, almost all of the volume of the hypercube is where it should not be. It's outside the hypersphere. Okay? High dimensional is a very disturbing world to live in. So finally, we could go on with these examples forever, but let me just give a quick final one, right? Think of an orange, right? An orange is roughly a sphere, right? And, the orange has its skin, right, which you don't want to eat, and then it has the pulp, which is the good part, right? So, what do you think a high-dimensional orange looks like, a hyper-orange, right? What do you think is the volume of the skin versus the volume of the pulp? Which one is going to be larger?
More skin than you had in 3D.
Exactly. So in high dimensions, the volume of the skin is going to be larger than the volume of the pulp. In fact, if you take you can do this as an exercise. Work out the formula for the volume of a hypersphere, right? And then, think of the volume of a region of size epsilon, close to the hypersphere, so the skin of the orange, and see what happens as you take the dimension to infinity. You know what's going to happen? The fraction of the orange that is pulp goes to 0. If the dimension is sufficiently high, the orange has no pulp. It just has skin. There's nothing left to eat. That's a kind of funky orange to have. But that's the world that we live in when we do machine learning. Please don't have nightmares about this tonight. We don't want to have a negative impact on your mental health.
Giant orange. That's what I remember from the class.
Yeah, that's right. 20 years from now, right, when you're old and gray, you're like, I don't remember anything from the PMP course, but I remember that disturbing orange that was all skin and no pulp. Yeah. We will resort to anything to make you remember the stuff in this class. Okay, so hopefully we've illustrated why the curse of the dimensionality is such a big deal. Right? There's all these ways in which it comes at you. Curse of dimensionality really is one of the top 2 things that makes life hard to read machine learning. But now, we're engineers. Let's go and figure out how to deal with it. Right? How do I fight the curse of dimensionality? And, in something like decision tree learning, something in the basic algorithm is already to some degree fighting the curse of dimensionality, although you can never completely overcome it. In instance-based learning, that is not the case. So in instance-based learning, explicitly fighting the curse of dimensionality can be the difference between success and failure. Okay? So what is the first way in which we can fight the curse of dimensionality? Any ideas?
Reduce the number of dimensions.
Exactly, right? Get rid of some of them. We don't want them. A lot of these dimensions, they might look good. They might look like they're your friend, but they're your enemy. So let's get rid of them. But, we probably don't want to get rid of them at random, right? So how should we get rid of some of the dimensions? Any suggestions?
Probably look for the ones that are best correlated to the classes.
Precisely, right? Remember, the whole game that I'm playing here is trying to predict the class well, right? So I want to retain the features that correlate well with the class and throw away the ones that don't. And how might I measure that correlation?
I'm kind of blanking out.
Okay, let me give you a hint, right? We saw one such method apropos of learning decision trees. Remember when we were selecting, the best attributes to test at a node? What did we use to select the best attribute?
The information gain.
The information gain, right? We can use that here too, right? Why not, right? That's what we want, right? We want the features that carry the most information about the class. Well, measure that using information gain. So there's two main classes. So by the way, this is always known as the problem of feature selection, right? For obvious reasons. And there are two main classes of feature selection methods. And what we're looking at here is the first one. It's often called the filter approach. Because what we do is we send all those features through a filter, and most of them don't make it through the filter. And then we only use with our nearest neighbor algorithm the features that come out the other end. Okay? We select each feature by how informative it is with respect to the class, and this can be done in many ways, but an obvious one is to use the information gain. Okay? The big advantage of this approach is that it's efficient. Right? I test each feature individually, I measure its correlation with the class. This is linear in the size of my data set. Not a problem. Okay? Even for a large data set. What is the big disadvantage of the filter approach? Again, let me give you a hint. It's similar to the big disadvantage of pre-pruning trees over post-pruning.
You're losing something that might be valuable.
Exactly. Let's suppose that I have a concept that's just, the parity of two of its attributes, of two of the attributes in the data, right? What is the problem of selecting features by information gain? Right? Let's suppose actually that I have no noise, I have no relevant dimensions, right? But I don't know that, right? I just have those, and I apply my information gain to each one of them, right? What is the information gain of each of those two features going to be? 0, right? They don't look like they say anything about the class. The problem with this filter approach is that it's looking at each filter in isolation. That's efficient, but on the other hand, what happens in most of the interesting cases is that features are not informative in isolation. They are only informative when you combine them with other features, and this method can't detect that. Okay? Despite that, it's still very widely used in practice because of its scalability. It's a very easy, very fast thing to do. And, in a lot of domains where what you really have is just a ton of completely relevant attributes, this gets rid of them pretty quickly. So, for example, in a lot of text classification problems, right, I want to classify documents by the words on them. And, there's 500,000 words in the English language, and most of them are probably not useful at all. Just this test of information gain probably gets rid of them quite easily. Okay?
But the parity example, it could be missing something really good that's in there.
Indeed.
Right?
So in a way you want to use this when there's a lot of irrelevant features and you suspect that there isn't something really good that you're missing. Or another way to put this is you want to believe, and this is the case in text classification, that the information that remains after you've thrown all that out is still good enough. And if you think about it, for text classification, this is the case. Because if I want to classify pages by topic, sports, politics, entertainment, technology, etc., if I only retain the 1,000 most informative words, well, if it has the word baseball, it probably is sports. Okay, so for some things this is fine, but for a lot of things it's not, and that's why we have the wrapper method. Excuse me. The wrapper approach, as the name implies, is you wrap the feature selection around the algorithm. Right? I want to throw out only the features that aren't useful even in combination with other features, but how do I know? I don't know that in advance. I will only know that after I run the algorithm. Well, so let's just do that. Let's run the algorithm with the features. Let's run the algorithm with different subsets of features and see how well it does. Right? So obviously this is expensive. Right? This could be very expensive, but it can be much better. And in fact, with some methods, including notably nearest neighbor, this can be a lot less expensive than it might seem to be at first sight if we are clever about avoiding redundant computations. Right? Don't just be recomputing all your distances from scratch each time, right? I compute my distance using these features, and then when I add a new feature, right, I don't recompute my distance from scratch. I just take the old distance and I add the new component. Right? So that's the general idea, and now there's two main ways to do wrapper type feature selection: forward selection and backward elimination. Can you guess from just the names what these two approaches are going to be like? What might forward selection be like? It's on the next slide, but let's avoid the temptation to look at it for the moment. All right, how would you do forward feature selection?
Add attributes into your group one by one.
Exactly. So I start out with no attributes, right? Nothing. And then I try, using only one of them. Right? This will probably be bad, right? But one of them will probably do better than the others, the single most informative attribute, so now I keep that one. And then what do?
You have to have some measure in some way.
Very good. So what should my measure be? Or, it can be lots of things, but one thing that it can be, right? Remember, we're just wrapping this around the algorithm, right? So we run the algorithm, right? And now let's say, again, think back to decision trees. What would you do, for example, in post-pruning, right? When we were evaluating different versions of a decision tree. How did we do that?
I mean, you could have a statistical test again, whether the data is the same after.
Yep, exactly. So that's one option, right? Another option is to have validation data, right? So I have some data and I look at that data, right? In fact, I can do cross-validation, and again, I can be very clever and even do what's called leave one out cross-validation, where I only leave out one example at a time. But notice that when I take out one example, most of the nearest neighbors don't change. So actually running through this efficiently can actually be done, in reasonable amount of time. Okay, so I try adding each feature, I measure the resulting accuracy, I pick the best feature, and then I try adding, one of the other features, and I keep doing this until when? Right, when should I, obviously if I wind up adding all the features, it stops right there, right? But why would I stop earlier than that?
Accuracy doesn't improve enough.
Yeah, or in fact it could even go down, right? If I come to a point where I now say have 10 features, and I try adding each one of the other 90 features as the next one, and in all cases it makes things worse or not better, then well, this is where I should stop. Okay? So this is forward selection. What do you think is backward elimination?
Start with all of them, remove one at a time.
Exactly. I start with all of them, and I remove one at a time. And when I remove, if when I remove each one of them, it always makes things worse, well, then I stop right there. What hopefully happens is that many of them are irrelevant, so when I remove them, things don't get worse. Okay? And so I remove one of those and I keep going. Okay? So, question for you. What are the relative advantages and disadvantages of forward and backward selection? What is an obvious advantage of forward selection over backward selection? Let's suppose that I have 10 relevant features and 1,000 irrelevant ones. Which method do you think will be faster?
Forward.
Yeah, forward selection is going to be way faster, right? This is a lot like pre-pruning and post-pruning, right? Very similar. With post-pruning, I have to grow the whole tree and then prune it back. It's a big waste of time. With forward selection, I just quickly, hopefully, zero in on the relevant features, and the other ones I don't have to deal with. Okay? But now, of course, there's also a big disadvantage of forward selection compared to backward selection. What might that be? Let me give you a hint, right? Go ahead.
I'm sorry, I was saying, is it the same as you were saying about missing, eliminating certain information too early before it.
The hint I was going to give you is a hint that I will, give you many times, and it's just this word parity. Right? What is the problem with forward selection if your concept is parity? It falls flat again, right? It's just like the wrapper method in this case. There are cases where the wrapper method fails and forward selection doesn't, but for this type of problem, it's exactly the same issue, right? I'm doing my forward selection, and I immediately think that none of the features is useful, so I don't add any of them, and I'm hosed. So it was fast, but I got the wrong answer. Okay. And if most of the features are relevant, you actually don't get that big of a performance benefit anyway. Okay. On the other hand, what usually happens in practice is that the vast majority of the features are irrelevant. So there is a big performance advantage of forward over backward. On the other hand, you could miss a lot of things, which is why you want to be aware of both methods. Okay? Questions?
So in terms of instance-based learning, backward elimination would mean, let's say you were in a very high dimensional space and you have 200 points closer. You pursue all of them?
No, so notice the following, right? We need to distinguish between feature selection and instance selection. Right? We're actually going to talk about instance selection a little bit, but for the moment, we're always assuming that you keep all of your instances. Right? So I have my big table, right? One instance per row, right? What we're talking about here is making the table thinner, not shorter. We're talking about throwing out features. I still have 200 examples.
That are closest to
Yeah,
equally
let's
close.
say 200, whatever, right? But the number of examples has not changed. What has happened is that there are 200 examples in a lower dimensional space. Okay? Questions? Okay. So we have here pseudocode for both of these, but I'm not going to go over it here because we already saw what it does. I encourage you to look at it at home. But there's more things that we can do, right? Feature selection is a bit drastic, right? Well, what if there was a little bit of information in that feature? Do I really want to throw it away? Maybe I can somehow squeeze the juice out of it without letting the noise swamp the signal, right? If some features are very informative and some are not very informative, well, I don't necessarily just want to completely throw away the informative features because there could be a lot of them, and when I do that, I could actually be compromising my performance. So the next method that we're going to look at, and is a very, very widely used one, is what's called feature weighting. And again, it's a very natural idea, right? What I'm going to do is I'm going to give weights to my features. Again, notice that this is different from giving weights to your instance, and in fact, you could do both, right? What I'm going to do is I'm going to say, oh, if this feature is very informative, it's going to count for a lot, so I'm going to, in my distance measure, right, I'm going to put weights on the contributions from the different features. And the more informative features, according to some criterion, will have a higher weight. Okay. Another way to think about this is that what I'm doing when I'm doing feature weight is I'm flattening the less important features. It's like saying, let's say, like my instance space was this room, and like the coordinates on the floor are very important, but the height is not very important, right? The height, maybe I don't want to throw it away completely, but I want it to count for less. What I'm going to do is I'm going to flatten the room, right? So now the variations in height make a relatively small contribution. Maybe they can break ties between things that are at the same distance horizontally. Okay? In the limit, of course, if I flatten things all the way, that dimension disappears. So feature selection is sort of like a limiting case of feature weighting when the weight becomes 0. Okay? But in general, the weights could be, very varied. Okay? So how exactly might I find the weights for the features? Again, there's many ways, but probably the most widely used one is to use continuous optimization, right? Use gradient descent, right? I have my measure that I care about, accuracy or some other measure of error, right? Let's suppose that it's a continuous function of my weights, right? If it's not, I'm going to have to be more careful, right? And then what I'm doing is like, think of, the value of my error as a function of those weights, right? What I'm going to look for is the value of those weights that gives me the minimum error. Okay? And I can do that using gradient descent. We will look in more detail at gradient descent a little bit later when we talk about neural networks, but for the moment you could just think of it as it's a method for finding, the value of the inputs to a function that make the function as small as possible. And, as the name implies, it's kind of like, if you want to find the value, just walk downhill. Right? Walk downhill with the weights. Start, for example, with all the weights equal, find the direction of steepest descent, and keep following it until you're in the valley. Right? And at that point, hopefully, those are your best weights. Okay? And that's feature weighting for you. Okay? I'm mentioning a bunch of these things fairly quickly. Of course, there's many technical details, but I think the important thing is for you to A, be aware of the general class of methods, and then B, the kinds of things that you can use to make them better. Right, such that if you run into a problem where feature weighting is really what you need, then you can sort of like, look into that in more detail. Okay? Okay. So, why don't we take a break here, right? So it's 5:20, right? So let's break until 5:30. Okay? And then we'll do the rest. Okay. Instance-based learning part 2. Let's look at some more of the issues that arise when you're doing instance-based learning and what you can do about them. So as I mentioned, and you've probably noticed by now, computational cost is one of the biggest issues. Right? We have this massive instances to store, and then we need to match them all at query time. What can we do about that, right? How can we reduce the computational cost of instance-based learning? And again, because this is a very well-known problem, and these techniques are quite well developed, there's a whole host of solutions. But they fall into four main classes. The first one is, well, let's see. I don't really have to run through all my instances at test time, right? Can I do that more efficiently? Well, sure. We're computer scientists. We have data structures for these things, right? So the first thing is the first type of approach is to come up with data structures that allow for fast retrieval of the nearest neighbors, okay? And there's a whole bunch of them, but the classic one for nearest neighbor is something called KD trees. Has anybody here heard of KD trees? They're also popular in graphics and image retrieval and whatnot. Okay. So what is a KD tree? I'm lazy today. I'm going to ask you to teach this topic for me.
Sort of recursively split the space into smaller spaces.
Exactly. So a KD tree is a little bit like a decision tree. What it does is that at each level it splits on one dimension. But the goal here is not to maximize accuracy, but to have the shortest path to every instance, right? I want log number of steps before I find my nearest neighbors. So what I typically do in KD trees is that I alternate between dimensions. I split on the first dimension and then I split on the second for all the cases and so on, and I keep cycling through them. And typically I just split, on the median of the data points or whatever, right? I'm just trying to split the space in such a way that the tree will be as shallow as possible, okay? So that's the idea of KD trees. KD trees work very well in low dimensions, right? And which is why they're used a lot in things like graphics and whatnot, right? But guess what happens in high dimensions? So success for these types of things is retrieving an instance in time log of the number of instances, right? That's success. Failure is retrieving an instance in time linear in the number of instances, which basically means you didn't save anything, okay? So in low dimensions, we can often get pretty close to log n, right? Guess what happens in high dimensions? I'm not asking you to do any detailed reasoning, just, on general principles, given that high dimensions are ugly and whatnot, what do you think is going to happen in high dimensions?
Tends towards n instead of log n.
Yeah, exactly. In high dimensions, it's going to become more like n. Meaning, in high dimensions, this stuff basically becomes useless, unfortunately. Now, why do you think things fall apart in high dimensions? Important application of what we saw 20 minutes ago.
From this description, it seems like you're alternatively splitting, right? So your chance of error is much higher if you split the tree based on one dimension. Most likely it was in the other.
That's part of the answer, right? But let's think a little bit more precisely what happens. Like, what I want to do, right, is I want to find my nearest neighbor, right? Let's just say we're doing one nearest neighbor for simplicity, right? I have my query point, right? And what I'm going to do is I want to very quickly sort the query point to the leaf where the nearest neighbor is going to be, right? So in an ideal world, what happens is that the points are all very far apart, right? So it's very unambiguous which branch I need to go down, right? And I only have to retrieve one sequence of nodes in my tree, and I know that my nearest neighbor is going to be in it, okay? So if the points are well separated, life is good, right? On the other hand, what happens if the points are not well separated? Then when I split on this dimension, I don't know. Maybe it's going to be that way, maybe it's going to be that way. It's not clear yet. Okay, so now I'm going down 2 paths. And then at the next split, maybe I don't know yet, so now I'm going down 4 paths. And before you know, you've gone down a number of paths order the number of data points. Right? So why would the latter case happen more in high dimensions? Right, so we want the points to be well separated, and then we'll get log n. If they're not well separated, we'll get n. And the problem in high dimensions is that
A lot more paths to...
The points are not well separated in high dimensions. Remember, the key thing that happens in high dimensions is that everybody starts to be at more or less the same distance. In low dimensions, it's very easy to say like, oh yes, I need to go this way, and I'm done. In high dimensions, I could need to go any way, right? All the points look equally close, right? So I need to go in all dimensions to look for my closest neighbor, okay? So KD trees are a very good thing to know about. It is it's like a standard tool in instance-based learning, but in high dimensions they will probably fail. Okay? The next thing to do is also a very good thing to know about. In fact, it's a good thing to know about beyond machine learning and data mining. It's a very nice trick that is used all over the place to scale things up. And the trick is the following. Where am I spending all my cycles? It's in doing similarity computations, right? I'm computing distances between points. If that distance was cheap to compute, then I could easily run through all my data points. The problem is the combination of something that is expensive to compute, like the distance over a lot of dimensions and a lot of data points. Okay? So how about we do, but on the other hand, the cheap, distance measure is probably not going to be very good either, right? Could be, for example, a distance measure where I've thrown away most of the features. Okay? So what can I do? Here's what I can do. 2 steps. Step 1, I use a cheap approximation of my distance measure to get rid of most of the instances. The key thing to realize is that most of the instances are nowhere near being your nearest neighbor. Nowhere near. You can tell very quickly that they're not going to win. 90% or 99% of them you can get rid of quickly. So what you want is a rough but quick approximation to the distance function they're interested in. And use that to weed out most of the instances. And then step 2. On the ones that remain, the ones that now, really could be the winner, now on those you apply the expensive measure to really pick the winner. Okay. And by the way, for a problem like this, as opposed to other areas of computer science, if you don't really find the nearest neighbor, it's okay. Right? Unless your data is very sparse, but then, scaling is not a problem anyway. If you end up with your second nearest neighbor, so what? It's probably good enough. They're probably all of the same class anyway. Okay? Nevertheless, on a good day, if you design your approximate measure very cleverly, you can actually guarantee that you will never throw out your true nearest neighbor. And therefore you get a free lunch. You actually weed out a lot of the instances very quickly, and you still know for sure that the one that you want to survive will survive and will come out when you actually do the expensive computation. Okay? This is a strategy that is used for a lot of things, and you can think of obvious ones, like, for example, image retrieval and so on and so forth. But more generally, this idea of having a quick approximation that you use to, filter out a lot of stuff, followed by the expensive one on a subset of that, is a very simple idea, but very powerful. Okay? So it's worth knowing about, not just for instance-based learning, but beyond it. Okay? So the next kind of approach is also a very interesting one. It's forming prototypes. And part of the inspiration for this comes from psychology, because it seems that people do this. Forming prototypes is based on the following notion. Why am I really storing all those bazillions of data points? Right? Okay, I have a big pile of points over here. Let's just say, those points are roughly in this place here. Right? I will remember that place and not worry about the details. Right? Forming prototypes means, what is a prototype? A prototype is a point in space or in a subspace that's kind of a good representative of a whole bunch of stuff around it. Okay? And I can summarize the data that way. Of course, I've lost some detail, but hopefully the prototypes capture most of what's going on, and then I have many fewer of them, and matching them is much faster. Okay? And again, there are many techniques for doing this. I'm not going to go into them, but it's good to be aware of them. Finally, one of the most popular methods, and one that also makes a lot of sense, is what's called edited k-nearest neighbor. And this is also based on the observation that we probably don't need all those instances, but for a different reason. Here's an illustration of the reason. Now, let's say that this plane is my instance space, right? And I have a bunch of positive examples over here. Positive, 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 etc. And then a bunch of negative examples over here, right? And now, roughly speaking, here in this simple example, the frontier between positive and negative runs around here. Okay? Right? Thinking of that whole Voronoi cell argument. Right? So now, let me ask you a question. What would happen to the, and remember, the only thing we care about here is the frontier, right? Because we just want to know which side of that frontier my query instances are on. Right? What would happen if I threw out this data point? What would happen to the frontier?
Nothing.
Nothing whatsoever. right? I can get rid of it. It's not doing anything useful. What would happen to this data point? If I threw out this data point, nothing, right? On the other hand, what would happen if I threw out, say, this data point? Well, in this case, something would happen, right? Because now notice, this here, right, is this segment of the frontier is the frontier between the Voronoi cell of this guy and the Voronoi cell of this guy, right? If I throw out this guy, now the frontier is going to swing like that. You see, so the moral of the story is the data points close to the frontier really make a difference. The data points far from the frontier, who cares? They're not doing anything. This is actually the notion that's behind the method that we're going to see much later, but is one of the most sophisticated methods in machine learning, the support vector machine. The support vector machine, as the name implies, is based on support vectors. Guess what a support vector is? A support vector is an instance that is holding the frontier where it is. It's supporting it, and it's a vector. That's why it's called a support vector machine. Okay? And the important thing to realize is that I just need to remember these guys, because they're the ones that define the frontier. The other ones, I can get rid of. Right? I got rid of all this stuff, and I still have the same frontier. Isn't that amazing? So this is the edited nearest neighbor method. Now let me ask you a question that is now a recurring question in this lecture. What happens to this in high dimensions? In low dimensions, this can be brilliantly useful, right? I could literally throw out, the vast majority of the data, right? There's only a few fraction of the data points that are close to the frontier, right? So this can be an amazing success. But what happens in high dimensions? Which fraction of the points do you think are going to be near the frontier? Most of them. Remember the hypercube example? Well, that's where this bites us. As I go into higher and higher dimensions, there's more and more directions in which I could go from the frontier to a point, and they're all close to the frontier. So you can actually run the edited k-nearest neighbor with some data that you generate, and as you add dimensions, the fraction of the examples that remain after you do the algorithm goes from small percentage to a third or half, maybe most of them. So the usual problem of the curse of dimensionality applies. Nevertheless, this is a very useful method to have. So exactly how does edited k-nearest neighbor work, right? So what's the algorithm going to be, right? I'm looking for an algorithm. It can be heuristic, it can be greedy search. In fact, it has to be greedy because doing this optimally is NP-hard, as most things in machine learning and AI are, right? So how might we go about doing this? And let me give you a hint, right? What we're doing now is selecting instances as opposed to what we were doing before that was selecting features, right? But I can also do forward and backward selection types of things, right? So what would be the forward selection analog of edited nearest neighbors?
Any point, any instance, all whose nearest neighbors are the same. So that's probably the first thing.
I partly agree with you, right? So remember, in feature selection, the forward method was I start out with no features, right? And then I see, what my best feature is and so forth, right? So by analogy, in edited nearest neighbor, I should start out with no points, right? Which means I don't have neighbors yet, right? So my very first point, right? Should I keep it? Well, I better, right? And so now let me propose the following heuristic, right? Remember the diagram that we just had? When do I know that a point is not going to be necessary, right? Think about this in the cross-validation sense. If when I bring in that point, it's correctly classified by the points that were already there, that probably means that it's not necessary, right? Because the other points are already doing a good job. This is a point that's not near the frontier because, all the points closest to it are already of the right class. So the heuristic is bring in one point at a time. If it's already correctly classified by the points that are already there, I probably don't need to remember it. If it is incorrectly classified, that means that the other points do not form the right frontier because it's passing, on the wrong side in this example, so I remember it. Okay? Everybody follow this? So this is the forward version of edited nearest neighbor. What might the backward version be? So in the forward version, I start with no instances, right? In the backward version, I start with all instances, and then what?
Remove ones that have no effect on your
Yeah,
equipment.
and then the same thing, right? I go to instance and say, like, if you were the query, right? If this instance was the query point, would it be correctly classified? If it was correctly classified, then it's probably not doing anything there. Okay? And I keep on doing this until all of them are necessary, meaning like, all of them would be incorrectly classified if I took them away. Okay? Questions? Simple idea, quite powerful. And again, I have the pseudocode for that here, but we already went over it. Okay? All right, so final and most important issue before we go on to talk about other kinds of distance-based learning is, of course, our old enemy, our old foe, overfitting. Right? So as somebody already mentioned, overfitting can be a big problem in nearest neighbor, just as it's for the other methods. So how can we fight it? Any suggestions? Actually, let me even not show that just yet. Any suggestions, right? How might you fight overfitting? And actually, let me even sort of like make this a more limited question. In most learning algorithms, there is one natural overfitting control parameter, right? For example, in decision tree learning, it was like, for example, the level of significance of the test, right? In k-nearest neighbor, as is, with no frills, just your basic k-nearest neighbor algorithm, is there a natural overfitting control parameter? And if so, what might it be, and how would it work? So, yeah.
K itself could be
Yeah, absolutely.
could be a parameter in that sense, right?
Very good, because if you think about it, what parameters do we even have in k-nearest neighbor? Well, the obvious one is k, right? So how could we use k as an overfitting control parameter?
I think if you're classified based on a larger number of neighbors, you're probably in a region of that class as opposed to somewhere isolated.
Exactly. Just your plain k is a great overfitting control parameter, because what happens is that as you increase k, right, you're averaging over a larger region, which means that you're losing resolution, right? Now you're no longer able to, like your glasses, have become, you're losing focus. So you can't learn concepts in as much detail. On the other hand, you're now much more robust, right? Now when like if k is say 100, right? And 70 of those 100 are plus, well, you're pretty confident that it is a plus, right? Because in this large region with a lot of examples, the majority is positive. Okay? In the limit, if I make k equals to n, I just predict the most frequent class, which is about the least overfitting you can imagine, doing. At the other extreme, if my k is equal to 1, as you pointed out, right, any little point is going to create a region of error around it, right? This point was just noise, but its Voronoi cell is going to be misclassified. Okay. So k is our overfitting control parameter. So how might we find the best value for k? Again, it's a matter of applying here a general technique that we already saw apropos of other methods.
Try increasing k and then see how the accuracy increases as you increase it.
Yeah, exactly. But, key detail, the accuracy on what data? On the training data?
The validation data.
Exactly, it has to be on the validation data, right? Because if it's the accuracy on the training data, I'm always going to be better off with one nearest neighbor, right? So what I need to do is cross-validation. Just hold, or if I don't have a lot of data, I can do cross-validation. I can even do leave one out cross-validation, where I just leave out one point at a time, right? Because if I do this cleverly, I don't actually need to rerun everything, right? When I leave out one point, most of my distances don't change, most of my classifications don't change. So I can very efficiently do leave one out cross-validation, where each fold is a single example, and find out the best k that way. And this is what people do almost all the time, right? They do k nearest neighbor with cross-validation to choose k. And it works pretty well. It's still a pretty fast thing to try. Okay. So this is method number 1. Method number 2 is something that we already saw before, apropos of efficiency. And again, it's often the case that that things that you do in machine learning to improve efficiency also reduce overfitting and vice versa, because they both involve searching less, having fewer options, and so forth. It costs you less time, it also reduces your chances of overfitting. So this other thing that we saw is forming prototypes, right? If instead of having all these data points, I glom them all into like big clusters, well, A big cluster is much less likely to be noise than a single isolated data point. Okay, so whatever methods we use to form prototypes, we can also use, to give me less overfitting. Okay. The optimal size of prototypes for speed and for accuracy might be different, but you can optimize, your parameters of your prototype forming algorithm using cross-validation and whatnot. Okay. Finally, here's another very popular method, which is in a slightly perverse way related to the additive, the nearest neighbor, k-nearest neighbor algorithm. And this is removing noisy instances. Again, let's think back to our nice little 2D example. Right? So let's suppose that I have a whole bunch of points here. These are negative here. Just a second. Wait. Right, so let's suppose that I have, this is negative, 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 positive, 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 positive. So in this data set, there's no noise. Right? Life is good. But now let's suppose that I insert here a noisy data point, actually let me put a few more good points here. And now let's say that this point for some reason was wrong. Right? It's a positive example where it should have been negative. It's that day on which your friend was hungover and didn't want to play tennis. Okay? Now obviously this point is going to have its own Voronoi cell, right? And it's going to do damage, and we want to get rid of it. Right? I would just like to delete this data point. And so the question for us is how do I figure out which points are noise? Right? Look at this diagram and, what does your, powerful 2D visual system say on this problem? How can you tell that this guy is an outlier? Why is this guy an outlier and this guy not an outlier and this guy not an outlier?
Surrounded by examples of the other class.
Exactly, this poor lonely guy is surrounded by enemies of the opposing army, right? He's very lonely, he's going to die soon, right? These guys are reinforced by, examples of the same class around them, right? I look at this guy, all of its nearest neighbors are positive too. Why would it be noise, right? This guy here, all of its nearest neighbors, until you go very far and get to the frontier, are of the opposite class. So I really have no reason to believe that this is a plus. Notice that this is a little bit like additive k-nearest neighbor because it's removing instances, but actually is removing them in a completely different, even opposite way, right? Also because the goal now is different. Okay. So basically what we do here is we run through each example in turn, and we see if some fraction of its neighbors are of the opposite class. Or another way to put this is I have my k, right? And I look at my k-nearest neighbors. If they're all the same class, I'm good. If they're all of the opposite class, then this is probably noise, right? But now the problem is, where should the threshold be? Suppose there's one of my 5, nearest neighbors is of the same class, but the others aren't. Is this noise or not? How would you decide? Well, if you think about it, this really has to do with the noise level in the data, right? If the noise level is low, right, then, all of your nearest examples should be of the opposite class. If your noise level is high, sure, 1 or 2 of them could actually be, right, you don't know. So the way to set this is to either use what you believe about the level of noise in the data, or again, you could use cross-validation. Okay? But there is no single threshold that will always work. I could say, I will decide, that you are noisy if, all of your data points are of the opposite class, or 4 out of 5 of them, or, or probably, at least the majority, right? So, questions?
It could also be not one point, but some larger region too, so it gets a little bit complicated.
No, but you're right, but this is the same, we're actually talking about the same thing, right? Because suppose that there were 2 of these guys here, right? Or even 3, right? Then what happens is that out of their 3 nearest neighbors, right, you're still winning. But if I look at my, 7 nearest neighbors, not look them like the minority. And the deeper problem here is the following. Well, maybe there really is a positive region here, right? How do I know that I should throw those out, right? At some point, there's enough of them that I'm okay, I'm willing to believe that there's a positive region here. So it really depends on the noise level, and you probably want to do something like cross-validation to decide. Okay, very good. So, that was a whirlwind tour of some of the main issues that arise in k-nearest neighbor and how to deal with them. But k-nearest neighbor is just the most basic of our instance-based learning methods. There's a whole plethora of interesting instance-based learning methods out there. And, we don't have time to look at all of them, but let's just look at some. And the first one that you definitely want to know about is what's called locally weighted regression. And the beauty of locally weighted regression is that you get a lot of bang for the buck. You should always be looking for that as a computer scientist, but particularly machine learning. Can I get a lot of mileage out of a little change to the things that I already know? And let's say one of the things that you already know is, good old linear regression. Okay? Good old linear regression, remember, forms, here's my x. Let's just do this in 2 dimensions. I have a bunch of data points, right? And linear regression just finds the straight line of best fit. Okay? This is Stats 101. There's packages to do this. It really boils down to a bit of linear algebra, inverting a matrix, etc., etc. Okay? But the problem is that this is not very powerful, right? On a very good day, your data actually follows a linear curve with, has a linear relationship with a little bit of noise. More often, what you're going to have is something like, complicated curve. This is what the real function is. And linear regression isn't going to give it to you. Okay? On the other hand, so let's say, what are we going to do now? We're going to fit polynomials, we're going to fit splines. You can do that, but it becomes much more complicated, right? Let us try to figure out what this curve is with all of its multiple coefficients and whatnot. And of course, in high dimensions, when I have many x's, this becomes a really big problem. Okay? So we do want to go to nonlinear curves, very much so, right? This is what machine learning is about, is dealing with the complexity of the real world as opposed to just using your little, Stats 101 toolbox. But how can we do that without paying a huge price? This is where locally weighted regression comes in. The idea in locally weighted regression is just shockingly simple, and yet you get this huge power out of it. The idea in locally weighted regression is the following. Let us be lazy, right? Again, that's the theme of this lecture, is being lazy. Let us not try to fit these curves, right? I'm just going to remember those data points, right? Leave them there. And then, when the query comes along, here's my XQ, right? What I wanted to do now is predict the value for my XQ, right? What is the Y for my XQ? Well, with my linear regression, I would have gotten this, which is quite far from the real value, right? So this is my real YQ, right? And this is my YQ hat. Bad. How about the following, though? What I'm going to do now is I'm going to do a linear regression, but just around the nearest neighbors of XQ. I find, let's say, the 10 nearest neighbors, are in this case, because it's a small example, let's just say the 4. Let's say there's one here, there's one here, and, there's one here. And, let's say another one there, okay? So I find my 4 nearest neighbors, okay? And now I just do linear regression over those, right? This is great because it's going to be a very cheap linear regression. It's only over 4 points as opposed to 1,000,000, okay? So now I fit a line to these 4 points, right? And guess what? This is a much, much better estimate. And yet, I just did it with my good old linear regression black box. Isn't this amazing? This is a regression instance of the fact that we saw before, that because of the Voronoi diagram, right, I can form a very, complicated frontier at no cost. Here I can form a very complicated curve because I'm fitting a different line everywhere. What I'm actually doing here, of course, is forming a piecewise linear approximation to my curve, right? I'm not going to approximate it exactly because, remember, it's a curve. I'm going to approximate with a bunch of linear regression, so it's going to be a bunch of straight line segments. But nevertheless, this straight line segment is going to be a much better approximation than this whole, line that's trying to fit everybody at the same time. So the moral of the story is laziness can really pay in machine learning. Right? This is one of those things that I think everybody out there should know. All those people who are just using linear regression, they could still use linear regression and get much, much higher accuracy if only they just did this. Okay? So if you don't remember, most of what we learned in this lecture, this is one thing that I think is worth remembering. Okay? Questions so far?
How is this different from doing a piecewise approximation in advance versus doing it?
So the result is the same, but again, remember, just as with the Voronoi diagram, why would we bother to go to all the trouble of figuring out the equations of all those Voronoi frontiers, right? It's a lot of trouble for nothing, right? I can just save it, till query time. And the problem that it does have the advantage that at query time this is going to be slower, right? But it's a small linear regression that I'm going to do at query time, so that's probably not going to kill you anyway. Okay. So how do we do this exactly? Well, we can do it in the usual way. And in fact, we're not forced to actually just fit a linear function, right? We could actually fit a quadratic function, right? Instead of making it piecewise linear, I could make it a whole bunch of parabolas and get a better approximation that way, right? So the general theme here is that by fitting it around the query point using the nearest neighbors, I get a piecewise approximation. But those pieces could be lines or it could be curves of some degree. Okay? And again, I'm going to have a choice of error measures to optimize. I could, do least squares as I do in ordinary, linear regression. I could also do distance-weighted least squares, right? I'm not now doing a least squares where all points matter the same, right? Probably when I do my linear regression, my points closest to the query point should count for more because that's where I really want to get my fit right, okay? So I can bring instance weighting into locally weighted regression just as I did into k-nearest neighbors, okay? Notice these are all very simple ideas, but they can be quite effective. Okay, so let's see how we're doing on time here. We have time to talk about a couple more types of instance-based learning. Let me just, briefly mention some of them. So one of them is, without again going into a lot of details, one of them is what are called radial basis function networks. And this actually, you can think of this as a type of neural network. We're going to talk more about neural networks later, but there's again a close analogy between this type of learning and some things that appear to go on in the brain, in particular in the visual cortex. A radial basis function network is actually a kind of instance-based learning that is again quite smart and in some ways not that complicated. Truth in advertising, it is more like at this point we're not very lazy, right? So radial basis functions are not a very lazy method, but still they're an instance-based method. So what do we do here is we're going to form a global approximation to my target function, but I'm going to do it as a linear combination of what are called basis functions. This again is a very wide class of methods in machine learning where I try to represent my concept or my function as a linear combination of what are called basis functions. A basis function is just some function of the point. In particular, it could be just a function of the distance between points. Okay? As I said, this is used a lot for vision tasks like image classification and whatnot. It's a type of neural network. What does it consist of? Well, here's the idea. Here's my f of x. I'm going to compute my f of x as a weighted combination of, let's say, Gaussians. It could be a lot of things, but the most frequently used thing is a Gaussian. So what I'm going to do is I'm going to put a bunch of Gaussians, all over the map. Okay? And then, what I'm going to do is so each Gaussian is going to have a value, right? So when my query point comes along, it has a value. And I'm going to do a weighted combination of those Gaussians. Okay? So in a way, this is a more powerful version of things that we've already seen. Those Gaussians are often called kernels or basis functions. Kernels and basis functions in machine learning are, used interchangeably. Some basis functions are not kernels and vice versa, but for these purposes, you can think of them as being the same. Okay? So a Gaussian kernel is really just, this form, right? It's exponentiated, squared, etc., etc. Okay? It's basically just, a bell shape centered at some point. Okay? So now I have a couple of questions to answer. The first question is, well, where should I put those basis functions? Right? Where should I put those kernels? Right? One choice is actually just plunk them down at random. This is actually not as bad as you might imagine. Another choice, which is okay if you don't have a lot of data, is to put one at every training instance. Everywhere there's a data point, I'm going to put a Gaussian function. What this Gaussian function is doing is like spreading out its influence, okay? Which is what's going to let me classify points that I haven't seen before. Another one is to cluster the instances, right? It's the idea of prototypes. I'm going to put a Gaussian where there's a big density of points. So instead of having millions of Gaussians, I'm just going to have 100 important ones. Okay? So this is step one. Step two is, now that I've put those bumps in space, right, how do I combine it? Well, now I can do linear regression, and it's okay because this linear regression is on top of something that is very powerful, namely those kernels. Right? So the combination of the linear, so this part here, these weights, can be found by linear regression. Okay? It's very powerful linear regression because it's not being done directly on the input dimensions. It's being done on the outputs of the basis functions. Okay? So again, where a linear function would be very simple, once I'm doing only a combination of these basis functions, I could have a very complicated and smooth function. This is not going to be piecewise linear anymore. It's not going to be jagged and ugly. It could be very smooth. Okay? So I can do that just using linear regression. The clustering can also be done using various methods. We're going to look at some of these things in the future. I could use k-means. I could use the EM algorithm. Another thing that I could do for this whole process is to use the backpropagation, which is a way of training neural networks, which we will see later. Okay? So this was a very brief introduction to radial basis functions. Any questions about this? Okay, so here is a completely different type of instance-based learning, but I think really gives you a picture of how general and powerful these methods can be. And this is a whole class of approaches that is very popular in practice, and it's called case-based reasoning. Case-based reasoning is probably the most widely used machine learning method in help desks. As you know, one of the biggest costs of software is the help desk, is when people call up and say, like, I don't understand what this program is doing. How do I fix it? Or like, my PC just broke down. What do I need to fix? Or how do I accomplish X? Right? And it's very expensive to have people manning the phones and then, figuring out the problem with you. If you could somehow partly automate this process, it would be really good. Even if the automation is just that the person on the help desk can quickly input the parameters of your problem into the computer, and the computer gives it a suggestion as to what the problem is. So case-based reasoning is very popular for this. The idea in case-based reasoning is that you're basically going to apply instance-based learning, but in a very rich symbolic space. Your procedure that computes similarity is going to be very complicated. It could be a huge program. So, for example, let's say, you have a help desk for computers, and your instance is described by something like, the user's complaint is that you get error 53 on shutdown, here's your CPU model, here's your operating system, here's the network connection that you're using, your amount of memory, and so on and so forth. Now, what is the problem? Okay. If you think about this is not that different from medical diagnosis, right? So maybe that, naive strategy of like, let me find the closest case and apply it, that might work. And if you think about it, and this is a large part of the reason why this works well for help desks, 80% of the problem that people have, somebody else had it before, right? And so if their case is similar enough to yours, right, then the person at the help desk can just retrieve that case and say, like, well, how about you try this? Because it's what worked for the other person. And then instead of it taking an hour to figure it out, it takes 2 minutes. Okay? So this is case-based reasoning. Here's a concrete example, still at a fairly, shallow level, but to give you an idea. From another domain, this is actually a real system called Cadet. And what it does is design mechanical devices. So like, say for example, you're a plumber and you want to design the plumbing for a house. And, you want to figure out, faucets and, joints and whatnot, right? This could take a lot of time and require a lot of expert knowledge. How can we do this using case-based reasoning? Notice that we're actually quite far at this point from just your plain old nearest neighbor making a class prediction, but how can we do this? Human experts, like, say an expert plumber or anything, they don't go into a new problem tabula rasa, right? They know all these things about how they've done the plumbing in previous houses, or how they've, built different devices and whatnot. And what they do is that they create a new solution by assembling pieces of previous solutions, right? And this is exactly what we want to do here. Okay? So in this problem, each training example is the function that you want to be performed by the mechanical system, and so that's the input. The output is the mechanical structure that performs that function. Okay? Let's say routing water one way or another, and so on and so forth. So that's your training set. This is what you wanted. This is the device that was built for that. I have a pump. that does this for you. Or I have, whatever, right? And the new query is the new desired function. What I want, right, is to figure out what the mechanical structure is that accomplishes this function. Okay? And I have a big library of these, right, coming from here. So the first thing that I need to do is I need to find matches to my new function in the library among the old functions. Okay? So here again, I need a distance function, but now this is probably going to have to be a fairly intelligent distance function because, just saying these things have features in common probably doesn't quite do it, right? They could actually need very different structures. And then part two, which is very much, characteristic of case-based reasoning and not just plain instance-based learning, is that I need to find a way to combine the pieces into the solution. It's not just a matter of voting anymore, right? I'm going to take one piece from this solution and one piece from that solution and combine them, okay? So for example, let's say that you have a stored case that was a T-junction pipe. In comes water and, at a certain temperature and, a certain flow. So you can represent this symbolically like this, right? Q1 and Q2 get combined to give Q3, where this is the flow, and same thing with the temperatures, right? And now what you want is a faucet. What is a faucet? You want it to obtain a certain volume and temperature of water, right? So you want something like this. You have your cold input and your warm input, and out of that you want a certain resulting temperature, right? And you want a certain resulting volume. And now what I can do is hopefully retrieve cases like this to actually find the structure that solves this problem, and you've just invented the faucet. I'm being a little superficial here, right? But this is just to give you the idea of how these methods work. Okay. As I said, case-based reasoning methods are very popular for a lot of things, and in particular for help tests. Okay, so to summarize, the last thing that we're going to look at today is collaborative filtering, which, as I said before, is probably the most famous application of instance-based learning these days, and it's what your project is going to be about. But before that, let us try to summarize the advantages and disadvantages of lazy and eager learning. So at this point in the class, we've seen two eager methods: decision tree learning and rule induction. And today we saw, today was lazy day, was instance-based lazy methods, right? So let's look at their differences and their pros and cons, right? So with lazy methods, you wait for the query before generalizing. You don't try to form a general definition of your concept ahead of time. That is too difficult, that's too much work. So what you do is you wait for the query, and then when you see it, you form a generalization just for the purpose of, answering that query, okay? Examples of this are, on the simple end of the scale, k-nearest neighbor, and on the sophisticated end of the scale, case-based reasoning. Okay? Eager is very different, is you generalize ahead of time. I get my training data, I do something with it, and then I have a decision tree. I have a set of rules that is ready to go. And when the query comes along, all I do is apply it. And of course, it'll often be faster. So ID3, FOIL, these are examples of this, and next week you're going to see naive Bayes, and then we'll see neural networks. All of these methods are eager. And most of the methods in machine learning are eager, but a lot of the time you want to use a lazy method. Okay? What is the big difference between them? So you would naively think that eager methods were better than lazy, right? This is what your mom taught you, right? Be eager, don't be lazy, right? Don't live for tomorrow what you could do today. With lazy methods, it's exactly the opposite. Leave everything till tomorrow, please. Don't do anything today, right? The thing that's slightly surprising and perverse is that because the eager learner is actually less powerful than the lazy learner. The lazy, unlike in real life, unlike with people, the lazy ones here are more powerful than the eager ones. And the reason they're more powerful is that the eager methods have to create a global approximation, and the lazy ones only have to create a local approximation. In fact, sometimes this whole class of methods is just called local methods, precisely for that reason, is that they do everything locally, around the neighborhood of the query point. Because they're doing everything locally, right, then the same machinery being brought to bear becomes much more powerful. Okay? So using the same hypothesis space, lazy methods can actually represent much more complex functions than eager ones. And we saw a very good example of this with linear functions. Linear regression is a very limited thing, but if you apply it lazily, it actually becomes very powerful. In fact, in the limit, just as with nearest neighbor, that piecewise approximation becomes a perfect approximation to the real curve. Okay? So lazy methods have a lot to recommend them. They also have disadvantages, which we saw, so you want to, given a new case, figure out which one is best for you. But as a rule of thumb, I would say that key nearest neighbor is one of the first things you want to try on any problem. Decision trees are easy to run, so is nearest neighbor, so why not do those easy things first before you do the complicated ones? And you might think that this is obvious, but I unfortunately see people in practice doing this thing of they go straight for the sexiest, latest, most sophisticated, mathematically intricate methods because, it makes them feel strong, right? And they could have used something much simpler and you would have done the same job much faster. So remember to use the simple methods first is another moral of this story. And as a great illustration of that, let us, conclude today's class by looking at collaborative filtering, also known as recommender systems. Everybody here know what collaborative filtering is? Let me just briefly define what the problem is, right? So, you're Netflix, right? Does everybody here know Netflix? You rent DVDs for a living. And what you would like to do is recommend to people other DVDs for them to watch. Because for two reasons, actually. That way, maybe you'll watch more DVDs, right? So Netflix makes more money. Actually, for someone like Amazon, they make more money this way. They can quantify that, recommending other books that, other people liked and whatnot. This increases their bottom line, but I don't know what the number is, but it's a large number. So let's say 20%. 20% more just by doing this. It's a lot of, return on investment. For Netflix, however, it's actually a little bit more subtle, right? Because you have a subscription fee, they don't necessarily make more money by renting more DVDs to you. You know why they make more money? You know why recommender systems are so critical to them? Is that the popular films are expensive for them. They have to pay the studios more for the popular films. What they want to do is shunt you towards, British TV shows from the 70s that cost them a penny each. This is a real example, right? British TV shows have never been so popular in America because of Netflix. And the way they do that, but of course, why are you going to watch some obscure TV show that you've never heard of and have no reason to think is good? If they have a good machine learning algorithm that can tell from the movies that you've liked, which of these things, more obscure movies, B movies, TV shows you like, then you'll rent those and you'll like them and you'll believe the recommendations and keep going. Okay? So collaborative filtering is a big deal these days. Any e-merchant worth its salt, has a collaborative filtering system recommending things for you to buy or see or do or whatever. Okay? So the goal here is to predict for each customer and each item, let's say it's a web page or even a news group posting, a movie, a book and CD, whether you will like it or how much you will like it. Okay? And so in the beginning, people approach this sort of like the traditional machine learning way, which is, let us look at attributes of these items. Is this an action movie? Does it star Arnold Schwarzenegger? Do these things predict that you like the movie or not? And these things are not bad, right? Some people hate Arnold Schwarzenegger, and if the movie is with Arnold, they won't see it. Some people watch a lot of action movies, some people watch a lot of dramas and foreign movies and whatnot. But you run out of juice with this pretty quickly because people's tastes are not that simple. It's very hard, if you think about it, to predict whether you will like a movie just from its general characteristics. And then somebody had this amazing idea of collaborative filtering. And the idea was, no, let's not look at the characteristics of the product. Let's look at what other people did. This is actually a much better signal. These other people, what movies did they like? Which ones did they give 5 stars to? And how similar are these people to you? Right? We're going to do this by saying, let me find people who have similar tastes to yours and use their preferences to predict yours. Bingo, this works way better than prediction just based on content. Now what really works best of all is to combine the two, content and other people. Right? But if you're only going to do one of these, you should certainly pick people. It works better than the content. Okay? So that's why this is called collaborative filtering, is that we're filtering out, the DVDs to figure out what the good ones are. But it's like there's this big collaboration going on between all the, 100 million users of Netflix or whatever it is. It's a powerful thing, right? You've had 100 million people collaborating to give you recommendations. You don't just have 5 friends that tell you what's a good movie to see. You have 100 million people on Netflix. Okay? And of course, some of them have tastes completely different from yours, but we filter those out. We figure out the people who could be, across the world, right, and very different from you demographically and whatnot. So like, these people seem to have very similar tastes because they tend to like the same things and dislike the same things. Well, then I'm going to use that person's preferences to make recommendations to you. Okay? So this is the idea in collaborative filtering. So how might we do that? Well, let's see. First of all, how do we represent each user? Let's just represent each user by a vector of their ratings. Right? This is how you have rated previous items. Like, for example, how many stars you gave to previous movies. And there's really two types of rating. There's explicit ratings, which is what people used early on, like literally how many stars did you give this movie on Netflix, right? But what people found then is surprisingly powerful, is actually a lot of the time you don't have those ratings, right? Nobody gave ratings, right? But there's still something you can do, which is just use the fact of whether you bought the book or not, right? Even if you didn't rate the book, the fact that you bought it is a sign that you at least thought it would be interesting to you. In fact, even just having gone to that page is a good sign, right? If I clicked on the web page, it's a sign that that page is interesting, more interesting than the pages that I didn't click on, right? You're a search engine, you give people 10 results, you click on these 2. Well, they're probably more interesting to you than the 8 ones that you didn't click on, right? So you can actually do a lot with just ratings of the implicit type. The basic algorithm is the same, and then it can vary, but the important thing to remember here is you don't need ratings to do collaborative filtering. You can just do collaborative filtering based on yes, no. What did you buy? Where did you go on the website, and so on and so forth. Okay. So you are now represented by a vector of yes, no, I bought this book, no, I didn't buy that book, or I gave 3 stars to this movie, 5 stars to that one, and so forth. Right. So now people are each person is a vector, and my entire population of Netflix users. This was the data for the Netflix prize. Right. Was a large number of people and the ratings that they had given to various movies. Okay. So now the question is, how shall I predict the rating that you would give to a movie that you haven't seen? Right? This is what Netflix is doing. It says, oh, by the way, I think that to this movie you would give a rating of 5, so, rent it. Right? So how shall we predict that? Well, you can use some type of instance-based learning, right? Look at similar people and use their rating on that movie to predict yours. Right? Very natural idea if you're familiar with instance-based learning. So how might you do that exactly? Well, here is in 2 lines. The main algorithm that people use and that you're going to implement in your project, it really is just these 2 equations. You have a paper that you can read to do the project that has lots of interesting details on other methods and whatnot, but it really just boils down to this. You could walk out of here today and start implementing it. And again, there's many other variations, but this one is actually pretty hard to beat, despite its simplicity. So here's what we do. And then we will unpack it and see what's subtle about what's going on here. Not all of it is actually very straightforward. So, RIK is the rating of user I on item K. Right? It's how much person I liked item K. And notice that there's a hat here, which means that this is our estimate. Okay? So my estimate of how much user K is going to like item K, is going to be RI bar. This is your average rating. Okay? So if the average rating that you give to movies is 2.57, that's what this is going to be here. Okay? And then alpha. Let's ignore that. The alpha is just for normalizing things, so no big deal. Let's ignore it for the moment. Sum over your neighbors, right? So I have to pick your nearest neighbors. Again, in general, I could use all of them, but let's just say that in general I do pick your neighbors, right? By some measure of their rating for the item, right? So now J is ranging over your neighbors, right? So this is your neighbor J. The rating that your neighbor gave on that item minus your neighbor's average rating. Right? So if your neighbor gave a rating above their average, and they're similar to you, I'm going to predict that you're also going to give a rating above your average. And conversely. Okay? And then this is going to be multiplied by a weight, right? So what we're doing here is just, distance weighted K nearest neighbor for regression. Right? No big deal. Okay? So, but what should the distance measure and what should the weighting function be? The people who did this, who first started doing this tried, gazillions of things. One thing that worked very well and is still, used is the Pearson correlation coefficient. What is the Pearson correlation coefficient? It's just a measure of whether two variables go up and down in tandem or not. So, here's the Pearson correlation coefficient between users I and j. And we use this both to select the nearest neighbors if we select them and as the weight for the neighbor. Okay? So somebody with a higher Pearson correlation coefficient with respect to you will have a higher weight in the predictions that are made for you. Okay? So what is the Pearson coefficient? It's just the following. It's the sum over all the items of your rating minus your average rating times your neighbor's rating minus their average rating. So again, what this is capturing is if your rating is above your mean, when your neighbor's rating is above their mean, and both are below at the same time, then you tend to vary in lockstep and the correlation is high. Right? You will get a high positive number when you sum this for all items. Right? On the other hand, if when you give a high rating, your neighbor tends to give a low one, and vice versa, then you're going to get a large negative number. You're going to have a negative correlation. Right? This is probably not a good person to make predictions for you. In fact, ironically, they might be good because if somebody has the exact opposite taste that you do, well, predict the opposite. In practice, doing that actually doesn't work so well, but it's an interesting twist. What will happen with a lot of people is just, well, sometimes you go up and they go up, sometimes you go up and they go down, and it's just noise and the correlation is close to zero. And you ignore those people too. Okay? Now, the denominator here has to do with the fact that you don't want to say that you are correlated just because you guys both give large values, right? The absolute scale on which you're grading, like some people are more, manic depressive than others, right? This shouldn't depend on how manic depressive you are, right? For example, if there's somebody who, when you like something a lot, they like it a little, and when you dislike something a lot, they dislike it a little, and you're always going in the same direction, right? They're a very good predictor of you, right? So I want to normalize this by just how much these things vary in total, and that's what this denominator is doing here, okay? It gives me a number that is always between -1 and 1, okay? So +1 means you guys are perfectly correlated. This person predicts exactly the same things as you do. 0 means there's no relation. -1 means they're exactly the opposite of you. When you give it, 5, they give 1, and vice versa. Okay? Any questions? So you could go and implement this tomorrow, but there's a couple of subtle issues here that we need to deal with, and there's also a couple of things that you might be wondering why, this looks exactly like this, right? So why are we doing this thing of subtracting the mean? Right? This is a little different from the basic nearest neighbor algorithm that we saw before. So let's look at those issues. The first thing that these people tried was the simpler version, was just this. I predict your expected rating on item K is just the average over your neighbors of their expected ratings times the weight. Right? This is the natural thing to do. Right? And then the people who did this, like every good machine learning person does, they tried a whole host of different variations. And most of them, as is usually the case, didn't make any difference or made things worse. But there was one thing that made a huge difference and which has always, been kept from ever since then. And this was exactly going from this version to this version, where what I'm doing is I'm looking at the difference between your neighbor's prediction and their average, and the difference between you and your average. Why is this so important? Because some people are grumpier than others. Some people kind of, are happy-go-lucky. They always kind of like things. And some people they're down on everything. They always hate, right? So consider the following two people, right? They have exactly the same tastes, but one is more of an optimist. So let's say I'm the optimist, and let's say you're the pessimist, okay? Or the reverse, okay? When I give 5, you give 3, okay? And when I give, let's say, 3, you give 2. And when I give, 2, you give 1, right? So we're completely well correlated, right? The difference is that we have different means, right? I'm oscillating above my high mean, and you're oscillating above your low mean. Okay? You are a perfect predictor of my tastes. We shouldn't let the fact that, one of us is an optimist and the other one is a pessimist get in the way of that, right? But if we just use this sort of plain version of nearest neighbor, that we wouldn't get that, right? You would look different. So the morals of the story is you need to subtract everybody's mean from their ratings. because I'm not interested in what your absolute ratings are. I'm just interested in whether like you're rating above your average and I'm rating above my average. If we will both rate above the average consistently when the other one does and vice versa, we're good. Okay? So this is one small change, but it's one that makes a very big difference to the accuracy of the system. Okay? So the alpha, as I mentioned before, is just a normalization constant, is just the sum of the weights, 1 over that, right? To make sure that, again, this is all normalized, okay? Another point here that we've alluded to is that your neighbors could actually be the whole database. You can do things that way. On a large scale, you probably don't. So you only want to pick, some number of neighbors. And there's actually something that you could play with in your project is, try different numbers of neighbors and see what happens. What typically happens, this varies by time and whatnot, is that you are better off selecting some number of neighbors, but it's usually a pretty large number compared to what's traditional in KNN. In KNN, people typically wind up using something like 3, 5, 7, a small number. In collaborative filtering, it's normal to use, 20, or there's this tradition of using, odd numbers. Odd numbers avoid ties when you have two classes, right? But people still, use them, right? So you might use something like 21 or 37. Probably because, if you have something like Netflix, there's a lot of people there probably are 30 people, in the whole world that have tastes similar to yours, so it makes sense, okay? Again, this is a parameter that can be set by cross-validation, okay? And now here's a couple more subtle issues. Notice that RJ is the average of all your ratings. You haven't rated all the movies. This is something that we've glossed over so far, is that I do not have complete data in this matrix, right? Netflix, has I don't know how many movies, right? Probably 1 million or millions of them. And you've rated maybe 100 of them if you're a particularly assiduous user. So most of those things are blanks. So number one, your average rating is just the average over the things that you rated. Point one, right? And now point two, right? And even more importantly, how do I compute the Pearson coefficient when most of you guys haven't rated most of the movies, right? I have to compute it only over the movies that you have both rated. If you've rated some movies and I haven't, well, I can't decide what our correlation is based on those, right? So the first thing that has to happen is that we have to look for people who've actually at least watched the same movies. And then among those, we have information to decide whether they tasted the same or not, right? So you have to ignore those things when you compute the coefficient, which is different from what you do traditional, which is, compute these things over all the data, except in this case, you don't have the data. Okay? Another important point to notice is that even after you've decided that you're going to use other people's ratings to predict yours as opposed to the properties of the object, you could still use any machine learning, algorithm on Earth to do this, and moreover, people have. In fact, the paper that you have for the project compares a few of these. And this paper has its own very sophisticated probabilistic method to propose, and and other people have too. But the moral story is like, even after 10 years or more of people doing this, the simple, instance-based method with Pearson coefficient is still hard to beat. Maybe you can beat it, but it's not really worth the trouble, of going to a more complicated method to get just a slight improvement. And in fact, in the Netflix prize, in the famous Netflix prize, somebody won $1 million for improving. So what Netflix said was like they had their own best in-house algorithm called Cinematch, and they gave $1 million to the first team or the first person to improve this by at least 10% in absolute error. And people didn't even know if this was going to be possible going in, but within, I don't know, a year or something like that, people have passed that threshold. And the amazing thing is that when you look at the winning entry in the second best one, they were both combinations of a lot of things, but mainly they were combinations of instance-based methods and another class of methods that we're not going to talk about here, which is matrix decomposition methods. But the interesting thing is, even after all these years, even in this competition of all these people trying all these fancy methods and different ways of doing things, this was still basically one of the top 2 methods for the problem. Okay? Questions? Okay, so before you start having fun with the actual net, so what we did with the Netflix data, by the way, is like we're not asking you to run your stuff on the whole data set, right? Because that might burn too many cycles. We self-selected a small subset of it. Okay, and we also selected a dense subset, meaning there's a lot of ratings in that subset. If you just picked a random subset, you would have almost no ratings and nothing useful to do. Okay, the reason I'm bringing this up is don't get too excited when your methods do very well. We actually used this once in class before at the time of the prize, and people were like, going ballistic, going like, hey, I'm doing better than the people in the competition right now. Well, because they weren't doing it on the real data set. They were doing it on a dense data set that was much easier. Okay? So bear that in mind. But on the other hand, if you want to go on to trying things on the real data set, it's also available, so you can. Right? And the Netflix prize is over, but if you find a new, better collaborative filtering algorithm, I can tell you, there's a lot of people in industry who would be quite happy to hear from you. Some of them in this very town. Okay? All right, so let's just see a very simple example of this to make things concrete, right? Let's suppose that I have, 4 users, the ever famous Alice and Bob, and also Chris and Diana, right? This is a real big data problem. And I have 6 items, R1 to R6, okay? And let's say that, I'm interested in Alice, right? So I want to predict whether Alex, will like R5 or not. Let's say these are movies, right? I want to predict Alice's rating on the 5th movie, okay? So now let's see. First of all, Alice is actually a pretty good user. She's rated a lot of movies, but not all of them, right? So I'm going to have to ignore this R2 here to start with, okay? And then the first thing that I have to do is, compute the similarity of Alice to Bob and Chris and Diana, okay? And notice that, some of these people have more data and some of them have less, right? So for example, Diana doesn't actually have a lot of data in common with Alice, okay? But Bob and Chris do, for example, right? And in particular, Diana has a very serious problem for our purposes, which is what? Remember, I'm trying to predict how much Alice is going to like R5, right? Will Diana be helpful for that purpose? No. Why? She hasn't rated it, right? So, right up front, we can get rid of Diana. She is not going to help us, right? Okay, so now we're down to Bob and Chris, right? So, without actually computing the Pearson coefficient, who do you think is more similar to Alice, Bob or Chris? Bob, right? Why Bob?
The ratings are similar.
Yeah, right. So let's look at the ratings that they have in common, right? Again, they've both rated a bunch of movies, but they don't have that many movies in common with Alice, right? So let's look at the movies that both Alice and Chris have rated, right? So Alice gave 2 to R1 and Chris gave 5. So Chris really liked that movie, Alice not so much. And then Chris gave 2 to movie 4 and Alice gave 4. So here it's the opposite. Alice liked it and Chris didn't. So do you think these guys are highly correlated or not so much? They're actually negatively correlated, right? So Chris is actually not a very good predictor of Alice, right? What about Bob? Well, R1, neither of them liked it, right? Bob, kind of hated it, and Alice just kind of thought it was mediocre, but neither of them liked it, okay? Now, Bob didn't rate R4, but he did rate R3, and so did Alice, and here they have the exact same score. So hey, Bob and Alice are pretty similar. So, what do you think our prediction for Alice is going to be? Again, you don't have to predict it exactly, but it's going to be roughly what?
4
4?
value minus the mean. 3 or
Yeah,
3.
exactly, precisely. So it's going to be somewhere around 3, right, adjusted by the difference of the means, right? But it's the prediction for Alice is going to be mainly determined by Bob because he is her nearest neighbor in this data set. And then we have to do that whole trick of adjusting. But basically, we're going to probably predict that Alice is going to have a middling amount of liking for this movie. Okay? Questions about any of this? All right, so we covered a lot today, and as usual, now it's over to you. We've published the second assignment. So as soon as you're done, with QuickStreamMine, you can go straight on to collaborative filtering. And before you know, you'll be machine learning pros. And then you'll do a startup and become billionaires and donate $1 million to UW, right? To have an endowed chair in your name. Okay, so if you don't have any questions, thanks for being here. I know this was an inconvenient time, but I think today was a useful class. You learned some very simple and yet very powerful methods. And I will see you again. All right, let's get started. Welcome back. Long time no see. Are you having fun with collaborative filtering? You don't remember that you did it so long ago. Right? Then, I I read this blog from the folks at Netflix last week that says that for the first time they reveal a bunch of stuff about how their collaborative filtering system works. It's actually pretty interesting. Not just the machine learning that depends on that have to happen. But the single thing in there that kind of struck me the most is they say that about 75% of everything that people watch comes out of the recommendation system. This is how important it is to their business. 3/4 of everything that people watch comes out of it. The other thing that was striking was the size of data sets that they're applying things to. Right, one of the main jobs has been to scale up algorithms like the ones that were in the Netflix competition to 5 billion ratings. That's a slightly bigger project than the one that you're doing. But at heart, it's all the same, right? So now you know how to do it. Okay, so in the meantime, today we're going to talk about one of the largest and most intensively researched areas of machine learning. And in fact, these days you could say it's the core, right? Or a big piece of the core of machine learning. And this is what's known as Bayesian learning. Bayesian because it's based on the famous Bayes theorem, or more generally, statistical learning. Okay? And there's a lot to cover. You're going to learn a lot today. So here's a preview of what we're going to talk about. So first of all, we'll review Bayes theorem, and we'll see what an MAP learner is. MAP is short for maximum a posteriori. And maximum a posteriori means you want to return the hypothesis that is most probable after you've seen the data. This is what a posteriori means. We'll see the notion of a Bayes optimal classifier, which is a theoretical notion, but it's a very important one. And then we'll look at one concrete practical learner, which is naive Bayes, which is, of course, the algorithm that span filters are, or at least traditionally have been based on. And in it, we will see how to apply naive Bayes to text classification, which is what span filters do. In fact, this is what a big chunk of your third assignment is going to be. So for those of you who are already done with collaborative filtering, tonight before you go to sleep, you can do your span filter, and that's a good chunk of the assignment then. And then we will look at a more powerful type of Bayesian learning than naive Bayes, which is learning Bayesian networks. And then we will look at finally, we will look at one of the most famous algorithms in all of machine learning, which is the EM algorithm. Okay, the EM algorithm is used. It's really an algorithm schema. It's used for a very wide variety of things. So it's definitely very well worth
Is your microphone on, Pedro?
Pardon me?
Is your microphone on?
Oh, I assumed it was on. You folks at Microsoft hear me? I guess
Kind of.
It's not very loud. Kind of low.
How do I tell if it's on or not?
You should see something on the front.
Yeah, I don't see anything. Oh, yeah, it is on. So shall I repeat or?
Oh, they could hear you. The room mics were picking up. It'll just sound better now.
Okay, all right. This was a little experiment in learning from noisy data. Right? This is so that you have a sense of what machine learning really is like, right? There's all this noise, and then there's this weak signal, and you're trying to pick up the signal from the noise.
I think the UW slide missed out on.
The what?
The UW slide missed out.
I know. Yeah. So see, these are the advantages of remote learning. Yeah, you get a more full experience of what machine learning is all about. On the other hand, you're also less prone to hallucination if you have a higher signal-to-noise ratio. So, okay, so Bayesian methods actually play two important but very different roles in machine learning, and it's important to be aware of them. And some of what we're going to be doing here is for one role, and some of it is for the other. The first role is as a set of learning algorithms. Right? There's many practical learning algorithms that naive Bayes that come out of Bayesian learning. And these algorithms have, they include things like naive Bayes learning and more general Bayesian network learning. They have a very important feature for our purposes that they're going to give us a new way to combine prior knowledge with data. Right? We saw in the very first week that machine learning is not just about the data. You have to bring some knowledge to bear. And the easier it is to bring that knowledge to bear, the more likely your machine learning will do well. Right? And then when we studied rule induction, we saw one way of providing that knowledge, which was to just state things in the form of rules or first-order logic. Okay? But one of the big advantages of Bayesian learning is that it provides a different way to include prior knowledge. In particular, in the form, as we'll see, of prior probabilities. So we're going to see what prior probabilities are and how we can use them to encode prior knowledge. But the other main role that Bayesian methods play is actually different from the things that we've seen so far, is that you can use Bayesian methods as a way to analyze any learning algorithm. So for any learning algorithm that we've seen so far and that we're going to see in the future, there's a Bayesian version of that. You can learn decision trees the Bayesian way. You can have Bayesian instance-based learning. You can learn rule sets the Bayesian way. So Bayesian methods provide a way to answer questions like, how well is this learner really compared to the best that you could do? So they provide a gold standard, which is the Bayes optimal classifier. And the other thing that they let us do is they let us analyze an algorithm. And analyzing is a help to maybe coming up with a better version. Okay? So these are the two roles of Bayesian methods, and we're going to see some examples of each. And as always, if you have questions at any moment, please feel free to ask them. So how many people here have heard of Bayes' theorem? Yeah, that's most of you. Okay, so Bayes' theorem is like a household word these days, right? Which is kind of amazing. What is Bayes' theorem, right? And why is it so important? Well, first of all, Bayes' theorem is something so simple, it's barely worth calling it a theorem. Right? So this is, and the proof of Bayes' theorem is actually so simple that you usually barely even see it. So what is Bayes' theorem and why is it true? And then we'll see why it's important, right? Usually you call something a theorem because it's a combination of it being difficult and being important. In the case of Bayes' theorem, it's not difficult at all, but it's so important that it rises up to the level of being called a theorem. So here's Bayes' theorem. So let's say that H is my hypothesis. And this hypothesis could be something as simple as, I'm a doctor and I'm diagnosing the fact that you have cancer or not, right? So it's just a binary hypothesis. You have cancer or don't have cancer. Or it could be a whole decision tree, right? You give me a bunch of clickstream data, and from that I induce my hypothesis about how people behave, right? What makes you leave my site? What makes you click on this page? What makes you do this and that? Okay? So this is the hypothesis. And D is the data. Okay? And what I want to know is what is the probability of my hypothesis given the data, right? I want the fact that I've seen this data, these measurements or these tests or symptoms or these click streams. I want my hypothesis or my choice of hypothesis to be influenced by the data that I have. And Bayes' theorem is an answer to the question of how do you do that? So here's Bayes' theorem. It says that the probability of the hypothesis given the data is a product of two things divided by a third. The first thing, P of H, is what's called the prior probability of the hypothesis. It's how much you believe in the hypothesis before you even see the data. Like I'm diagnosing, say, people for breast cancer, and I can have a prior probability that somebody has breast cancer before I've even seen them. Right? Before you even walk in my office, I don't know anything about it, so like, 1% of people get breast cancer. That's my prior probability. It's how much you believe in the hypothesis before you've seen anything. The second term is the probability of the data given the hypothesis. This is, for example, the probability that your test for, say, TB will come out positive given that you do have TB. Okay? If you think of the hypothesis as the cause and the data as the effect of that cause, like for example, you have these symptoms because you have this disease, or there are these words in the document because it's about, sports or something, then what this is really saying is what is the probability that this cause produces these effects, right? What are the chances that you have, a high temperature if you have the flu, right? That's what this is doing. And finally, this term here is just the probability of the data. This is the probability of seeing that data irrespective of which hypothesis is true, right? What is your probability of having, a high temperature, irrespective of, which disease you have or of whether you have any disease at all? Okay. And so Bayes' theorem just says that the probability of the hypothesis given the data is the prior probability of the hypothesis times the probability of the data given the hypothesis, also known as the likelihood, divided by the probability of the data. Okay. So we're going to see an example of this shortly, but first of all, why is this true? And the reason that this is true is actually shockingly simple. It just has to do with the following. You see this P of D here? If you put it over on this side, right, what you get is P of D, right? I can multiply both sides by P of D. It disappears from the right-hand side and it appears on the left side. It just says P of D times P of H given D is the same as P of D given H times P of H, right? And if you think about it, these are just two different ways of computing the probability of D and H. The probability that the hypothesis is true and I see this data is the probability that the hypothesis is true and then I see the data given that it's true, right? This is one option. The other option is that, well, this is the probability of the data and this is the probability of the hypothesis given the data, right? So these are just two different ways of writing the joint probability of these two things. And Bayes' theorem is just a one-line consequence of that. So Bayes' theorem is really just a restatement of the definition of conditional probability, which you might remember from your Stats 101, all those years ago. Okay? Questions about this so far? Why is this important for us? Right? So we're doing machine learning. Let's say we're learning, decision trees. We want to choose a good decision tree, right? How do we choose what is the best decision tree? Right? This actually, Bayes' theorem gives us a way to decide which decision trees are better and which ones are not so good. Namely, the better decision trees or the better whatever are the ones that have the higher posterior probability, hence the name MAP, maximum a posteriori. And that posterior probability is a function of two things. One is how much you believe the hypothesis a priori, and the second one is how well those hypotheses agree with the data. Okay? So let's say that, let's call my most probable hypothesis my HMAP, right? HMAP is the hypothesis that maximizes P of H given D, okay? So argmax H in H means the hypothesis in H that maximizes this expression, okay? So, okay, very good. I want to pick the hypothesis that is most likely considering both my prior beliefs and my data, right? And now let's apply Bayes' theorem to that, right? Which means that I can replace this by this, okay? So all I did from this step to this step was apply Bayes' theorem, okay? And so far I haven't gained anything, right? And now in the next step, P of D has disappeared, right? Why has P of D disappeared? Yeah, exactly. P of D is the same for all the hypotheses, right? It's the probability of the data irrespective of the hypothesis, right? And so it's the same for all the hypotheses and doesn't affect, it's going to affect the value of the MAP, of the posterior probabilities, but it's not going to affect the choice of MAP hypothesis, right? Because it's going to raise or lower them all by the same amount and the winner is still going to be the same, okay? So we get this. And now you might ask the question, okay, but what was the benefit in going from here to here? Well, the benefit is that it's hard to figure out what this is, directly. Now this has divided things into two pieces. One piece is your prior beliefs, right? You can assign higher prior probabilities to the things that you have some reason to believe are true, right? Usually you have a lot of knowledge about the problem, or hypotheses or assumptions that you're willing to make. This is where you can encode them, right? So in Bayesian methods, this is the new place that you have to put in your knowledge of the domain. It's your prior distribution over the hypothesis. Okay? You could say that some things are completely impossible. You just don't believe that they could happen. Or you could say that some things are possible, but one is twice as likely as the other, and so on and so forth. Okay? For example, you could say that larger decision trees are less likely than smaller ones, because you believe that your phenomenon really is described by a small decision tree, okay? But turns out we can simplify this even more. We can, let's say, and this is often the case, that we really are lazy, right? As I keep saying, machine learning is great if you're lazy, like me. And like specifying prior probabilities is too much work, right? You have to think too much, right? And we want this all to be automatic. Right, so if you don't want to have to figure out what is a good prior probability for each hypothesis, what can you do? Very simple. You can just assign the same probability to all hypotheses. So like, a priori, I don't care. It's like Monsieur Laplace and whether the sun will rise or not before you've ever seen the light of day. Right? So if you assign the same probability to all hypotheses, i.e. you have a uniform prior distribution over the hypothesis, then this part, right, is also going to be the same for everybody, which means that you can do what? Right, you can drop it just like you dropped P of D, right? And then you just get this. You get that the hypothesis that you should choose is the hypothesis that has the maximum probability of the data given the hypothesis. Also known as the likelihood, right? So the likelihood is the probability of seeing the data as a function of the hypothesis, right? And so now I'm calling this HML, where ML stands for maximum likelihood. Okay? And this is actually what typically study in Stats 101. They study, how to find the maximum likelihood hypothesis, and we're going to see an example of that shortly as a reminder. Okay? So what are the pros and cons of going the maximum likelihood way versus going the Bayesian way? One advantage of going the Bayesian way is that you do have this way to encode knowledge about the domain. Okay? The disadvantage is that you have to do that. And some statisticians really quibble with the notion of you just pulling some numbers out of thin air and saying like, well, I believe that a priori, this hypothesis has a probability of, point whatever, right? The question there is like, well, we're supposed to be looking for an objective answer, and this brings in subjectivity. The Bayesian answer to that is that subjectivity is inevitable. And when you use maximum likelihood, right, apparently there's no subjectivity there, but really you're making the assumption that all hypotheses are equally likely a priori, so that assumption is hidden in there anyway. Okay? So there are these two schools of thought in statistics, the Bayesians and the frequentists. The Bayesians believe in subjective probabilities. The frequentists believe that the only legitimate probabilities are things that are the frequency with which something happens, or the limit of that as you do more and more trials. So for a frequentist, it doesn't necessarily make sense to ask the question, what are the chances that, Mitt Romney will be the next president, right? Well, we don't have 1,000 trials of that to compute how many times, he became president versus how many times Barack Obama won, right? But from a Bayesian point of view, it makes sense to ask that question. It's like, if I ask you now, make your best judgment, and you can probably come up with something, okay? So for most of this class, we're going to follow sort of like the Bayesian view of things. But it's good to remember that sometimes when we use a prior probability, it's going to be a prior probability that's computed from data, right? We're going to have a set of documents, and some of them are going to be on sports. There's 10,000 documents, 1,000 of them are on sports, and so my prior probability of sports is 0.1, and nobody disagrees with that, right? Bayesians and frequentists both agree with that. What frequentists disagree with is when I say, well, I think that a priori, simple decision trees are more likely. And then the frequentists will go like, well, but why, where did that come from? Okay. So, I think the right attitude to these things is to not fall into either camp, but to be open-minded and to use the appropriate tool for the job, right? So I think we should look at this as, it's one more set of tools that we have to do machine learning with, okay? All right, so let's see a nice example, classic example of Bayes' theory. All right, we have a patient. And we want to decide if this patient has cancer or not. Okay? So the patient takes a lab test. Right? This is actually literally what happens when you go in. But lab tests are not perfect. Right? If the lab test says that you have cancer, you don't have 100% certainty that you have cancer and vice versa. Okay? So, but let's say that the patient went in and the result was positive, but the test only returns a correct positive result in 98% of the cases where the cancer really is there. Okay? So when the cancer is there, with 98% probability, the test is positive, which means it's a pretty accurate test, but it's still not perfect. Okay? Conversely, let's suppose that the person does not have cancer, then this test, in 97% of those cases, the test correctly comes out negative. Okay? So again, it's pretty accurate, but it's not perfect. And notice that the probabilities are different in the two cases, right? In general, the probabilities of false positives and false negatives are not going to be the same. Okay? Now, there's one more piece of information that we need to have before we can answer the question, what is the probability that the patient has cancer? Right? This is a very typical application of Bayes' theorem, because what we know is the probability of the test being positive given that the patient has cancer, right? We can compute the probability of the effect given the cause. But really what we want to have is the probability of the cause given the effect. Given that this test was positive, what we really want to know is like, what are the chances that this patient has cancer, right? And this is what Bayes' theory is going to do for us. But for that we need one more very important number, which is the prior probability of cancer in the population, right? A priori, before you even do the test, before you see anything, what are the chances that somebody has cancer? And those mercifully are pretty low. Let's say it's 0.008. Okay. So now let's do this as an exercise. Okay. So what is the probability of cancer? 0.008. Okay. What is the probability of the test coming out negative? Sorry. What is the probability that the patient does not have cancer? 0.992. Correct. What is the probability of the test being positive given that the patient has cancer? 0.98, right? This is the easy part. What is the probability that the test comes out negative given that the patient has cancer? I heard a lot of murmurings, but no clear signal. Be confident. 0.02, right? Because they have to add up to 1, right? These two guys have to add up to 1, right? Just like these two guys have to add up to 1, right? So you guys did this one very quickly, right? Sometimes questions are so easy that you start thinking it might be a trick question in the end, right? So here, fear not, there's no trick question here. Although there is an error that people very often make, and we'll talk about that shortly, right? So what is the probability of minus given cancer? So what is the probability that the test comes out negative given, that you don't have cancer? 0.97, right? And so what is the probability of the test coming out positive given that the patient does not have cancer? Well, that's 0.03, right? Okay, very good. So now, finally, this is just the data, right? This was just, taking what's in the question and doing, knowing that the sum of, each of these two things has to be 1, okay? So now, what is the probability that the patient has cancer given that the test comes out positive? Okay. Let's write Bayes' theorem. Let's start by writing down Bayes' theorem. Okay, so what do I need to write here? Let me do the first step. It's the prior probability of cancer. I'll just represent it as C, right? Times what? Right. Probability of plus given cancer, right? Divided by what? So probability of plus given cancer, right? Divided by what? Probability of plus, right? That's the only thing left to have here, right? Okay, very good. But what is the probability of plus? It's actually something that we haven't seen how to do yet, right? What is the probability that the patient has cancer? The probability that the patient gets a positive test, irrespective of whether they have cancer or not.
Be the probability they got a plus given that they have cancer times the probability that they have cancer plus the probability of plus given that they don't have cancer times the probability we don't have cancer.
Yep. Everybody follow that? I can write almost as fast as you can talk. Does everybody agree? Right? So this is a new point, right? So let's parse this, right? We're going to look at this, a little bit more detail shortly, but this is the sum of two things: the probability of plus and cancer, right? Plus the probability of plus and not cancer, right? So let's look at the second one first, right? This one. Obviously, the probability that you have a positive test is the sum of two probabilities. The probability that you have a positive test and cancer, right? And the probability you have a positive test and not cancer, right? Because, that's all that can happen, right? Anything outside of this, is not a positive test. Okay, so everybody agrees with that part, right? Well, so now, using the definition of conditional probability, right? What is the probability of positive and cancer? Well, it's the probability of cancer times the probability of positive given that you have cancer. Okay? Because this is the type of thing that we do all the time when we're dealing with Bayes' theorem. Okay? And now at this point, so this thing is equal to this, right? And now we've reduced this to the numbers that we already have, right? P of C we know is 0.008, P of plus given C, right? And now notice that the first part of this is just what we just computed, right? So this P of plus given C, P of C appears in both the denominator, in both the numerator and in the denominator, right? And then the other thing is just the same thing, but with not cancer. Okay? So all we have to do at this point is plug in the numbers. Okay? And I encourage you to do that exercise But let me actually do something much more fun than plug and chug, which is, give me a guess. What do you think this, looking at these numbers here, right? What is your sense of how likely this person is to have cancer? Just give me your intuitive feeling, your gut feeling, intuition. And do not be afraid to be wrong, right? Because nobody's going to get this exactly right. Yeah.
Like a few percent.
A few percent, like say 5%?
5, yeah.
5%. Okay, so we have 1 vote for 0.05. Anybody else? So, what is your reasoning behind 0.05?
Well, so the prior probability is so low that intuitively you need a very accurate test to get to that, to be able to diagnose that.
Okay, good. Anybody want to say something else, higher or lower? You will get a free extra 10 points in this class's grade if you answer correctly. Now you're really thinking.
1%.
1%. Okay, anybody want to say more?
So isn't this after the test was positive?
Yes, no, absolutely. This is after the test, yes.
Right.
So exactly, notice, right? The test came out positive, right? And you're going to tell this patient, so what you're suggesting, right? And whoever said 1% is doing that even more so, is this person came in, right? They tested positive for cancer. And you're going to tell them, no, don't worry, it's almost certain that you don't have cancer. Are you sure you want to take on that responsibility? What if they die of cancer because of you? Right? This is the decision that, doctors have to make. Right?
Second test.
No, very good. So, exactly. When in doubt, gather more data, right? Do a second, more accurate test if it's justified, right? This is why in TB, for example, we have both the skin test and an X-ray. The skin test is quick and cheap, but if it turns out negative, then maybe you're good. But if it turns out positive, then now you really want to be sure, and that's when you go for the X-ray. So this is a very common thing to do. Okay, so anybody want to throw out a different number, just for the heck of it?
75%.
Okay, 75%. Okay, very good. This is what I like, right? Okay, 20%. Very good. It's getting better and better, right? So
98%.
98%. You score highest for boldness, which may not be for correctness, but okay. So anybody want to say even less than 0.01?
0.05.
0.05. You mean 0.005?
0.05, yeah, sorry.
Okay, very good. I honestly don't remember what the answer is, right? So I'm a totally unbiased, host of this game, right? But let me tell you where roughly the answer is going to lie, right? Anybody else want to fall one way or another and share the glory of being right, or the shame of being wrong? Except there's no shame in being wrong.
85. 85%.
Okay, 85. So that's somewhere between these two. Okay.
50%?
Very good, right? We were missing that, old faithful, the principle of indifference, right? So that's the spirit, right? But that's the spirit when you don't have data. And in this case, we do have data. So, okay, but the interesting thing here is, you guys are all over the map, right? So what?
Near 50% is.
You believe near 50%? Okay, so we have 2 votes for near 50%, but somebody here is saying no.
No, it's closer to
Right.
1%.
So, okay, so, for example, he's pretty confident that it's pretty close to 1%. Okay, and the answer is, see, we have this, we have this scale here, and as I said, I don't remember the exact value, but I can tell you, and you just have to plug in the numbers and verify that the right answer is 200%. No, just kidding. The right answer is going to be in the low end of the spectrum. Why is the right answer in the low end of the spectrum? Well, first of all, there was a test, and the test did come out positive, right? So this absolutely has to increase the probability that the patient has cancer, right? Otherwise, the test would be useless, right? So the probability that the probability that the patient has cancer goes up a lot, as a result of the test, right? And when you get this number, you can compare with the prior probability and go like, yes, this really increased a lot. But the thing is that it's starting from such a low basis, right? Remember, the prior probability is 0.008, 2 zeros, right? So even if we go with the 0.01, right? This is already an increase, right? I mean, it does increase some, right? It's not going to be 0.008105, right? But here's the thing to remember is that, and this is actually something that people forget all the time. Even trained doctors tend to do this, which is they forget the prior. They just look at the accumulating evidence and say like, oh, now it must be really likely that this person has cancer. And they don't realize that this is the difference between probability and determinism, is that these are just incomplete pieces of evidence. They move the needle, right? But if you're starting from a very low probability, even after moving the needle for a while, you still have a low probability. Okay? So you wind up with a probability that is substantially larger than this, but is much less than 50%. Okay? And again, this is something that happens again and again, is you have something for which the prior probability, also known as the Bayes rate, is very low. And human beings, for some reason, just tend to not take that into account. And then they make all sorts of judgments that are very off for this reason. In fact, there's a couple of psychologists, Tversky and Kahneman, who actually won the Nobel Prize in Economics for having a whole series of studies of how people are, at least apparently rational. And one of the most famous ones is exactly this. You give people a bunch of these judgments, and they get them wrong. So those of you who got this wrong, don't worry, you're in very good company. Most of mankind agrees with you. Okay? On the other hand, it is the case that you can't ignore the Bayes rate. However, just in case the lows are gloating too much at this point, there's a twist to this story, right? Let's say, let's just say for the sake of argument that the probability comes out 0.1. Okay? Does this mean that you can tell this patient to go home happy? Well, it can't be, right? Because if that was the case, then there was no point in doing the test, right? They probably didn't have cancer before the test. That's the prior probability, and they probably still don't have cancer, right? So let's say that the probability went, again, in very, very round numbers from being 0.01 to being 0.1, right? Why is it that 0.1 is something that maybe the patient needs to worry about, whereas 0.01 is not?
It's 10 times more.
Indeed, it's 10 times more, so it's a big increase, right? But actually picture yourself, right? You just went into the doctor's office, right? You had a test, and they said you have a 10% probability of having cancer, right? And now, actually, the good doctors will actually do this for you. They will tell you what the probabilities are, maybe even without the numbers, and they will let you make the decision. And now you have a choice between the following things, right? You are going to go home and not worry about it because, 9/10 probability you don't have cancer. Or, again, this is a very common situation. You are now going to do an invasive procedure. Are they really going to dig into your chest or your leg or whatever and figure out if you have cancer or not? And hopefully, if you have it, they'll remove it. Okay, so which one are you going to do? And let's say this invasive procedure, for the sake of argument, something that, you're going to have to go in one day and, it's going to be unpleasant but not too painful, and then you're going to have some recovery period of a week. So what would you do?
Is the invasive procedure going to be sure?
Yeah, exactly. Good point. Let's assume for the sake of simplicity that with that procedure will get rid of your cancer for sure. So there's no uncertainty there, right? So you know that you have a 10% probability of cancer. Do you want to do it? Do you want to do the surgery or not?
It depends on the person, but 10% is enough to scare someone.
Exactly. So both of those things are very true. It depends very much on the person, which is why it should be the person making the decision. But the other thing to
I think it also depends on the cost of the procedure, whether or not it's covered by your insurance. It might be considered experimental.
Absolutely, right? So if it's going to bankrupt you and then you're going to be alive, but they're poor, you're right. So let's think of precisely. So whether or not you're going to go for the procedure depends on how much it's going to cost in money, how much it's going to cost in pain, how much it's going to cost in time, right? But the reason why you might want to go for it, even with a 10% probability, is that if you have cancer and you don't do the procedure, you die. That's the highest cost you can imagine paying, short of, being tortured all your life or something, right? So this is actually something that we've already alluded to before, but, this is a very, nice case where it shows up, is that what really matters to you is not what is the most likely thing, right? Is what is the outcome that is best for you, given the information that you have. If you really value your life a lot, right, and let's say that the total cost in dollar equivalent of this is $5,000, well, with 10% probability, you waste $5,000, right? Oh, sorry, with 90% probability, you waste $5,000. But with 10% probability, right, you've just saved your life. So if you think your life is worth at least $50,000, you actually want to go with the procedure. And studies show that people tend to value their life at more on the order of millions of dollars. How do people find this out? They ask you questions like, for example, you could get a new job in a different location where you will pay X more, but now you're going to have, a longer commute and an expert increased chance of dying in a car accident. And you can see how much people value their life by, the trade-off between the two. Okay, so the bottom line is, the probability is still low, but it could have put you over the threshold where you decide to go for the procedure. Okay? Hopefully what happens on a good day is that you can do a second better test that is still not too expensive, and then, that one will tell you much more surely what's going to happen. Okay? So these are two very important things to keep in mind when dealing with applications of Bayes' theorem, or really decision-making in general. One is, do not forget the priors because they can make all the difference. But number two is, you don't just care which outcome is more likely. You care which outcome has the highest expected utility for you. That's actually the technical term, is the highest expected utility. The expected utility of dying is, the minimum you could possibly have, right? And the maximum expected utility is living, a long, happy, and healthy life. Okay? Any questions about this? Okay, so hopefully this example kind of, made everything a little more concrete. Let's see a couple more things, right? So something that came up here was that we had, at this point here, right, we actually, we had to figure out how to compute this, P of plus, right? And then we figured out how to do it, but there's actually, a couple of general rules behind that you want to know, right? And those rules, they're very simple, but incredibly useful. They're the product rule and the sum rule. And, you may remember this from Stats 101 or not, in any case, let's go over it. So the product rule is a way to compute the probability that two events happen, A and B. And it's just what we've seen in a number of instances already, is that P of A and B is P of A given B times P of B, or alternatively, it's P of B given A times P of A. Okay? The probability that A and B happens is the probability that A happens, and then B happens, given that you know that A happened. Okay? The second one is the sum rule. The sum rule, so the product rule is the probability of a conjunction of things, A and B. The sum rule is the probability of a disjunction of things. Where's the probability that A or B happens? Okay? So the probability that A or B happens is the probability of A plus the probability of B, right, minus the probability of the intersection. Why did I subtract the probability of the intersection?
It's counted twice.
Because it's counted twice when you add them up. Okay, so doing this with, that old stalwart, the Venn diagram, right? Here's what we have, right? This is A, this is B, right? So P of A, let's say, we have uniform distribution over the plane here. P of A is the area of this ellipse. P of B is the area of this ellipse. When I add the two, this area here got counted twice. Okay? This is A and B, right? So now I have to subtract it once so that I have the right result. Okay? Everybody agree? Okay, very good. So these two rules are two of the most useful things you can know in probability. It's amazing how much basically just falls out of them. One of the things that falls out of them, that's actually what we were sort of like using in a very simple form just now in the cancer example, is the theorem of total probability. Okay? And the theorem of total probability is again best illustrated with a little Venn diagram. And this is the following. Again, let's suppose that the plane here of the tablet is, my event space. And let's say we have a bunch of events that partition the space. Let's call this, A1, A2, A3, A4, A5, A6. Okay? So one of these is guaranteed to happen, and no two of them happen at the same time. Okay? So mutually exclusive and exhaustive outcomes. Okay? And now I have another event that I'm interested in, and that's B. Okay? And again, P of B is the area of this ellipse. Okay? And now what the theorem of total probability does for us is it allows us to compute the probability of B as a function of two things. The probability of each of the A's, so P of A1, P of A2, etc., and the probability of B condition on each one of those. Okay. So the A's partition the set of all outcomes into some distinct things, and now what I want to know is the probability of B as a function of how often each one of those happens, each of the A's, and how often B happens when one of those is true. Okay. And so here's this formal statement of this. So what is P of B? Right? P of B is the sum over all the A's of the probability of A times probability of B given A. Okay? Why is this the case? Right? Well, clearly the total area of B is the sum of these sectors, right? You agree? And what is each one of these sectors, right? This sector here is A1 and B, right? A1 and B. You agree? And this sector here is what? A6 and B, right? So P of B, let me write this here, right? P of B is equal to what? P of A1 and B, right? Plus P of A6 and B. You agree? This is very simple. This is just decomposing this orange into its segments. Okay? Very good. But now I can apply my definition of conditional probability or product rule, right? And what is P of A1 and B? It's P of A1 times P of B given A, right? It's the probability. So okay, let me write that down. So P of A1 and B, right, is equal to P of A1, right, times P of B given A1, right? Everybody agree? And the same thing holds for everybody. So notice, right? At this point, we have our theorem, right? It's just the sum over all the A's of P of A, of P of that A times P of B given that A. Okay? And if we go back to the Venn diagram, why is this the case, right? Well, P of A1 is this whole segment, right? Assuming that the P of the whole space is 1, right? But I'm only interested in this fraction of the segment, right? So P of A1 tells me the size of the big segment, and then and then this is the size of the smallest segment where B holds, and it's the sum of those that I'm interested in. Okay? Everybody follow this? Why is this so useful and important? Because often it's very hard to just flat out compute the probability of something. This is a little bit like the probabilistic analog of reasoning by cases, right? Think about the following, right? What are your chances of getting run over by a car if you cross the street? This is a little hard to figure out, right? But now let me ask you another question, right? What are your chances of getting run over by a car if you cross the street when the light is green for you? Well, that should be low, right? Unless there's some crazy driver out there, right? If the light is green, then you can go, right? And now let me ask you the other question, right? You're at a busy intersection, right? Pick yourself like in the middle of Manhattan with all that traffic rushing through, and people there are not nice like they're here in Seattle. They will not slow down for you, right? So what are the probabilities of getting run over by a car if the light for you is red? Well, that one is pretty high, right? Because they are rushing by. If you're just walking to the intersection with the red light, you might be in trouble, okay? So this is what the A's are here. They're, the light is red, the light is green. And B is the probability that you get run over. The probability that you get run over is totally different depending on whether it's green or whether it's red. Okay? And so what I'm doing here is I'm going to compute the probability. So what is the probability that it's green? What is the probability that it's red? What is the probability that you get run over given that it's green? And what is the probability that you get run over given that it's red? And then the sum of that is the probability that you get run over. Okay? Questions? Okay, very good. So these are just a few useful probability things to know. Let us keep going. So now we've learned this notion of the MAP hypothesis, right? And if you imagine a beautiful world where there's unlimited data and no computational resources, this is all you need. You're done, right? Because you can use the following brute force learner. You have a hypothesis space, like say the space of all decision trees over these particular attributes, or pick your own favorite representation. And all that we have to do is, for each hypothesis, We compute its posterior probability according to Bayes' theorem, right? So there's going to be this data term, and then there's going to be this one that encodes your prior knowledge, right? And then I just pick the one for which this is maximum. Easy street, right? Of course, the slight detail is that there's usually an exponential number of hypotheses, so this is not going to be feasible. But it's very good to keep this in mind as a reference point, right? As we do the things that computational limitations allow us to, in the back of our minds we should always be thinking, well, how close is this to what we would ideally be able to do? And sometimes we can get pretty close, sometimes we can even get right there. In a lot of cases we have to compromise, and we would like to know how much we're compromising. Okay? Mm-hmm.
So if you were to do that, you would need the exponential number of prior probabilities too, right? How would you...
Yes.
How do you-
Yeah, very good. So I have not just assumed that you have infinite data and infinite computing power. I've also assumed that you personally have infinite knowledge and infinite time. But hey, right, we're already in La La Land, so we might as well take it all the way, right? So, to answer non-facetiously, yes, one of the problems that actually happens in these methods is that if there's a lot of prior probabilities to specify, it becomes very hard for you to do it. Both because you don't have the time and the patience, or more often, you really don't have the knowledge. But what you might want to do, right, is you might want to try to reduce that question to a smaller number of questions. Like, for example, I could say, my probability of my decision tree just goes down exponentially with the number of nodes. So you've made one quick statement that covers the whole space, right? Now, the downside of that is that this is a fishy statement, actually. Do you really believe that the simplest decision tree is the most accurate? Probably not, right? The real decision tree is probably of intermediate complexity. So this is something that you see in practice all the time, is that people do make these sort of like crude a priori assumptions, and they're very important because without them, you couldn't learn. On the other hand, if you squint at those hypotheses, often you realize that they are pretty dubious. Okay? This is another of those counterintuitive things about machine learning, is that often you get a lot of mileage out of making false assumptions. In all other areas of enterprise, if you make false assumptions, you're hosed. In machine learning, false assumptions, could actually be fine. Because those false assumptions combined with data, right? The data is, really what gives you the part in the day, get you to an answer. Okay. You have a question?
Yeah. Is it possible that the most probable hypothesis is also overfitting the data? Is there any relation between those?
Great question. So, does anybody want to say something to that? I'm glad you asked that question. I couldn't have planted it myself. In fact, remember, right, this is always a question to ask, right? Whenever you see a new machine learning method, you should always ask, well, what about overfitting, right? Aren't we going to overfit here? Are we going to overfit here?
So the data just includes the training data, yes.
Right, so this term here, right, just depends on the data, right? So clearly, this term is going to want to fit the noise, right? So we're either going to overfit or something is going to save us from overfitting, and what might that be? Well, let's get this guy out because it's the same for all the hypotheses and doesn't matter. So what might it be?
This is a guess, but does it have to do with the fact that you're not incrementally building up the hypothesis as you look at the data? You start with the hypothesis?
So remember, I start with the hypothesis space, right? Just to be concrete, I have 1,000 decision trees and I need to pick which one is more likely.
Right, but with the decision tree learners, it's you start with something really small and then you're building enough as you sort of go through the data one piece at a time.
Absolutely, but let me try to deflect you from that path, right? You're right, this is what we're going to do in reality, but for the moment we're in this beautiful imaginary universe where I can build all the decision trees that I want from all the data right off the bat, right? So what you're saying is actually quite deep in the sense that often the computational limitations that we have and having to do things online and so forth actually help us to fight overfitting. So again, in most other areas, computational limitations can only hurt you. In machine learning, computational limitations can actually help you avoid overfitting. So in a way, your answer is a very good one, but it's not the one that I'm looking for right now, right? The answer that I'm looking for right now, notice, there's only two things here. One is the likelihood and the other one is the prior, right? And what we saw is that the likelihood wants to overfit, okay? So now my question is, if something is going to save you from overfitting, what could it be?
That's prior.
It's the prior, right? Because like Sherlock Holmes said, once you've excluded all the other possibilities, what remains must be the truth, right? So there's only one thing left here that could save us from overfitting, is the prior, right? So my question to you is how might the prior save us from overfitting? Right, overfitting means that I just pick the hypothesis that best fits the data. But overfitting is when that's not the best hypothesis. So how could I return the best hypothesis even though it's not the one that best fits the data? It has to be because I said a priori that I prefer that hypothesis. Right? Let's say that H2, right, is higher in likelihood than H1. Right? But H1 is really the true one. The only way I'm going to return H1 is if its prior exceeds the prior of H2 by more than the likelihood of H2 exceeds H1. Okay? So what this is saying is correct prior knowledge will save you from overfitting. If the prior knowledge is also incorrect, well then you're hosed, right? Both things are pointing in the wrong direction and there's nothing you can do. But prior knowledge can help you avoid overfitting. So if you think about it, what we actually have here is a formal statement of something very important that we already we've seen in a more intuitive way, right? When I say something like, I'm going to put a complexity penalty on my trees, right? The Bayesian way to look at this is to say, you have a prior belief that small decision trees are more accurate. And that's what's going to allow you to override the likelihood and avoid overfitting. So a good prior will save you from overfitting. A bad prior will either not help or even make things worse. So coming up with a good prior is very, very important. There's also this balance between the prior and the likelihood, right? As I get more and more data, at some point the likelihood swamps the prior. Right? It's just the data has more and more votes. Now, it's okay if that happens once you really have enough data to be totally confident that that's the right hypothesis, irrespective of the prior. But if the prior is too weak, the data will swamp the prior too soon and you will overfit. On the other hand, if the prior is too strong, what's going to happen? Right? If you're overconfident in your prior, the opposite is going to happen. You're going to underfit. You're going to be stuck on saying, well, this is the hypothesis, even when your data is already strongly saying that it's not. Okay? So this is a trade-off that needs to be done very carefully. You have a question?
It was related to something you said.
So in principle, right, this prior gives us a very nice place to put our knowledge in, and then we compute the posterior for all the hypotheses, and we pick the best one, and we're done. Okay? But of course, that is not the end of the story. Before we go into that, however, let's see how concretely this relates to things like, I want to learn the concept of spam. I want to learn a set of rules for spam, right? And what happens as I see, more data, right? How does this relate to concepts that we've seen before, like, hypothesis space and version space and whatnot? Okay, so let me give you this in a very simplified form, but I think it will give a very important intuition about what goes on in learning when you have a hypothesis space and then you start seeing data and updating your posterior probabilities as a result. So here's a very simple setting. Let's suppose that my data set D is just the classes of all the examples. So C of X1 is the class of the first example and so on and so forth. Okay? Let's say I'm just classifying emails into spam and non-spam or whatever. Okay? And now let's say that I'm going to make the following very simple assumption, that the probability of the data given the hypothesis is 1, meaning that the probability of that class is 1 if the hypothesis is consistent with the data, right? And otherwise it's 0. Okay? So you see what I'm saying? This is also like the cleanest case that you could possibly have. Okay? So what I just gave you, looking at this from the point of view of Bayes' theorem, I just gave you the probability of the data given the hypothesis, and in either case. Okay? So if the hypothesis, so concretely, if the hypothesis says that this email is spam, right, then the probability that it's spam is 1. And the probability that it's not spam is 0, right? So this is completely categorical. And similarly for the case where the hypothesis says not spam, okay? In that case, it's not spam with certainty, okay? This is sort of like the simplest thing that you can assume. Now, what about my prior, right? Let's also assume the simplest prior that we can assume, which is the indifferent prior. It's a uniform distribution over all the hypotheses, right? So if my hypothesis space is H, then my prior probability is just 1 over the cardinality of H, right? If I have a billion hypotheses in my space and I have a uniform probability distribution over them, The probability of each hypothesis is what? 1 over a billion, right? Okay. So what happens after I've seen some data? Right, so I start out with a billion hypotheses, all of which are equally likely. And each one of them has a tiny probability, right? Because there's a lot of them, and it's uniform distribution. And then notice that because the hypotheses are completely categorical, right? What happens to a hypothesis if for a particular email it predicts it's spam, and the email turns out to not be spam? What do I know about that hypothesis? It has to be wrong, right? That hypothesis that just said that this thing was the opposite of what it was, I have to throw it out, right? So what happens as I see more and more data, right, is that fewer and fewer hypotheses remain, right? A hypothesis will only remain by this part of the scheme, right, if it's consistent with every single class that I have in my examples, right? So as I see more examples, I have fewer and fewer hypotheses left. The remaining distribution among those hypotheses, right, these are other hypotheses that were all consistent with the data, right? So the likelihood makes no distinction among them, right? And according to the prior, they're equally likely, right? So what is my distribution after I've seen all that data? Here's what it is. If the hypothesis is consistent with the data, meaning it makes the right class prediction on each example, then its probability 1 over the size of the version space. Remember the notion of version space that we defined here in the first week? The version space is the set of hypotheses that are consistent with the data. Right? So it's always a subset of the hypothesis space. It's what's left after I throw out all the hypotheses that are inconsistent with any of the data points. Okay? So obviously only those remain, so the probability of each one of those is 1 over the number of those hypotheses, because it's still uniform. Okay? Everybody follow this? Okay, so here's a graphical illustration of what's happening here. This is really, so like what happens when machine learning is at work. In the beginning, so here the x-axis are my hypotheses, right? In general it's going to be a very large space, but I've just put them on one axis for simplicity, right? So all my hypotheses are on the x-axis, the first decision tree, the second, the third, the fourth, or whatever, right? And on the y-axis I have the probability of the hypothesis, okay? So in the beginning what I have is this very shallow, very wide pool of probability, right? There's a lot of hypotheses with very little probability each, right? Meaning you have a lot of inroads, right? This is a very high entropy distribution, you know very little. But then as I see data, right, some of those hypotheses disappear, right? What that means is that the probability mass, remember, the area of this gray rectangle has to be what? 1, right? So, and now I've just shrunk the width of the rectangle, so its height has to what? Go up, right? So what happens is that I now have fewer remaining hypotheses, but they're more likely. Okay? So now my rectangle is becoming more like a square. So where's this going to end? As I see even more data, even fewer hypotheses become possible, and so now I have the opposite. I have a very thin and very tall rectangle. And on a good day, in fact, this ultimately is what's called a delta function, which is non-zero everywhere except at that one right hypothesis. On a bad day, they all become 0, and you know that you've done something wrong, and then what do? Remember, we saw this in the first week, right? What happens if all your hypotheses are inconsistent with the data? You go back to the drawing board, right? You need a larger hypothesis space. Okay? But this is really what's going on, is that the number of hypotheses is shrinking, but each of them is also becoming more likely. Okay? Now let's take a slightly more interesting case, right? And suppose that P of D given H is 1 minus epsilon, if H is consistent with E, and epsilon if it's not. Okay? So actually, maybe the easiest one to understand is the second one, right? The probability isn't 0, it's epsilon. Okay? Which means that your hypothesis, you rolled out some noise, right? Your hypothesis gets an example wrong, but that doesn't mean that the hypothesis is wrong, because there's some probability that the example got flipped by noise, right? Remember the play tennis example, your friend, had been partying last night and hadn't hung over, and didn't want to play tennis because of the headache. It wasn't because it was a bad day for playing tennis, right? So if I throw out every hypothesis that disagrees with even one example, most of the time I'm going to throw a lot of good hypotheses because it doesn't allow for any noise. Okay? So let's say I allow for epsilon noise, meaning some small probability of noise. Okay? So this hypothesis says that it's not spam, but it actually but the label is spam, right? But maybe the label really should have been spam, and this hypothesis is correct. Okay? So now what happens to this picture? And in fact, the new picture is actually what typically you're going to see in practice, because this no noise case is a little bit extreme. In the beginning, you again have this uniform distribution, but then what you get is something more of this shape. This is not exactly a normal distribution because let's say we're in a discrete domain, right? But what's going to happen is that here at the peak, right, I'm going to have the hypotheses that are consistent with all the examples that you've seen. But then you also have these tails here of hypotheses that were inconsistent with a lot of examples. But now remember, no hypothesis is ever completely impossible. They just become less and less likely. Okay? And then what's going to happen is that this bell shape is going to get narrow and narrow, right? It's going to have a very sharp peak here. But if you zoom in over there, there's still some tiny probability that the hypothesis is correct, right? Eventually, if the true hypothesis was in your space, right, you are going to get the delta function here. But with finite data, you don't get there. Okay? Questions? So this is a good picture to keep in mind as we do this what's called Bayesian updating, right? As a new data point comes in, I update my posterior probabilities with the likelihood of that data point. Okay, so what happens is I get more data is that my probabilities become sharper and sharper. They go from being flat to being very, very peaked. Okay, so let us look at a little Stats 101 example of statistical learning network. And this is, what most statisticians actually do for a living, which is regression. Right? And in particular, let's look at linear regression because it's the simplest case. Okay? So what is the statistical learning view of this? Right? You may remember that you learned something like the following. Well, you learned the line that you want is the line of least squares, which is the one that minimizes the sum of the squared errors, right? So let's first of all remind ourselves of what that is, or see it for the first time if you didn't take a stats course, and then let's see how we can arrive at this using our notions of statistical learning. So here's the setting, right? Let's just say I have one input variable x, one cause, let's say, and one output variable y. And my model of what's going to happen is going to be the following. I have a true line f, right? So the solid line here, f, is the true function, right? Y is this function of x. But the data points that I get are corrupted by noise. So to the true function, I added some error e. So I get this point over here, right? Because there's measurement error, or there's whatever, there's sources of error. So even though the point should have been there, I really saw it here. Which means that the points that I get in my data set, they do not form a straight line. Okay? But what I really want to do is I want to recover that straight line from all those noisy data points. So what should I do? Right? And the traditional recipe is find the line that mix, here's my, the dashed line is my hypothesis, and the recipe is return the line that minimizes the sum of the squares of the errors between the points and the line. Right? Which means it's trying to be as close as possible to all the points, and whether they're above or below doesn't matter, right? Because the square is symmetric. Okay? Everybody with me so far? Okay, very good. So here's what I just said in a little bit more detail. My examples are pairs xi di, where di is the noisy training value. This is the data value. And what is di? Di is the true function f of xi, which in this case is a straight line, but it could be anything, plus a noise term ei. Okay? And let us assume, as people usually do when dealing with continuous variables, that the noise is just Gaussian, right? And there are many good reasons to assume that noise is Gaussian, including the central limit theorem that says just about everything becomes Gaussian if you have enough of them and they're independent. Okay? So E is a normal distribution. Okay? Okay, so now let's put our statistical, hat on. What do we want to do here, right? Well, let's make things very simple and again assume a uniform prior, right? So I just want to find the maximum likelihood hypothesis, right? So at this point I actually have everything I need to answer this question, right? I know that my noise is Gaussian. I know my data points. I know that my f is something of the form ax plus b, right? And what I want to do is I want to find the maximum likelihood A and B, right? The maximum likelihood A and B are the A and B that make the data as likely as possible. Right? The maximum likelihood notion is that your hypothesis is likely if it makes what you see likely. If you have a hypothesis that says that what you're observing is unlikely, that hypothesis is not very credible. Okay? So this is the task before us. So how do we do this? Well, as I said, we're going to wind up with this answer. My maximum likelihood hypothesis is the one that minimizes the sum over all the examples, I equals 1 to m, we're assuming there are m examples, of the square of the difference between the data value and the value according to the hypothesis. Okay? So I want my line to be close to all the data points as much as possible. Of course, you can't go through all of them because they don't fall into a line, so this is what I'm going to try to minimize. Okay? Everybody with me so far? Okay, so I just gave you sort of the punchline because you probably already knew the punchline, but the question is, how do we arrive at this, right? In Stats 101, people could just say, well, this is a good heuristic, right? Minimize the sum of squares. What we're going to see here is that this is actually the maximum likelihood hypothesis, right? And why is this the maximum likelihood hypothesis? Well, so let's apply our definition. The maximum likelihood hypothesis is the one that maximizes the probability of the data given the hypothesis, right? And now, remember, I have a bunch of data points, right? Each of these points is a data point, an x, y pair. And I'm going to assume that they're all independent, right? So once you've given me one data point, that doesn't tell me anything about what the next one is going to be like, right? They do not interact. Which means that, and if they're independent, right, this means that the probability of all of them can be expressed as just the product of the probabilities of each one of them. This is a crucial thing that we do all the time in statistical learning. It's a simplification of the world, but it's one that makes things work. A lot of the time it's false, but we won't deal with that case here, right? I'm re-expressing my probability of my entire data set as just being the product of the probabilities of the individual data points. Okay? Everybody with me? Okay, and now I can just replace this by its expression according to the normal distribution, which is this slightly yellow looking thing. There's this normalization constant here. And then it's basically what? It's an exponential of a quadratic function of the difference between the data value and the hypothesis value. Okay? Divided by the square root of the standard deviation, which is the variance. Okay, so if the normal distribution is very wide, then things fall off slowly, right? You have something like this. If the variance is low, then the normal distribution is narrow, and the fall off is something like this. Okay? So this is what we want to do, right? We want to find the hypothesis, meaning the values of the slope and intercept of that line that maximize this. Okay? All right, so how are we going to do that? Well, first of all, here's a very common trick that makes our life much easier, which is maximizing a product is a complicated thing. Right? So let's not do that. Let us take the log of it. Right? Why would we take the log of this thing here?
Becomes the sum.
Exactly. A log of a product is a sum. And a sum is much easier to deal with than a product, right? But now, am I screwing something up by putting in the log or not? I better not be screwing anything up, right? Because otherwise I can't do that, right? So why is it that taking the log here is okay? Remember, I'm just trying to find the hypothesis that maximizes this value, right? And remember, the log function is something that looks... Actually, let me put the axis here, right? The log function is something that looks like this, right? It has the very important property that it's a monad, so this is x, right? And this is log x, right? Log x is a monotonically increasing function of x, right? Meaning that when x goes up, the log also goes up, right? It never goes down, right? So, how is that useful to us here?
Because that way the max will always be.
Yeah, if I find the max of the log, I've also found the max of x, right? Because they go up in lockstep, right? The log goes up less and less, but it can happen that x1 is greater than x2, but its log is smaller, right? So by taking the log, right, this is a very common trick, right? By taking the log, I have made my life easier The values change, but the winner doesn't change, and that's all I care about. Okay? So I take the log, and so now what I have is a sum of logs, right? So we're at this line here now. Okay? Okay, so the first thing that happens is I can get rid of this part. Why is that? It's the same for all the hypotheses, right? This is just the normalizing constant that makes sure the Gaussian integrates to 1. It doesn't affect who the winner is, so that can go away, right? Okay, very good. So we're now at this stage. The next thing that can go away is the variance. Why can that go away?
Assuming it's the same.
Because it's also the same for everybody. By hypothesis, right? I've hypothesized that the variance was the same everywhere. The technical term for this is homoscedastic. I'm sure you really remember this, long after you've left this classroom. In reality, things might be heteroscedastic, which means you could have different variances at different data points, but that's a more complicated case that we're going to ignore. So this guy's the same everywhere, so again, it's a constant, then we can ignore it, right? So now we're at this stage. And now I can replace the argmax of this by the argmin of this. Why is that?
Because you flip the sign.
Yeah, I flip the sign, right? So if I flip the sign, the maximum has now become the minimum, right? I have turned everything around. Okay? So the argmax of this negative thing is the argmin of this positive thing. Everybody agree? Okay, so here is our good old sum of squares. Right? I want the argmin of the sum of the square differences between the data values and the predicted values.
If you get more data, then the variance will change.
What, sorry?
If you get more data to work on.
Yeah, so if I get more there, then there'll just be more terms in this sum. Right? It'll be a harder problem and more computationally expensive, but hopefully I'll get a better, fit at the end of the day. Or I will have a higher confidence in my result. So what have we learned here, right? What we've learned is that if your noise is Gaussian, right, then what you want to do is minimize the sum of squares. So instead of minimizing the sum of squares just being something that falls out of the air, it's actually a consequence of the noise being Gaussian. And it also tells you that, well, yes, if you believe the noise is Gaussian, then this is a good thing to do. If you don't believe the noise is Gaussian, then maybe minimizing the sum of squares is not the right thing to do, and now I can do something else. So this is a very nice small example of how this statistical analysis can, number one, help you understand better what you were doing all along, right? But also help you understand when to do something different, right? Now it's not just like, well, pick whatever you like. It's, well, what is your noise like? If it's Gaussian, then do this. If it's not Gaussian, then what you need is you need the expression for the distribution of that noise, and then you go through the same exercise with that expression. Okay? So this is a very general recipe that will apply across a very wide variety of circumstances. Okay? Questions?
Can we replace squares of differences by just looking at absolutes of difference and summing them up?
You sure can. So nice application of what we've been looking at, right? So what would that mean? Right, so squared errors means the distribution of the noise is Gaussian, right? If instead of squared errors you just use absolute values, which by the way could be an excellent idea, what does that mean about my noise?
Uniform?
No, not uniform. Remember, uniform is the probability is the same and then you get a sudden cutoff, right? And that's not what happens here, is that like with absolute value you have a constantly increasing penalty, right? As your data point and your prediction move away from each other. Right, so remember, a Gaussian distribution is, let's suppose that, the mean is 0, just to keep things simple, right? So here's my x, right? And that x, so this is what a Gaussian distribution looks like, right? If you use, the sum of the absolute values of the differences, what you're actually assuming is what is called an exponential distribution, which is something that looks like this. Because remember, the log of this is a parabola, right? That's how we got the sum of squares. The log of this is just something like this. So this is a linear function exponentiated, and that's an exponential log. And and you can play. You can imagine putting in other things and seeing what the corresponding probabilistic models are.
Laplace.
Yes, this is also called the Laplace distribution. Yeah. More questions? Okay, so why don't, let's see, let's go for a little bit more. Yeah, let's cover a couple more things and then take a break. Okay, so we've learned a lot of interesting stuff so far, but usually the goal in learning a model, whatever it is, or at least one of the important goals, is to make predictions on new instances, right? I am Netflix, and I want to recommend new movies to you. That's the point of having a good model of your tastes, is to make predictions for new things. And so the question that we're now going to ask is, in this framework, how do we make predictions for new things, right? How do I predict, whether a new patient has cancer or not, or whether something is spam or not? And you might be asking, like, why am I asking this question? Don't we already know how to do that? Well, actually, we thought we knew how to do that. But in this Bayesian framework, actually, things get a lot more interesting. And let me illustrate that with an example, right? So my goal now is not to produce the most probable hypothesis, like, what is the most probable decision tree? Is what is the most probable prediction for this day, right? Given that it's sunny and humid and low temperature, should we play tennis, right? So what should I do now, right? Consider the following very simple example. Let's say we have just 3 hypotheses in our space. Hypothesis 1 has a posterior probability of 0.4. Right? Let's say I've already, I had my priors, I had my likelihood, I updated, my priors with the data, with the likelihood coming from the data, and now the posterior probability of my hypothesis is now, 0.4 for each one, 0.3 for each 2, and 0.3 for each 3. Right? So there's 3 hypotheses. Their probability adds up to 1. Okay. And now let's say that I have a new instance x, and the first hypothesis says that this is a positive instance. This is a chair, let's say. And my second hypothesis says, no, it's not. And my third hypothesis says, no, it's not. So, over to you. What would you predict in this case? Positive or negative?
Negative.
Because?
H2 and H3 are more likely to put together.
Exactly. The balance of evidence here is that this instance is negative, right? But notice, this is not what we've been doing so far, right? What we've talked about so far is I find my most likely hypothesis, right? And then I make predictions according to it. I find one decision tree or one whatever, and then I make predictions according to that. And what this is showing is that when you do that, you can go wrong. Because if I had made the prediction according to only the most probable hypothesis, which is H1, I would have predicted plus. But yet, hypothesis 2 and 3 together have a probability of 0.6. Okay? So overall, I have a probability of 0.6 of having a negative instance, and the probability of being positive is only 0.4. Right? So there's something important here that we've been missing. And Bayesian learning alerts us to that. Everybody got this? Okay, so let us generalize from this example. And this leads us to this very important notion of the Bayes optimal classifier. The Bayes optimal classifier is the best that you could ever do, supposing you had no computational limitations. And what is the best that you could ever do? The best that you could ever do is for each hypothesis, you have its prior, you compute its likelihood, right, according to the data, however long that takes, right? For every single hypothesis, you multiply the 2, and then you have the posterior probability of each hypothesis. And then my prediction for a new data point is obtained by summing over all the hypotheses in their exponential or even infinite number. And what do? I take each hypothesis prediction. So what is P of Vj given Hi? Is the probability of the jth value given the ith hypothesis. Let's say now I'm trying to predict, what type of furniture this is. Is it a chair? Is it a table? Is it a cabinet, right? And let's say according to hypothesis 1, right, according to this one thing that I've been doing object recognition with, the probability of chair is 0.3. Okay, so then what I do is 0.3, and for another hypothesis, like let's say it's 0.9, right? And for yet another hypothesis, it's probably not a chair, it's a table, so the probability of chair is 0.1. Okay, so the probability of chair that I want to compute intuitively, right, should be an average of these, right? They should get to vote, right? Whichever one has the most votes at the end of the day should win, right? But what should the weights in that average be? Right? Should they all count equally? Well, obviously not, right? I don't want a hypothesis that's very unlikely according to the data to count as much as one that really agrees with the data well, right? Or a hypothesis that I don't believe in much to have the same weight as one that I do believe in a lot. So the weights need to be the posterior probabilities of the hypothesis. So the optimal prediction is made by voting among all the hypotheses where the weight of each hypothesis is its posterior. The more I believe that hypothesis, the more it should count. And remember, these guys add up to 1, right? So this, it really is a weighting function among the hypotheses and therefore also among their predictions. Okay? And notice that, if you do the math in this example, this will give us the right answer, right? So the first hypothesis, has a probability of 0.4, right? Its probability of minus for that instance is 0. The probability of plus is 1, right? I do the same thing for the others, right? Except that here things are reversed, right? So now the total probability for the hypothesis plus is 0.4, and the total probability for the hypothesis, so the total probability for the prediction plus is 0.4, and the total probability for the prediction minus, right, is what? 1 times 0.3, right? Plus 1 times 0.3, i.e. 0.6, i.e. it wins. Okay? Everybody follow this? So this is the optimal thing that you should do. Are we done? Can we go home happy? Well, actually not, right? Because this is a trivial example where there's only 3 hypotheses. When the number of hypotheses is 2 to the 20, you can't do this. So the Bayes optimal classifier is an interesting theoretical notion, but in almost every case it's a completely impractical thing to do. There are some cases like linear regression where you can actually compute in closed form what that vote is going to be. And if you can do that, then great. But most of the time you can't. Right? So this is like completely infeasible. So the question becomes, what do we do in that case? So we just did this. And this is where this notion of a Gibbs classifier comes in, which we've mentioned briefly last week. The Gibbs classifier, in some sense, is the second best thing that you can do compared to just averaging over all the hypotheses. By the way, this thing here is also called Bayesian model averaging, because I'm averaging over the predictions of all the models. Okay? So given that Bayesian model averaging most of the time is not an option in practice, what can you do? Well, there's lots of things that you can do, but here's a very simple one that is worth remembering, and this is what's called the Gibbs classifier. The Gibbs classifier just consists of doing the following ridiculously simple thing. Choose one hypothesis at random. Just one. Don't sum over the exponential number, just pick one hypothesis at random with probability proportional to its posterior. Right? So the whole trick here is that the hypotheses that are more likely a posteriori should have a higher chance of being picked. Okay? And in particular, if some hypotheses have a 0 probability a posteriori, those never get picked. Okay? But bottom line is all I have to do is pick a single hypothesis according to the posterior, right? And then I classify the new instance according to that hypothesis, right? Now, a priori, right, this sounds like a pretty bad idea, right? That hypothesis, is probably going to be some random piece of crap, right? So this doesn't sound like a very good idea. Surprisingly, though, this is actually a pretty good idea. It's a pretty good idea because you can prove that the error of this hypothesis is at most twice the error of the Bayes optimal hypothesis. So if the Bayes optimal hypothesis has an error of 1%, this will only be 2%. Pretty good. Concerning you just went from an exponential amount of work to, an O of 1 amount of work. If the Bayes rate is by the way, the error of the Bayes optimal hypothesis is often called the Bayes rate, as in BAYES rate. Not to be confused with the base rate, which is the prior probability of something like the base rate of cancer. Unfortunately, in the English language, these two things are very confusable, even though they're totally different. So hopefully from context, you'll know which one we're talking about. Here, we're actually talking about the Bayes rate, which is the error rate of the Bayes optimal hypothesis. If that rate is like 20%, then the Gibbs classifier will have an error of 40%, which is not so great. But nevertheless. Does this remind you of something that you've seen before? Vaguely? we saw some, I'm not surprised that you don't remember it because this was just an off-the-cuff remark that I made before. But remember when we talked about the nearest neighbor algorithm? And we actually showed step by step how you could guarantee that given enough data, the error rate of naive Bayes, naive Bayes we'll see shortly, the error rate of nearest neighbor was what? At most twice the optimal, right? Which is exactly the same thing that we're seeing here, right? You remember that? So, is it a coincidence that these two values are the same? Right? What is your prior probability for the answer to this question being yes? Is it a coincidence? Is it not a coincidence? Well, if it was a coincidence, I wouldn't be asking the question, right? Like, would I say, like, well, of course it's a coincidence. Let's move on, right? It's not a coincidence, right? So what happens is that you can show, I won't do that here, but, I invite you to think about this as an exercise that with infinite data, nearest neighbor becomes the Gibbs classifier, right? So nearest neighbor is not the Bayes classifier, but it is the Gibbs classifier. So this is another way to see that nearest neighbor is actually pretty smart. And also what we have here is at least a practical strategy for coming up with a good hypothesis. Of course, you could do better than that, but at least we have that one, starting point. Okay. Questions about any of this? All right, so this was like the more theoretical part of the class, like the framework, Bayes learning as a framework for learning. What we're going to see in the second half of the class is, the rubber meets the road. We're going to look at the naive Bayes classifier, the second simplest algorithm you'll see here after nearest neighbor. We'll see how to use it for text classification, in particular things like spam classification, and then we will look at Bayesian networks and how to learn them. Okay? So it's 7:55. Let's reconvene at 8:55. Okay, let's get going again. So what we've seen so far has been pretty abstract, right? We were talking about hypothesis spaces, and that could be anything. Could be decision trees, but then there's a lot of them. So let's ask ourselves the following question. What is the simplest application of these Bayesian ideas that you could possibly come up with, right? Just as simple as you can imagine. And this is the famous naive Bayes classifier, and it's what we're going to look at first. And what we're going to see is that despite being incredibly simple, in fact, shockingly simple, it's also shockingly powerful, and we will see why. So, let's assume that I'm trying to learn a function f from x to v. Each instance in x, traditional setting, is described by some set of attributes, say 1a to an. For example, this could be for several words, whether they appear in the document or not, or the symptoms of the patient, or the things that they put in their credit application form or whatever, right? And v is the set of classes that I could assign to this example, okay? So, let us start, turning the crank on our Bayesian machinery and seeing where that gets us, okay? So, I'm given a new document that I want to classify, so I want to say, what topic is this about, for example? So I want to pick the value of the class that is most probable given the words on the page. Okay, let's call that VMAP. Okay? And as we know, VMAP is going to be the argmax of P of V given the attributes. Okay? So to say this in English, I want to pick the topic for the document that is most probable given the words on the page. Or, I'm a doctor and I want to predict the disease for this patient that is most probable given, their symptoms. Okay? So far this is just a definition. Okay? Well, now let us apply Bayes' theorem, right? That's why this is called Bayesian learning, right? So when we apply Bayes' theorem, probability of the class given the attributes becomes probability of the attributes given the class, right? Times the prior probability of the class, right? A priori, how many documents are on this topic, divided by the probability of just seeing those words irrespective of the topic, right? And as before, right away we can get rid of this guy, right? Because it's the same for everybody, right? So now let's look at where we are, right? We started out with having to compute the probability of each class given all values of all attributes, right? Notice that this is never going to be practical, right? Except in really toy problems, right? What I want here, for example, for a text classifier is like, given every single possible combination of words that I could have on the page, right? Tell me what the class of that is. This is, completely unrealistic, right? It doesn't matter how much data I have. I will never have seen all the possible documents that everybody would ever write up to say 1,000 words. Okay, so this here is not feasible, right? Let's look at what we have now in this case, right? So now we have two pieces. Is this one feasible to estimate from there? The prior probability of each class V? Let's say the prior probability of the topic being sports versus politics or whatever. Given that I have, a training corpus of labeled documents, this one is about sports, this one is about politics. Is this one an easy or a hard thing to compute? This is a really easy thing to compute, right? I have 10,000 documents, 1,000 are about sports. Well, the probability is 0.1. Okay. What about this one? Is it easy or hard? So let us state this probability in English. This is, for example, given that my page is about sports, what is the probability of seeing every possible combination of words on that page? Is this hard or easy? It is actually just as hard as before, right? I have something that is exponential in the number of attributes, right? In order to, what both of these cases mean is that in order to classify an example correctly, I have to have seen it before. And in fact, I have to have seen it many times so that I can correctly compute all the probabilities. Right? This is exactly what machine learning is not about, right? Machine learning is about generalizing to the examples that you haven't seen. And you can't do that in this case. You still can't do that here. So, what was the point of applying Bayes' theorem here? We seem to have done this little mathematical manipulation for nothing, right? Well, you're right. So far, this has been for nothing. But this is where the famous naive Bayes assumption comes in. The naive Bayes assumption is, again, a good example of what we do in machine learning when we're stuck. Is we just make stuff up, right? What you learn in this class is the opposite of everything your mom taught you. Procrastinate, make stuff up, right? You could see this as vindication, or you could see it as very dangerous. But so let's make something up, right? What is the simplest thing that we could make up? Well, it's a pretty naive thing, and that's why this is called naive Bayes. And this is, we're just going to assume that all the attributes are independent given the class. Right, so the joint probability of all my A's given V is just the product over all the A's of P of A given V. For example, in medical diagnosis, this is actually not such a bad assumption because what it says is that the outcomes of all my tests are independent given whether or not you have cancer. And the reason this is not a bad assumption in that very particular case is that it's not a bad assumption by design. Because doctors do not waste, your time and money on redundant tests, right? If the first test already told me something, there's no need to take a second test to tell me the same thing. I want a second test that's a very different piece of evidence. Like I said, the first one was your temperature, and the second one was your blood pressure, right? So often in medical domains, this independence assumption approximately holds by design. But in most domains, this assumption is completely false. Like, for example, in text, do you think this assumption is true or plausible or very implausible, right? So in text, what this assumption means is the following is, this is how the documents that you've seen were generated. First, the writer picked a topic for the document. Let's say the writer said, this is going to be about politics, okay? Well, so far so good, right? There's some prior probability, right? But then what this hypothesis is saying is that this is how a document in English gets generated. The writer just flips coins to decide what each word in the document is going to be. They're biased coins, so, in articles about politics, words like White House and president and whatnot might appear more often. But, the document is just formed by flipping, coins or whatever you want to, random process you want to use, and assembling a document that way. This doesn't sound like what real human writers do, I think. Right? You know that these days there are these things out there that generate documents, based on, keywords that are likely to lead to click-throughs. I don't know if you've seen this, but, This might be a more realistic model than we might think. But nevertheless, as a model how things get generated in English language, it's completely implausible. Nevertheless, we're going to make this assumption that everything is independent given the class. Notice that this is the simplest assumption, or in some sense the strongest assumption, that can get you something useful. Because if I just assume that all the attributes were independent of each other and of the class, right? That everything was independent, sure, that's even simpler than this, but then you don't have a classifier, right? Because the attributes don't tell you anything about the class. E.g., the symptoms don't tell you anything about the disease, or the words on the page don't tell you anything about the topic. The simplest thing you can assume is that the attributes each depend on only one thing, which happens to be the thing that you're interested in, and that's the class. Okay? So we make that assumption, right? And now we get the naive Bayes classifier. The naive Bayes classifier just says, I should pick the hypothesis that maximizes the following product. The product of the prior probability, I should pick the class that maximizes the following. The product of the prior probability of the class and the product over all the attributes, or the product of the attribute given the class. So what I'm going to ask when deciding over, sports versus politics is, first of all, are there usually more stories about politics or more stories about sports, right? In this particular source, news source, let's say. But then the other one is for each word. Is it more likely in documents about politics, or is it more likely in documents about sports? Right? Let's say the word baseball, right, probably appears more in pages about sports, and the word, Obama appears more in pages about politics, right? And so what I do is I do this for every single, word, right? And I do the product of that over all the words, multiply by the prior of the class, and I pick the one that maximizes that. Okay? This is the naive Bayes classifier. You can see why it's called naive. The thing that's shocking is that despite being naive, for example, for things like text classification, naive Bayes works a lot better than, say, decision tree induction, which seems, a much smarter thing to do. Okay? So in a little bit, we will see why that might be the case. But for the moment, let's just make things concrete and see what the actual algorithm is. Any questions about things up to this point? Okay, so what we have here is essentially a very simple formula, right? And all we have to do is implement the formula, right? Isn't it amazing what hard projects we give you? There's going to be a few more interesting things, It's not just implementing the formula, but so let's see what some of those things are, right? So, here's our naive Bayes learner. It's given a set of examples, right, as training data. And now what I have to do is the following. For each target value, for each possible class, I estimate, this is where my p hat comes, I estimate the probability of that class. It's just a fraction of examples that belong to that class. And then for each attribute value of each attribute, I estimate its probability condition on the class. So here again is my hat. Okay? This is basically counting the fraction, right? For example, what is the probability of baseball given sports? It's, out of all the pages that are about sports, the fraction of them that have the word baseball in there. Okay? So straightforward thing. And then to classify a new instance, I just do a product of all those things. Okay? Maybe this was belaboring the obvious, but anyway, this is sort of like the algorithm that you have to implement. Okay? Now, implementing this for text is going to involve a few additional subtleties, but we'll get to them in a second. Okay, any questions so far? Okay, very simple, right? Joyfully simple.
So with the product,
Mm-hmm.
the product, the chances is that if any word does not occur, it might bring down the whole equation to 0.
Sorry, can you say that again? I didn't catch it.
With the product, if a word does not occur, then it brings down
Yeah.
to 0.
This is one of the problems, so thanks for pointing it out. We're going to see in a little bit what we might do about that. In fact, first we'll see how bad that could be, right? So here's a very simple example of this at work. Before we go on to these issues, let's go back to our good old friend, the problem of deciding whether to play tennis or not. And let's say that the outlook is sunny, the temperature is cool, the humidity is high, the wind is strong, right? And now I want to compute this. Okay? So how do I do that? Well, I had my table of examples, right, of different days on which it was sunny or not, and humid or not, and we played tennis and didn't. From those tables, I compute the fraction of days on which, yes, your friend wanted to play tennis, the fraction of times on which, no, they didn't want to play tennis, the fraction of tennis days that were sunny, right? We played tennis on 20 of those days. 5 of them were sunny. So P of sunny given tennis then becomes 25%, okay? and so on for everything else. And then all that we do at classification time is do the product of all these things. So let's say it comes out as 0.05 for yes, and 0.021 for no. And then, should you play tennis or no? Should you call up your friend and get rejected, or will you call up your friend and be accepted? So the probability of yes is 0.05, and the probability of no, these are both after seeing the data, so these are posterior probabilities. It's 0.05 for yes and 0.021 for no. Sorry, 0.005 for yes and 0.021 for no. Right? Yes or no? No. Very good. Is something puzzling you here? Nothing is puzzling you? Okay, let's move on. What might be puzzling you here?
What's the third outcome?
There's something a little puzzling here, which is like, these guys don't add up to 1. I must have messed up big time somewhere. Where did I mess up big time? Actually, I didn't, but where's the problem here? Why do they not add up to 1? Is this a bug, or is it real? And if it's real, why is it not a problem, or is it?
Not dividing by the probability of the data.
Exactly, I didn't normalize, right? We decided to not normalize because normalization doesn't bias anything. We still pick the same winner, but of course, since we don't normalize, the probabilities don't add up to 1. So do not be disturbed by that. Okay? The appropriate reaction to this is to at first be slightly disturbed, but then not, right? If you were not disturbed at all, then maybe you were not paying close attention. But if you were permanently disturbed, then you didn't, actually see the deeper point here. Right? Well, deeper. It's not even deep, but anyway. Okay, so 2 points here. The first point is, what is going on here? How can Naive Bayes be so good at things like text classification and many other things, right? Medical diagnosis, actually, it's pretty good for, right? Naive Bayes is very good for medical diagnosis. But there we kind of have an explanation as to why. But domains like text classification, they completely violate the assumption of Naive Bayes, right? This just threw grammar out the window. It threw meaning out the window, right? It says that instead of composing sentences, I just, throw random words on the page, right? Why is it that this can do so well, right? Before we think about the technical justification, right, just think about this problem from the point of view of intuition, right? I have a text classifier that classifies things into topics, right, just by how frequently different words appear, right? How can that do well? Any thoughts? First of all, does it seem very incredible that it does well, or does it seem, maybe not so implausible? It is a fact that it does very well. Until support vector machines came along, Naive Bayes was the state of the art for text classification. And people were very shocked at the time because Naive Bayes was this, simple little thing that nobody thought was worth anything, and then, it basically, kicked the butt of decision trees and backpropagation and all these fancy things that people had. So how can that be?
Maybe it's one of the reasons could be that there's enough differences between the different classes such that the small so you're assuming that they're independent and counting some things double instead of counting for that. Maybe those are not really major.
Right. So here's what happens, right? This independence assumption does not hold, right? It's definitely violated. So it means you need to do things like double count things and whatnot, right? But here's the key question that you have to ask ourselves is, if all that I use from my, here's another way to look at this, right, is that the only thing that I'm using from my data, right, apart from the class priors, are how often each word occurs with each topic. And the question that you really need to ask yourselves is not, is this independence assumption true, is there enough information in those statistics to allow me to distinguish the topics of different, the topics of different pages? And the answer to that is, by and large, yes, because different topics use different words, right? Some words are very common, right, like the and they appear, but usually we take those out, right? We basically filter them out. Once we reduce things using, for example, a feature selection algorithm like a filter method by information, again, this is very common in this domain, right? Like we saw last week, we retain only, say, the 1,000 or 10,000 most informative words, right? Well, those tend to differ by topic, right? Because different topics talk about different things, basically. So yes, we are ignoring grammar, we are ignoring what the person was trying to say, or the fine art of the journalist and whatnot, but it doesn't matter, because as far as figuring out what the topic of the page is, you have enough information in just how often each word occurs in each topic.
Could you say that the model is of the word frequency? It's not about whether, as long as the frequencies are different, doesn't matter if they have different.
Yeah, so exactly. So what's really going on here is that what we have is not a good probabilistic model of how these pages get generated. It's just a classifier. As a probabilistic model, it's bad. But as a classifier, it can actually be pretty good. And again, this is an example of something that happens very often in machine learning. In machine learning, very often, we don't have the means to build a very accurate model of what's going on. It's too hard. We don't have enough knowledge. We don't have enough data. The saving grace is that it doesn't have to be a very accurate model. It just has to be a model where the right class wins most of the time. That's the key thing, is that these things could all be way off as long as the true winner is also the winner in the simplified model. Because then we'll pick that one, and who cares if we picked it in a very, oversimplified way. We just care about picking the right one. Okay? So this is what happens, right? Is that all that we require is that the argmax using p hats, right? See, on this left side I have p hats, be the same as the argmax without hats, right? Notice this guy and this guy could be very different. As long as the argmax is the same in both cases, right? We're good, right? It could be that the true probabilities are like this, and the naive-Bayes probabilities are like this. They're way off, but I'm still making the right prediction. If they were like this, then I would be making the wrong prediction. But the saving grace is that a lot of the time we are exactly in this regime. And then naive-Bayes gives me the right decision. Okay. So this is how naive-Bayes can be so good despite being so apparently naive. Apparently when the folks at MSR first went to Bill Gates with the first spam filter, which was naive-Bayes, this was a student's summer internship project. Bill Gates came down on them because of this. He was like, well, how come? This doesn't seem for real, right? These models are extremely unrealistic. Very good question. But the more subtle point is that even though the models are unrealistic, they can actually be all you need for classification. And if you think about it, if that's all you need for classification, then you're just wasting resources doing something more complicated. Okay? Now, having said that, the flip side of this is that, sure, naive-Bayes can pick the right winner a lot of the time, but the probability estimates are not trustworthy. So you can believe the decision that comes out of naive-Bayes, but you should be very, very careful about believing the probabilities. So, in particular, naive-Bayes could say something like, oh, the probability that this stock is going to go up is 0.95. When in fact it's only 0.51. Right? Well, 0.51 is greater than 0.49, so this is the right call, right? But 0.51 and 0.95 are totally different things, right? And so this is actually typically what happens with naive-Bayes, is that it's a very manically pressive classifier. Naive-Bayes does not know moderation. It tends to either say that the probability is very close to 1 or very close to 0. Why might that be the case? Why is that the way in which naive-Bayes is typically going to be inaccurate? Why would it tend to give probabilities that are more extreme than the real ones?
Because of all the overlap?
Exactly. Naive-Bayes has all these pieces of information that are actually dependent, and it's treating them as independent. Right? When the second attribute comes along, naive-Bayes thinks that this is a completely independent source of information. Whereas in fact, it's largely just repeating the information that you saw in the first attribute. So once naive-Bayes has seen 1,000 of these, it's way overconfident, right? These thousands, have all sorts of redundancy among them, as in real text, but naive-Bayes doesn't know about them. So the moral of the story is, yes, naive-Bayes is a very good classifier to try. In fact, as a rule of thumb, the first two things I would try on any problem are naive-Bayes and nearest neighbor, because they're so easy, they're so simple. And a lot of the time they work. And even if they're not the greatest, they will give you a good baseline and a good starting point. But be very wary of believing the probability estimates that come out of naive-Bayes. There's actually things that you can do to try and recalibrate the probabilities, like shrink them back towards 0.5 and whatnot. So there's things like that you can do, right? But certainly the probabilities that come out of the raw naive-Bayes classifier are something to be treated with a lot of suspicion. Okay? All right, so on to the second point, which is what somebody already very perceptively brought up, which is, well, this all sounds very good in theory, but in practice, there's probably going to be a very big problem in that I could have, let's suppose that I have a value, right, an attribute value that never occurred with some class in the training data, right? You know, this could very easily happen, right? I could have many attributes, many values, some of them could be very rare, my data set is not very large, so it never occurred, right? In which case, what's going to happen is that my estimated P of that A given that V is 0, right? Well, the probability of this word given that, you know, this page is whatever is 0, right? So that can happen. Is that going to be a problem for us or no? I mean, you know, let's say I'm building a text classifier, I have 1,000 attributes, right? And one of them has never occurred with a class and the probability is 0. Is this a problem or is it something we can ignore? Give me your gut feeling, right? Again, there's no penalty for being wrong. Do you feel lucky today? It's a problem. Why is it a problem?
If you have a relatively limited number of training examples, and it happens that none of them has A1, then you can never train anything as anything.
Well, let me push back on that, right? Because what's going to happen is that that attribute is useless, right? But you still have all the other attributes that hopefully predict the class well. Mm-hmm.
So when you're trying to see like the probability of an example, you just multiply the probabilities of the individual attributes together, right?
Mm-hmm.
And so, but then when you have a 0, it doesn't matter what the other ones were, it just pulls everything down to 0, which is kind of distortionary. That's the fun thing about 0.
Yeah, this is the problem, right? And boy, it's a big problem. One little 0 out of those 1,000 attributes wipes out the information from all the others. Because remember, your posterior probability is going to be the product of all of them times the class prior, right? But as long as one of them is 0, it doesn't matter what the other ones are. So that one, you know, darn little attribute wipes out the information from all the others, right? So this is going to be a major problem. Except we can solve it very easily. How can we solve this problem? Remember, we saw a way of dealing with this problem when we were talking about rule induction. What was the way?
Assume a probability.
You what, sorry?
Assume a value, and based on what you see, you change.
Yeah, exactly. I'm going to pretend that ahead of time I saw each value once with each class. Right? I'm just going to hallucinate those examples. And then I'm good, then I never have 0. Right? Remember our whole notion of Laplace estimates and M estimates? Well, this is another great place where we're going to use them. In fact, this whole vast, you know, space of algorithms that use machine learning algorithms that compute probabilities and estimate probabilities from data, this keeps applying, right? The richer the model you want to build, the more likely some of those probabilities estimated from data will be 0, the more useful something like the M estimate will be. Okay? So just as a quick reminder, what is the M estimate is that I'm going to estimate my probability of AI given Vj as the following, right? So first of all, the maximum likelihood estimate would just be the number of examples that had both the value of the attribute and the value of the class, right? Sorry, that value for the attribute and that value for the class, right? NC, over the number of examples that had that class. So for example, my probability of baseball given sports is the number of pages that have baseball and sports over the number of pages that have sports, okay? This would be my maximum likelihood estimate. But we don't have to do a maximum likelihood estimate. We can do a Laplace estimate, which in fact is a Bayesian estimate because it involves using a prior, right? And without going through the details of how you can derive that, because you can and you can do that as an exercise, what can you do? Well, let's say that P, right, is your prior estimate for this probability, right? So, and it could be a very uniform thing, it's just 1 over the number of values, okay? And then you multiply that by M, right? Add to the numerator, and in the denominator, you just have n plus m. Right? So this is very easy to do, right? This is equivalent to hallucinating m examples, right? Out of which mp have the corresponding value ai. Okay? Any questions? Again, this is a very simple thing to do, but if you don't do this in your naive-Bayes classifier, it's going to give you crap. If you do this in your naive-Bayes classifier, at least for things like spam filtering, right? In domains where you have a lot of data, then maybe, you know, the 0 will not happen, but you're always going to be in danger then. Okay? Questions? Here's one more very important detail before you go implementing naive Bayes. Don't do this. This is death. What you need to do is the log of this. You know why? This is another thing to always remember when you're computing probabilities. Yeah?
Oh, floating point precision?
Yeah, exactly. Are you picturing this like, I'm multiplying here, let's say, 1,000 probabilities that are all numbers smaller than 1, right? Sometimes a lot smaller, right? Let's say each one of these is like, 0.1, right? I just have something here on the order of 0.1 raised to 1,000. This is the mother of all underflows. And there was no need, right? Because you just want to pick the maximum, right? So take the log and do sums. So golden rule, never multiply probabilities. Do sums of logs of probabilities and then life will be good and well behaved. This is a very easy thing to forget, but when you forget it, errors happen. In fact, I personally, in my life, have been seriously embarrassed by this. I published a paper, a long time ago on, why naive Bayes works so well, right? Because at the time, people were very puzzled by this. And one of the things that I had in that paper was an empirical comparison of naive Bayes with other things, like, say, decision tree learning. And naive Bayes was basically, beating the decision trees or doing better on almost all the domains, except for one, where it was losing by a lot, right? And in the paper, I left that there. Well, sometimes that's going to happen. But then somebody, Ronnie Kohavi, who's actually a well-known data mining guy, he was also, this when we were both graduate students, he sent me an email saying, like, I've tried to reproduce our results, and this one did a point here. I'm getting something completely different. This was a sonar classification data. It was sonar pings, and the attributes were, the volume, the intensity, and different frequencies of the sonar, and the goal was to distinguish rocks from mines, right? A very useful thing to do if, say, you're the Navy, right? And, my naive Bayes was working way worse than his, right? And this is a published paper in a journal that's, highly cited, right? And it's still wrong. You can go there and see that bogus data point. Well, guess why that was happening? I didn't do this. I got carried away with making naive Bayes very fast. I don't know why, because it was fast already, right? And I was doing these products. And the distinguishing feature of this domain is that it was the one with the most features. Back then, 60 attributes was a lot. Most of the others had 10 or 20. This one had 60, and it was the one domain where things had underflowed. And, the accuracy should have been something like 85%, and I was getting 25%. The base rate, and, I should have paid more attention, right? Because the base rate for that domain was 75%. Right? I mean, like 75% of these things were rocks and 25% were mines. In fact, it was bad luck on my part, because what happened was that it was essentially just choosing a random class. And by bad luck, the class of the first example was what had become the first class, and that one, happened to be, a mine. Right? Because if it had been the other way around, this would have looked like 75%, and it wouldn't have looked this scandalous. So anyway, the moral of the story is take logs of probabilities and add them. Okay. All right. So in your project, what you're going to do is build a spam classifier. Right? And a spam filter is basically a text classifier just applied to the decision of whether or not something is spam. But you can apply text classifiers for a lot of things. One of the things that you can use them for is to automatically categorize news stories by topic, right? Or automatically categorize web pages by topic. And in some ways, the topic classification problem is more interesting because it's more challenging, right? I have a lot of classes. So what I would like to do now is look at specifically how we build a naive Bayes classifier for text, because there's a few more things in addition to just the generic naive Bayes classifier, and then see what happens when we do apply it to text. Okay? So, let's say that, for the algorithm that I'm going to describe here, for simplicity, for the moment, let's just assume we have only two classes, right? And the extension of this for, any number of classes is straightforward, right? So let's just say we're trying to decide whether the document is interesting or not. So positive means interesting, negative means not interesting, okay? The first decision is, how do we represent our documents, right? And notice that, these days, the answer is obvious, but it's not clear, back when people started doing this, how I take text and I map it to a classification problem, right? In classification, what I have is a vector of attributes, and in text, what I have is, language, right? And what people did was sort of like the simplest thing that you could do was just think of the text as a bag of words, which sounded like it was going to be very dumb, but actually turned out to work pretty well, okay? So I'm just going to do that here, right? And let's assume that what we have is one attribute per word position in the document, okay? So if the document is 1,000 words long, I have 1,000 attributes, okay? And the attribute in each position is the word in that position, okay? So if I have, let's say 10,000 words in the language, in general I have more, but let's say I've restricted this to the, 10,000 most interesting ones, I have attributes with 10,000 possible values, right? So this is a lot of values, right? And then my learning, right, is going to consist of using my training corpus of documents to estimate P of plus, P of minus, and then the probability of each document, given that it's positive, meaning interesting, or that it's negative, okay? So far so good, very straightforward. So now let's make our naive-based assumption, right? This is the first thing that we're going to do to make this problem tractable is, I'm going to assume that my probability of the document given the class is just the product over all the positions in the document, right? So I just have to run through the document of the probability of the word that I'm going to see in the test data or that I see in the training data at that position, right? What is the probability that the first word in the document is the? Probably pretty high, right? What's the probability that the first word is a verb? Well, probably not, because usually documents don't start with verbs and so forth, okay? But now we need to make one more assumption, which again is a brutal oversimplification, but for the same reason is not going to hurt us that much, which is I'm going to assume that the probability is not going to vary with my position in the text. In real text, of course, as in the example that I just gave you, the probability varies with position. Like, for example, the is quite likely to be a first word and the verb isn't. But we're going to, ignore that and assume that the probability stays the same throughout. Okay, so this greatly simplifies our problem, right? Because now, instead of having to estimate 1,000 things, I just have to estimate one for each word. And again, this is basically, treating your documents as instead of having sequential structure, just being a random jumble of words, right? Very unrealistic, but it's not going to hurt us. And so with those two assumptions now, we have a complete algorithm, and this is what we're going to ask that you guys implement for spam filtering. So let's say these are my examples, right? My examples are a set of training documents. Let's say spam and non-spam. And V is the set of classes that I want to predict, in this case spam or not spam, or interesting or not interesting. Or if you have 20 topics, then the 20 topics are the classes. The first thing that you do is you take all your documents and you collect all the words and tokens that appear in them. By the way, when I say tokens, it's because non-word tokens are often very informative. Depending on the domain, but for example, a traditional example in spam filtering is if you have many exclamation points in a row, right? If one of your tokens is 3 exclamation points, this is a really good sign of spam. Because most people don't send emails with 3 exclamation marks, but in spam, if you have free in capitals followed by 3 exclamation marks, there's a good chance this is spam. This also caused some people that had a tendency to send, messages with a lot of exclamation marks and capitalized words to get their messages classified as spam. But these days things are more sophisticated than that. So tokens can be informative, not just words. So then my vocabulary, right, is just all the distinct words and tokens in my examples. And now the first thing that I have to do is compute all my class prior probabilities and all my conditional probabilities of the words given the classes. Okay? So for each target value, for each possible class, I do the following. I first collect all the examples of that topic, say all the pages that are about sports. Okay? And then my prior probability of the class is very simple. It's just the size of that set over the size of the entire corpus, right? If I have 10,000 pages and 1,000 are about sports, the probability is 0.1. Okay? And then the next thing is to deal with the attributes. So we concatenate all the members of, say, the class sports, right? I'm not going to care which document they came from because this is all just going to boil down to counting, right? So I count the total number of words in the documents of that class, right? And remember, duplicate words count duplicate times because I care whether a word occurred, once or twice or 50 times, right? That's going to make a big difference to my probabilities, okay? And then for each word in the vocabulary, right? If nk is the number of times that word occurs in the documents, in the total concatenated text of that of that topic, then my estimate of the probability is just going to be nk plus 1 over nk plus the size of the vocabulary. Okay? So this is just my simplest possible Laplace estimate. Right? If I haven't seen any data, then it's just 1 over the size of the vocabulary, which seems reasonable. Right? I'm just uniformly generating words. Right? That's the principle of indifference. Okay? But if I've seen a lot of words, then this just becomes my maximum likelihood estimate. It's the fraction of the words that are, that are that word. Okay? Notice this thing of concatenating all the documents. What I'm trying to say here is that I'm not going to care which document things came from. I'm just going to treat it all as one big document. Okay? And notice that this is not the only way to build a classifier for text or a spam classifier, but it's the easiest one. If you want to do variations from this, you're more than welcome to try them, but this is at least one way that you can do things that works reasonably well. Okay? Questions? Okay, so here's our classifier finally, right? Then you do the usual prediction. No need to repeat that. Here's a concrete example just to persuade you that this stuff really works. Let's just take 20 newsgroups from Usenet and 1,000 training documents from each one. So this is not a big data problem. This is a small data problem. And here they are, right? Comp.graphics and so on and so forth, right? We apply this exact algorithm that I just described. This is the reason I'm using this dataset is actually publicly available, right? This is a dataset that you can actually play with. You can download it from the web and you can use it, right? And it's small, so it's easy to play with. The accuracy of naive Bayes on this dataset is 89%. Notice that I have 20 newsgroups with equal frequency, so the base rate is 5%, right? If I just randomly guess the class of each, the topic of each posting, based only on the frequency of the class, I will only be right 5% of the time. Okay? Or if I pick the most frequent one, in which case they're all equally frequent, so it can be any one of them. But the default accuracy here is just 5%, right? This is where having many topics is a more challenging, interesting example than just having two things, right? So the base prediction here is just 5% accurate. Naive Bayes gets you all the way from 5% to 89%. Now later we're going to look at things like support vector machines, which are the state of the art. And let's say on this data set, I don't remember exactly how well support vector machines do, but let's say they get you to 95%. Right? It's very hard to get to 100% because at the end of the day those assumptions are false and the structure does matter. Right? But the key thing to remember here is the following: is that naive Bayes, for all its simplicity, gets you from 5% to almost 90%. And then all the very fancy, latest, greatest optimization machine learning techniques give you another 5%. Okay? And this is not uncommon. Maybe they give you another 10%. Right? Depends on the problem. But the bottom line is, a simple algorithm, carefully applied, can give you most of the gains that you're going to get. Okay? So it's very much worth knowing about. So here's a little example of such a story. Here's a graph, right? And again, this is from real experiments, comparing naive Bayes with using TF-IDF, right? People in information retrieval, have spent many years developing, these kinds of measures and techniques for these problems, and TF-IDF has been, the winner, okay? And the thing is that naive Bayes, out of the box, is already beating TF-IDF, or essentially doing as well as TF-IDF. If you with less data, TF-IDF is slightly better. With more data, naive Bayes actually starts to dominate. And then here's actually it's a combination of naive Bayes and TF-IDF. But the bottom line is, think of all those years that people in NIR spent, working on things like TF-IDF, naive Bayes. You run it on some data, and it's as good as that. If you think this example is a little bit shocking, you should look at medical diagnosis. Doctors spend all these years in college learning how to do diagnosis, and then I give you a database of patient records and whether or not they had diabetes or not. You run naive Bayes on that and it beats the doctor. People also in the early days of AI, right, one of the things that they did was build these medical expert systems that had lots of rules. If this and this, but not that, then they have diabetes. This basically beats that out of the box most of the time. This is a really good illustration of the power of data. A really simple algorithm like naive Bayes. You give it, a reasonable amount of data. It doesn't even have to be a lot, right? There's lots of these medical data sets available on the web. They typically have, say, 1,000 or even less examples. Naive Bayes with that number of examples is enough to do better than doctors. People have done some studies where they compare naive Bayes and Bayesian networks, which we're going to see in a little bit, and they tend to do better than people, despite the fact that doctors have all those years of training. So this is a good illustration of the power of machine learning. Okay? Don't tell this to your doctor because they might get demoralized or they might get furious. But this is the case. Doctors, of course, have a big advantage in that they have access to information that naive Bayes doesn't. Right? They can see how you're looking that day, and they maybe know more information about you than just the tests. The big problem with people, though, is that they are very inconsistent. If the doctor's in a good mood, right, they might be more likely to give you, one diagnosis than if they're in a bad mood. In fact, there was like this study that, I don't know if you guys saw in the press, I think this was done in Israel or somewhere, that if, after lunch, if you are on trial for something, right, you want the judge to make the pronouncement after lunch, because then they're in a good mood. And they're much more likely to acquit you or give you a lenient sentence than when they're hungry and grumpy. Also, the end of the day is bad, right? They just want to, they want to be done, and they're in a bad mood, and right? So, naive Bayes doesn't have that problem, right? Naive Bayes doesn't get hungry and it doesn't get in a bad mood. So, anyway, any questions about naive Bayes? So, very simple little algorithm, shockingly useful. People started out using it in machine learning as a straw man for fancier things, and then somehow it kept winning. And now we kind of understand why it keeps winning. Nevertheless, it is still the case that the naive Bayes assumption is very naive, right? Really assuming that everything is completely independent given the class. It's pretty radical, right? So the question is, what else can we do, right? We don't want to make that radical assumption. On the other hand, we know that we can't just let everything depend on everything, because then we just don't have enough data to compute the statistics, and we don't have time, even if we have the data. Okay. So what can we do? And this is where Bayesian networks come in. Okay. So the idea in naive Bayes, the idea in Bayesian networks is that we're going to allow some dependencies, but only in limited amounts. Okay. We're going to try to put dependencies where they really matter, where they're strong, where they make a difference, and leave them out elsewhere. And that way we'll do something that's better than naive Bayes, but still tractable. Right? So this is the game in Bayesian networks. And, things are going to be somewhat more complex, but many of the ideas transfer over to the more general case. So Bayesian networks are all based on exploring the idea of conditional independence. So let us start by defining conditional independence. We say that the variable x is conditionally independent of the variable y, given variable z, if once I know z, telling me y doesn't tell me anything more about x. All the information that y had about x is contained in z, right? And the technical statement of this is that for all values of x, y, and z, the following has to hold. The probability of x's value given the value of y and z is the same as the probability of x given only z. Okay? So this is the technical statement, and what this means is that if x really is conditionally independent of y given z, then everywhere that you have this, you can replace it by this. Okay? And you can see what this is going to bias, right? Is that here I was conditioning on two things. Here I'm only conditioning on one. In this case it's not very impressive, but suppose that here I was conditioning on 1,000 things. Then I have to estimate 2 to the 1,000 different numbers, and I'd be in trouble. Here I only have to estimate one number, and I'm in very good shape. Okay? So conditional independence can really bias a lot. And again, unconditional independence is not interesting because it just means that things are unrelated and they don't carry information about each other. Okay? So a more compact way to write this is to just say P of x given yz is equal to P of x given z. But when you see something like this, you have to remember that this statement is actually a whole bunch of different statements. It's P of x for every possible value of x, conditional on every value of y and on every value of z, right? Each and every one of those things has to hold for the conditional independence to hold. So it's a strong condition. Okay? Again, this condition can be relaxed in some ways, but we're not going to look at that here. Okay? So this is what Bayesian networks are based on. Here's a very simple example. There's a thunderstorm. Okay? Now, if you think about it, right? Let's say I ask you, how likely is it that we will hear thunder in the next 5 minutes? Right? Right now we're indoors. You don't know what the weather is outside, so you just can use your prior probability for thunder, which is probably pretty low. Right? But if I now tell you that it's raining outside, does that make your probability of thunder go up or down, or does it stay the same? It goes up, right? Because there's a storm. And when there's a storm, there's more likely to be thunder, right? So thunder and rain are not independent. Rain tells you something about thunder. Okay? But let's suppose that now you actually see a bolt of lightning. Are you going to hear thunder in the next 5 minutes? Well, yeah. And what if I now tell you that it's raining? Who cares, right? You already know that there's going to be thunder, regardless of whether it's raining or not, right? This is what conditional independence is all about. Rain has information about thunder, but that information is subsumed by the information in lightning. If you don't know lightning, it's good to know rain. But if you know lightning at that point, if all that you want to do is predict thunder, it doesn't matter if it's raining or not. Okay? So thunder is conditionally independent of rain given lightning. Okay? And by the way, of course, the conditional independence assumption is an instance of this, right? This is what Navier-Bayes is doing. It's saying that P of xy given z is just the same as P of x given z times P of y given z, where z is the class and x and y are attributes. Okay? Questions? Okay, so here's a nice little example. You are a park ranger, right? You have such an interesting life when you do machine learning. You know? On Saturday mornings, you play tennis with your friends after partying on Friday night, right? And now you're a park ranger. You know, it's like you get to live vicariously when you're in machine learning. Actually, there's a famous statistician, John Tukey, who said, like, the beauty of being a statistician is that you get to play in everybody's backyard. And this is true, right? The biologists will always be doing biology, the marketers will always be doing marketing, but you, as the demanding person, get to work with a different set of these people, you know, every year. It's endless fun. Or like another famous machine learning person says, you know, like, he went into machine learning because that way he could remain a dilettante all his life, right? In this world of over-specialization, one of the last fun things you can be is a machine learning expert, because then you get to, you know, work with 20 different kinds of experts. So, on that note, tonight I invite you to be a park ranger, right? I bet you didn't see that one coming. Although the mention of thunder and lightning might have, you know, put you in the mood for that. So, you're a park ranger, and of course a big part of your job is to prevent forest fires, right? Prevent, you know, detect early, put them out, so on and so forth. And so, you know, you being a park ranger and at the same time, you know, an expert on machine learning, right? This is very rare, right? You're a park ranger with high expertise in machine learning, right? You're a very valuable person. So one night you have nothing to do and you build a little Bayesian network for predicting whether there's going to be a forest fire, right? So what might that Bayesian network look like, right? It's night and you're in your tent, you don't have a lot of light and a lot of time, so it's going to be a small, simple Bayesian network. And let's say it's like this, right? So this node here is forest fire. So the first thing that you do when you design a Bayesian network for a problem is you write down the variables, and there's going to be, you know, as the name implies, it's a network, so it's going to be a graph, and it's going to have a node for each variable, okay? So one variable, and let's say, to keep things simple, they're just going to be Boolean. So one variable is whether there's going to be a forest fire or not, which is what you're interested in. Another variable is whether there's a storm or not, right? Now you're trying to put in the variables that you think are relevant to predicting whether there's a forest fire or not, knowing that in some cases you might have access to some of them, and in other cases you might not. Okay? So certainly storms could cause forest fires. Why? Because there's lightning, right? If there's storm, there could be lightning, and of course lightning could start a forest fire. Okay? But now, because you're a very smart park ranger, you also put in thunder. Now thunder doesn't cause forest fires, so why would you put it in?
Because it can be a sign of lightning, which causes forest fires.
Precisely, right? This is what's so deep about Bayesian networks, is that not all reasoning happens in the obvious direction. Lighting causes thunder. So if you're in your tent that night and you hear thunder, right? But you didn't see the lightning because your tent is very nice and opaque, right? Or you're under this big canopy of trees, right? You can still suspect with high confidence that there was lightning, right? And therefore there's a chance of forest fire, right? So a lot of these things that are indirect sources of information are worth putting in your model. Okay? Of course, the other source of forest fires is those darn tourists. Right? Of course, they do pay your salary, right? So maybe, you know, you need to deal with them, right? So if there's a bus tour group, right, that could also cause a forest fire because, for example, they could light a campfire, right? They got carried away with being in the forest and living the natural life and whatnot, and they lit a campfire. And then the campfire got out of control and you got a forest fire. Okay? So the next thing that you do, as you've already realized from my drawing here, is that you put in the arrows between the things that directly depend on each other. This part of designing a Bayesian network is very fun and very intuitive, and in fact is another way in which you can put knowledge into your model, right? Bayesian networks give you a beautiful way to incorporate knowledge into your model. It's beautiful because it's very rich and powerful. The knowledge is encoded in where you put the arrows, and in fact it's even more encoded in where you didn't put arrows, because those are the things that do not really depend on each other. It's also very beautiful because it does a really good division of labor between man and machine. People are good at this type of qualitative reasoning, saying like, oh yes, campfires cause forest fires. Computers don't know about causality and stuff like that. Or, like lightning can cause forest fires. But then the thing that people are not good at all, but computers are very good at, is computing parameters. Right? If you now ask your, expert, well, how likely exactly is it that there'll be a forest fire if there's a campfire? Well, that's a very hard thing to guess. But if you have a data set, right, of forest fires and campfires and tourist groups and storms and whatnot, then the computer can, in a fraction of a second, run through that data set and compute the necessary probabilities. Which brings us to the second part of the Bayesian network. So Bayesian network has two parts. The first one is a graph with nodes for the variables and arrows to a variable from the things that it depends on. Okay, so this is the intuition. There's arrows to forest fire from lightning, from campfire. Notice, for example, that, of course, there's an arrow to campfire from bus tour group, but there's also an arrow to campfire from storm, right? Do you agree with that arrow? Why would there be an arrow from storm to campfire? Hey,
Less likely to have a campfire when there's a storm.
Is what, sorry?
You're less likely to have a campfire if there's a storm.
That's one, yeah, exactly. So that's one thing, right? And now you can imagine, well, let's see. Here's more things that you could imagine, right? If there's a bus tour group and it's stormy, then, people are more likely to light a campfire because, they want to feel warm. On the other hand, maybe, if there's a campfire and there's a storm, the rain will put out the fire. Right? And there's another moral in this story, which is, if you want to capture all the details of the problem, you will wind up with a completely connected network. Right? There's always a path by which everything, you can always make up a story, right? This is what you, as a human, can do that computers can. You can always make up a story by which anything depends on anything else. In fact, this has been called the first law of ecology, right? Is that everything depends on everything else. But we can't handle that in machine learning, which means that you, as the machine learning expert, need to make this judgment call about what are the dependencies that are important enough to include versus not. Including all of them is not an option. But if you don't include the important ones, then you'll have an inaccurate model. Okay, so it really takes expertise and judgment to do this, and of course, it might take multiple iterations. Okay, so but let's suppose that you just had, created this network. Now there's the second part missing, which is equally important, which is the actual parameters. So what are the parameters in the Bayesian network? They are for each node a table giving the conditional probability of that node given its parents. So for example, for campfire, right? Campfire has two parents, storm and bus tour group, right? And so, assuming they're all Boolean, those parent variables can be in four possible states, right? There's a bus tour group and there's a storm, there's a storm but no bus tour group and so forth, okay? So what I need to know in my Bayesian network is for each of those configurations, what is my probability of campfire? Let's say 0.4, 0.1, 0.8, 0.2, okay? And also my probability of not campfire, but these ones are really redundant. Why? If I know the probability of campfire, right, what is the probability of not campfire? It's just 1 minus that, right? So really, for completeness, I'm putting that here, but you really only need to start the first one. Okay? So already here is the moral of the story, which is that if each node does not have too many parents, you're in good shape. Right? Because notice, the size of this table is going to grow exponentially with the number of parents. If you have a lot of parents now, then you're not in good shape. But the beauty of Bayesian networks is that I could have a network over a lot of variables. As long as each one of them only has a few parents, you can learn a model. Okay? Questions?
So, when you talk about parents, are you talking about ancestors, all parents, or
Very good. So let's get to that. So first of all, what this table is the probability of the node given its parents. So for example, for lightning, right, it's a very simple table because it only depends on storm. Okay? For forest fire, here's a more interesting case. Forest fire. Who are the parents of forest fire?
Storm, lightning, and campfire.
Storm and campfire. So what about bus tour group? Bus tour group is not a parent of forest fire, right? The definition is you're a parent if you have an arrow to the node. But forest fire does depend on bus tour group, right? We already saw that. So how come I don't need to have a table for forest? So what is the table that I need to have for forest fire? It's the probability of forest fire as a function of storm and campfire, not as a function of bus tour group.
Is lightning included also? Let's say it's storm, lightning, and campfire?
Yeah, what do you think? Is it included or not?
Well, it's also a direct parent of forest fire, so
Oh,
I
yeah,
assume it is included.
Absolutely. So very good. So what
So
are
there should be 8 conditions then?
Yeah, exactly. So in this case, forest fire depends on lightning, storm, and campfire, right? So there's 8 conditions. So you need a table with eight columns, basically, right? You do not need bus tour group in there, and you also do not need thunder. Okay. And what is the reason? So this is the rule, right? But now let's see why this makes sense, right? Did I just pull this out of my hat? Not really, right? So what is this Bayesian network really saying, right? Well, we saw that a Bayesian network is all about exploiting conditional independence, and then I gave you this sort of like example, right? An intuitive justification for how you built it, but how do the two things connect, right? Another way to ask this question is, if you give me this network, what conditional independences are you saying hold, right? Because that's really technically what's going on here, right? So for example, one of the things that I'm saying is that forest fire is conditionally independent of bus tour group given campfire. Because I'm saying that bus tour group only affects forest fire through campfire. Again, of course, this is an oversimplification, right? Somebody might be smoking and, throw out, their cigarette and so on and so forth, right? But, in this simplified setting, right, I can ignore bus tour group even though it's an ancestor of forest fire. It does have an effect on forest fire, but it's only through campfire. So my table only needs to talk about campfire, right? So the rule is that each node is conditionally independent of its non-descendants given its parents. Now this is a mouthful, but it's worth understanding. So, given its parents, a node does not depend on its grandparents or grand-grandparents, right? This is like, genomics, right? Your genes depend on your ancestors, right? But given your parents' genes, they don't depend on them, right? Everything, that your grandmother could say about you is in your parents. Okay? So this one is sort of like the easy part, right? Given your parents, you're independent of your ancestors, right? But notice that I'm saying more than that. I'm saying only independent of its non-descendants. So for example, does campfire depend on forest fire, even given storm and bus tour group? Right, just think about this intuitively, right? I've told you whether or not there's a storm and whether or not there's a bus tour group. If I now tell you whether there's a forest fire, does this tell you something about whether there was a campfire or not? Yes, it does, right? Because if there's a forest fire, this makes it more likely that there was a campfire, right? Meaning forest fire has some information about campfire that is not contained in storm and bus tour group. Just like, so the rule is your children have information about you, right? They're your children, you're closely related, right? And therefore, if your children have information about you, so do their children. So your descendants have information about you as a node in a Bayesian network, even if you know your parents. Okay? Notice, however, that this does not mean that I need to have my children in my table. My table is only with my parents. Okay? Why is that? Well, here's where the trick really happens. Remember the product rule? Right? P of x and y is P of x times P of y given x. Right? Let's do that product rule actually for a lot of variables. Right? So P of x1, x2, xn. Right? The product rule says that this is what? This is P of x1, right? Times what? P of x2 given x1, right? Times P of x3 given what? Right, just think of x1 and x2 as one Cartesian product variable, right? So this is P of x1, x2 times P of x3 given x1 and x2, right? You agree? This is actually the crucial step, right? The probability that they all happen is the probability that the first one happens times the probability of the second, given that the first one happened, times the probability of the third, given that the first two happened, okay? And what's the last term in here? It's P of xn given what?
x1 to xn minus 1.
Given everybody else, right? Ouch. That's what we can have, right? I can estimate P of x3 given two things, not a big deal, right? Let's say they're Boolean, right? But P of x1 given 500 other, P of xn given 500 other variables, no, right? So what I would like to do is simplify this long chain of things such that each variable only depends on a few of them. And then I'm in good shape. And this is really all that the Bayesian network is doing. For all its sophistication and complexity, all that the Bayesian network is doing is saying, well, but if x3 is conditionally independent of x2 given x1, then this guy can go away. Fewer parameters. And if xn, for example, only depends on xn minus 1, sorry, if the only parent of xn is xn minus 1, then all the others can go away. It doesn't mean that xn doesn't depend on them, right? But it only depends on them via xn minus 1. Okay? So what the Bayesian network allows us to do is to take the, so the chain rule, right? The product rule, when you apply it many times, is often called the chain rule, is to take the chain rule where these probabilities are getting conditioned on ever, more and more things and make them short again. But also notice the following thing is that it actually doesn't matter for me at this point whether x3 depends on x5, 6, 7, 8, 9, and 10, right? Their turn will come to depend on x3. At this point, I only need to worry about whether x3 depends on the variables that were before it. So the recipe for constructing the Bayesian network is that you have to pick an ordering on your variables. And then when you look at each variable, you only try to figure out who does it depend directly on out of the variables that I saw before. The variables that come after, their tables will take care of those dependencies. Okay? So what the Bayesian network lets you do is turn this big train of things into just this expression. The probability of my complete state is just the product over all the variables of the probability of each variable given its parents. Right? So what it allowed me to do was replace x1, x2, x blah, 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 blah by just the parents. This is really all that's going on. Right? If you can make conditional independence assumptions, then you can shrink the number of things that appear in here. On a good day, you can shrink them till these are all small tables and learning is easy. On a bad day, you can't and learning is still hard, but then what you do is you make false assumptions, you oversimplify. Right? This is what naive Bayes does. It's like, I'm going to ignore those dependencies and just make them simpler until I have something that I can estimate. Okay? Questions? So by the way, so now we know about Bayesian networks, right? And obviously naive Bayes is a special case of a Bayesian network, right? It's a Bayesian network where I make the strongest possible, conditional independence assumptions that still allow me to do something useful. So here's my question for you. What is the Bayesian network corresponding to naive Bayes? Well, let's say, I have my class here, right? And then I have my attributes, A1, A2, let's just put 4 down. A3, A4, right? So, over to you. What is the graph?
All arrows pointing towards the class.
So, all the attributes are connected to the class, right? Right? Because they depend on the class. You agree? Right? Very good. Are there arcs between the attributes?
No.
No, that is the precious thing that we gained with the naive Bayes assumption. There are no arcs between the attributes, right? Again, notice that they can depend on each other through the class, right? But not directly. Okay?
Wait, so which direction do the arrows point?
Very good. That is the final and trickiest question. Which direction do the arrows point? Okay, you have a 50-50 chance of getting this right. So there's two choices, right? They either point from the attributes to the class or from the class to the attributes. So let's have a vote. Who says it's from the attributes to the class? Okay, 1 vote there, 2. I can't count on Microsoft. There's at least 1. So 3, 4, 5, 6. 6. Okay, roughly speaking. Who says it's from the class to the attributes? 1, 2. There's a lot of abstains, right? You guys aren't playing the machine learning game. Do you feel like it today? Come on.
They're procrastinating.
Oh, very good. Yes, exactly. Yeah. Okay, I take it back. You are thinking like machine learning people. Yeah. So, okay, anybody want to justify?
The class to attributes is trivial, basically.
Sorry, one more time.
Like, class to attributes is trivial, right? Because you go from attributes to the class.
So here's one option, right? I mean, you got to at least say that this makes a lot of intuitive sense, right? The class is determined by the attributes, right?
I'm going to change my answer and argue for the opposite one. So the equation we had, so the arrows go from parents to children, and the equation we had, parents was on the right, is like, attribute given parents, and then in the naive phase, it was attribute given class, which implies the class of the parent.
Yeah, absolutely. So, oops, now I'm erasing the whole thing, but never mind. So let me draw this again, right, and go back to our situation of high suspense. You actually found this answer the hard way, right, by looking at the math. But you're right? You can't disagree with this. Like you just like line up the definition of Bayesian network with where the arrows go, and now do this for naive Bayes, and you conclude that the arrows go this way. It's the class that's the parent of everybody else, right? Now, why is this the case, right? Here's what, at least in my mind, would have been an easier answer to this question, right? An easier way to arrive at this answer. What happens if the arrows are from the attributes to the class, right? I need a table for the class, right? And how many entries is that table going to have if I have n attributes? N Boolean attributes.
2 to the number of a.
2 to the n, right? So if the class is a child of all the attributes, we're hosed. We didn't gain anything, right? The whole point of naive Bayes was to avoid the situation. Right? What I need is humongous table that there's no way to estimate. If the arrows go from the class to the attributes, now life is good, because I just need a teensy little table for each attribute as a function of the class, which of course is what naive Bayes does. Okay? So if you got this wrong, don't worry, because this was a trick question, right? The intuition here is actually in the wrong direction. Like, well, sure, I mean the class, is what determines the attributes. But in a way, what's really happening here is that we are doing the opposite of what would be intuitive, because it's what serves our machine learning purposes. And again, this very often happens, right? You do the opposite of what's the natural intuitive thing, because it's what, remember, this is all there to serve you at the point where you need the data to give you the information that you need. Okay? Questions?
Is it wrong to think of this way too? In the Bayesian network, you were kind of building the model, right, through inductive by saying this depends on this, finally it depends on the class. Whereas here, you're estimating from the classification.
Right, so this is a good question, right? But which gets us to another interesting point, which is, if you think about using naive Bayes for medical diagnosis, right? Actually, this diagram makes total sense then. Because it's your, you have the flu. Therefore, because you have the flu, you have a fever, right? So if you build a medical, people have indeed done this, right? If you build a Bayesian network for medical diagnosis, it will have this shape, where the arrows go from the diseases to the symptoms, because that's actually the natural setting. But there's many other settings where it's the opposite. And this gets us to the strange questions like, what is the relationship between what we're doing here and causality, right? Notice that the intuition, and it's a good intuition, is to have the arrows go from the causes to the effects. This is a very good rule of thumb. When you're building a Bayesian network, let the arrows go from the causes to the effects. After all, this is what Bayesian Bayes theorem is for, is that that's where your knowledge is, but then you can turn it around, go from the effects to the causes, from the symptoms to the disease, right? But the key thing to realize is that this is actually what you know that the machine doesn't. The machine doesn't know anything about causality. It's just measuring correlations, which is actually all the more reason why you should put in your causal intuitions. And in fact, it's a nice exercise to do, which is the same distribution. If you pick a bad ordering for the nodes, we'll get a very large Bayesian network. If you pick a good ordering, which is typically the causal one, we'll give you a very small Bayesian network. Now, of course, what we'd like to do is to actually infer causality from data. We're not going to look at how we do that here, but in some cases you can actually do that. So yeah, that's a very good question. More questions? Okay, so we are almost at the end of our time. There's still a couple things to cover. If necessary, we'll finish them next time. But let's go on to those. So now we know what a Bayesian network is. As usual, first we saw the representation, what it can do, what it's good for, how you encode prior knowledge, and so forth. But now we actually have a question to answer before we go on to learning. And this is the question of how do we do inference in Bayesian networks? And what do I mean by inference? Inference is actually, when you say that, oh, Socrates is human and humans are mortal, therefore Socrates is mortal, right? So we saw one example of inference when we looked at, first order rule induction, right? Inductive logic programming. In the case of something like a decision tree, the inference is trivial, right? It's like you go down the tree and you take the class from a leaf, right? But in Bayesian network, inference is actually potentially a very complicated thing. Because what you have when you're doing inference in a Bayesian network is, I tell you that, today there was a storm and there was lightning, and I tell you that, I don't tell you anything about bus tour group and campfire and thunder, and now I want to know the probability of forest fire. How do you answer this question? I haven't actually told you yet how you answer this question. And for some other representations it was obvious. In this case it's not obvious. Notice also that what we're doing here is a lot more powerful than a lot of the things that we've seen so far. Because all that a decision trees gives you is, are you going to leave the website or not as a function of your clicks so far and your demographic information and whatnot. In a Bayesian network, you can actually do something much better. You can compute the conditional probability of any variable or any subset of variables given any other, right? A Bayesian network isn't just one classifier, it's a whole bunch of them. It's a classifier for any variable given any subset of the other variables. I can ask, probability of forest fire given storm and lightning, or given storm and campfire, or I can ask about the joint probability of thunder and forest fire given just storm. Any of these combinations is possible. Now the question is, how do you compute that? I haven't told you yet, right? So the simple way to compute this is to remember that this is just a compressed form, right? The Bayesian network is just a compressed form of the full joint distribution of everybody, right? If I give you a table, and in this case there's only 6 variables, there's 64 states, right? I could actually give you a table with every one of the 64 states and the probability of each one of those, right? And then the probability of whatever you're interested in can be computed just by summing some of those entries, right? Not a problem. Of course, the whole problem is that I can't afford that exponential blow up. My Bayesian network compressed my representation exponentially, but, this is a very big but, it did not necessarily reduce my inference time from exponential to polynomial. In the worst case, I might still have to sum out an exponential number of things. So in general, inference in Bayesian networks is intractable. This shouldn't surprise you so much because Bayesian networks are a very powerful representation. You can encode satisfiability problems, you can encode anything in a Bayesian network. Therefore, inference in Bayesian networks is intractable. So the Bayesian network could be compact, but then when you're summing out variables, you cannot avoid making an exponential number of computations. So one or two things can happen. Either the network is simple enough that you can do this exactly, in which case life is very good indeed, or it's not, in which case what you do is you resort to approximate methods. And there's a whole bunch of approximate methods. I'm not going to talk about them here, but the most popular one I'll just mention is something called Monte Carlo. Monte Carlo is a glamorous name for just using randomness. What you do is you generate samples from the network at random. And then, for example, let's say you want to compute the probability of forest fire given storm. What I do is I generate states from the Bayesian network where storm is always true, and I compute the fraction of those where there's a forest fire, and that's my probability. Okay? So in very, very simplified form, this is how Monte Carlo inference works. Okay? Exact inference is really just a clever way of doing what would, if you weren't clever, would just be exponentially summing over all the relevant states. Okay? So this is how we do inference in Bayesian networks. Now, of course, the remaining interesting question is, how do you learn Bayesian networks? But today we're out of time, so we will cover that next week. Okay? And in the meantime, have fun with collaborative filtering. All right, let's get started. Welcome back. Now that you are experts on collaborative filtering, in addition to already being experts on clickstream mining, not to mention all the algorithms that get used for these things, it's time to become experts as well on spam filtering. Right? And after that, you can name your price and get a job working for anybody, because the demand is high and the supply is low. Okay, anyway, in the meantime, here's what we're going to do today. Two things. First of all, we're going to finish talking about Bayesian learning. And in particular, we're going to do the thing that we didn't do last time, which is to talk about how to learn Bayesian networks. Very interesting and large subject in its own right that, we won't have a lot of time for, but we're going to cover that. And in particular, we're going to talk about one of the most important algorithms in the class, which is the EM algorithm. EM is not just used for learning Bayesian networks, it's used for learning a lot of things, but we will introduce it here, applicable Bayesian networks. We will see it again much later in the class when we talk about unsupervised learning and clustering. And there we will see that it's also used for clustering. So a very good algorithm to know about. And you can probably come up with new applications of it yourself. But then the bulk of the class is going to be one of the funnest topics in machine learning, which is neural networks. So we're gonna start talking about neural networks today. We'll probably only finish next week, but as you'll see, it's a very interesting topic. And as usual, please feel free to ask questions at any time. So let's start by briefly reviewing what a Bayesian network is. Right? A Bayesian network has nodes that represent what? Variables, right? And it has edges that represent what? What does it mean to have an edge between two variables in a Bayesian network?
The one influences the other.
Exactly. One directly influences the other, right? And in particular, the edges are directed. So having, for example, in this example here, campfire has an edge to forest fire, because that means that my distribution for forest fire is expressed as a function of its parents, campfire and lightning and storm, okay? So the graph of the network tells me what the independent structure is, right? And then remember, the formal notion is that each node is conditionally independent of its non-descendants given its parents. And last time we saw the reason for each part of this definition, right? It's a bit of a mouthful, but it makes sense. So the graph tells us who depends directly on whom. And then the other thing that we have is at each node, we have a table that tells us what the probability of that node is conditioned on its parent. So for example here, the probability that we have a campfire, given that there's, say, a storm and no bus tour group is 0.1, which makes sense, right? Because if there's no tour group, there's probably no campfire, right? There could be somebody wandering through the woods without a group, and they could have lit a campfire, but that's less likely, okay? So this is what a Bayesian network is. And remember, a Bayesian network is actually a more powerful thing than most of the stuff that we saw before, like rule sets and decision trees and nearest neighbor and whatnot. Because those algorithms, all that they gave us at the end of the day was a way to make the prediction of one value. Is this a good credit risk or a bad credit risk? Does this patient have diabetes or not, and so forth? A Bayesian network actually allows you to predict any subset of variables given any others. It's a much more flexible thing, right? I can look at this, it's like having an exponential number of classifiers all baked into one representation. Very handy thing to have. So for example, in this Bayesian network here, right, you could predict campfires as a function of storm and lightning, or as a function of storm and bus tour group, or predict anything else as a function of anything else. In particular, you don't have to know all the other variables to predict one. So for example, if I want to predict forest fire, and I know lightning and campfire, right, then I actually don't need to know anything else, right, which is good, right? But if I happen to, for example, not know campfire, then I can use instead storm and bus tour group. Because they tell me about campfire, and therefore indirectly they tell me about forest fire, okay? So this is very nice, this is very powerful, it's a very flexible representation, it's also very compact as long as each node doesn't have too many parents, right? This is the key thing. I can have a Bayesian network over a lot of variables. It remains compact as long as each variable only has a small number of parents. If one variable has a lot of parents, then we run into trouble and we need to do something else, okay? Now with this power comes the problem that we now have this problem of doing inference in Bayesian networks, right? How do we do this computation of the probability of some subset of the variables given another subset, and maybe ignoring the rest of them? And we briefly mentioned this last time, right? But the main thing that we didn't go into that we're going to go into today is how do we learn this from data, right? After all, this is our main purpose here, is to figure out how to learn these things, okay? And there are basically two main dimensions along which this problem can vary, and therefore for combinations, since each one of them has two options. So the first option is whether the structure of the network is known or unknown. Okay? So the structure of the network being known means that I already know this part. I'm just trying to figure out this part. Okay? I know who depends on what. What I haven't figured out, and the data is going to help me figure out, is how. How much. Okay? So this is one option, known or unknown structure. The other dimension is whether in my training data I have in each example the values of all the variables or only the values of some. Okay? We already faced this problem, or in a way a simpler version of this problem, apropos of what? Where did we look at this problem of learning with missing data?
Decision trees.
Decision trees, exactly, right? We had to figure out what to do if some examples were missing some of the values of the attributes, right? What did we do at learning time and what did we do at inference time? And, we saw a few solutions to that problem. In all truth, those solutions were purely heuristic, right? We had no particular guarantee that they would be good. They seemed to be reasonable. The solution that we're going to learn today actually is in some ways the well-founded solution to this problem. Okay, and you'll see why and how. And in fact, one thing that you could do is, if you have your training data with missing values and you want to learn a decision tree, maybe the first thing that you should do is actually run EM to learn a Bayesian network the way that we're going to look at here, to fill in the missing data. Right? People often don't do that because it's very expensive and doesn't scale as well, but at some level that is what you should do. Okay? So we're going to look at each of these combinations in turn. Right? So first of all, let us look at the case where the network structure is known and we have complete data. Okay? So we just want to learn now the parameters of the Bayesian network. So how might you do that? Hint, this is not a trick question and it's easier than it seems.
Just look at the data and infer the frequency with which.
Exactly, just look at the frequency with which things happen in the data. Right, remember, this is what we did when we learned naive Bayes. Right? In naive Bayes, all that we did was count how often each attribute value occurred with each class value. Right? That's all. That was all we needed to do. And if you think about it, a Bayesian network, as we saw last time, is a generalization of naive Bayes, right? So if we know how to do this for naive Bayes, then maybe we know how to do it for Bayesian networks in general. Okay? In particular, for example, let's go back to our Park Ranger example, right? What do I really need to do? I need to learn all these tables for all the nodes, right? But if I know how to learn each of these tables, then I'm done. And how do I learn a table? Actually, it's very simple, right? To learn the table for Campfire, right, I just have to count how many times, for example, when storm is true and bus to group is true, what fraction of that time Campfire is also true, right? And let's say I have 1,000 examples and 400 of them, I have 1,000 examples in this condition and 400 of those, have Campfire equals true, then the probability is 0.4. And since these are the days of big data, let's say that instead of 1,000 examples, you have 1 billion, right? Out of which 400 million have Campfire true. Doesn't this sound more impressive, right? But it's just as easy, right? It will take longer, right? But notice the time only goes up linearly with the size of the data, right? You can still do this amazing thing that is very appealing to people with large data problems of a linear scan of the data does the job for you. So what I have to do in that linear scan of the data is for each variable and for each combination of values of its parents, count how many times each value of the variable occurs. Okay? And then we're done, right? That is basically our probabilities when I divide each, for example, the number of times that C was true divided by the total number of times that S and B was true, right? And same thing for not C. I get my probabilities. Okay? Any questions? So learning Bayesian networks when the structure is known and there's no missing values is very straightforward and very fast, and this is really good. Okay? There's really no difficulty there. Okay? It's just the same ideas in naive Bayes generalized. Okay, but now let's go to the interesting stuff, right? What happens if you have missing values? And again, in the real world, most of the time you have missing values. And the larger your data set, the more likely it is to have missing values. So what do we do with missing values? Okay. If you think about it, there is no very obvious answer to this problem because it's a kind of a chicken and egg problem, right? Why is it a chicken and egg problem? Well, first of all, if there were no missing values, as we just saw, then the problem would be easy, right? We could learn a Bayesian network quite easily, okay? But now notice, so this is the chicken side, let's say. But now let's look at the egg side of things. The egg side of things is something that was not the case when we were learning decision trees, and this is the following. Suppose that I just gave you the Bayesian network for this problem, right? Suppose I gave you the structure and I gave you the parameters. So now you have the complete model, okay? Notice that given that, you could actually now infer the missing values, right? Because this is what the Bayesian network does. Let's say that, in this example, I knew, for example, everything but campfire and forest fire, right? What I would need to do is, using inference, one of the inference algorithms that we mentioned last time, compute the probability of campfire and the probability of forest fire given bus, tour group, storm, lightning, and thunder, which hypothetically I have, right? This is what the Bayesian network is for. So if I had the model, I could infer the missing values, and if I had the missing values, I could infer the model, right? So you see why this is a chicken and egg problem. Okay. Now, of course, the problem with chicken and egg problems is which one comes first, right? That's the whole problem, right? Do we do the chicken first or do we do the egg first, right? Well, the EM algorithm is an algorithm for solving chicken and egg problems in machine learning, right? This is actually the deep technical idea behind the EM algorithm, right? So how do we do it? By the way, EM is short for expectation maximization. And the idea in the EM algorithm is a very weird idea at first. EM is actually one of those ideas that it kind of takes a little, while to get your head around it. It's like recursion, right? The first time you see recursion is like somebody's pulling the wool over my eyes here. This can't work. But after a while you get used to it, and then it's a very powerful tool. EM is the same thing. At first it looks like a strange idea. But once you get used to it, it no longer seems strange, and it's a very powerful tool to have. And the basic idea in EM is the following. Which one comes first, the chicken or the egg? We don't care. Take a dinosaur, right? Take any old, ugly initial model that you want, or any old, strange way to fill in the parameters, right? This is your dinosaur. And let that dinosaur lay an egg, right? And out of that egg, hopefully will come a dinosaur. This is the key thing. That looks a little bit less like a dinosaur and a little bit more like a chicken, right? So out of this dinosaur egg came a slightly chickenish dinosaur. And then that slightly chickenish dinosaur lays an egg, which is now more of a chickenish egg than it was before. And on a good day, if things work well, little by little, your dinosaur turns into a chicken, and your dinosaur egg turns into a chicken egg. Right? I mean, biologically, this is what the answer to the question of which came first is, right? It wasn't the chicken or the egg, it was the dinosaur, right? And, this can go all the way back to amoebas and whatnot, but let's not go that far. Right? So the idea in EM is that you can start with a monster, but if you run through this process enough times, that monster will turn into a beautifully formed thing. In our case, a beautifully formed Bayesian network. Okay? So this is the intuition. Let's see how this works exactly. So you could actually, as I said, you could start with the chicken or you could start with the egg. It doesn't matter. In different applications, one or the other might make more sense. Typically, when we're learning Bayesian networks, we actually start by just ignoring initializing the parameter values. Right? We're going to start by filling in the complete model, right? Ignoring the information that we don't have. Okay? This is one plausible way to win. Is I'm just going to ignore the missing information, and I will get a model that's probably not terrible, right? It's not quite right, particularly if a lot of examples have a lot of missing information. This could be ways off from the truth. But it's a nice, quick way to get an initial model. Okay? So let's just say we start by doing that. We form our initial estimate of the parameters, just ignoring the missing information. And we will see a little example of this in just a little bit. And then what we do is we repeat 2 steps until we converge. The E step and the M step. The E step, the expectation step, is the step that consists of computing the expected values of the missing data with my current model. And this is why it's called expectation, because these are the expectations in the statistical sense, right? I don't know what this value here is, but I predict that it's 1 with probability 0.7 and 0 with probability 0.3. Okay, And I can do those computations using the Bayesian network, right? So I'm going to take my current model, broken as it may be, crappy as it may be, and use it to fill in my missing values. Okay? And notice that I'm not filling in my missing values I'm not truly filling them in with like 0 or 1. I'm filling them in with a distribution over their values. Just like we did in decision trees, remember? We saw like, well, I can just go and fill in the value, but a smarter thing to do is to fill it in with fractional examples that says, oh, 0.7 red, 0.2 blue, and 0.1 green. That's what we're going to do here as well. Okay? You could actually fill them in with full values. This is sometimes called hard EM because it forces things to go one way or another. It can be faster, but it's not as sound. Okay? So let's assume that we do the standard version. Okay? So at the end of this step, I fill in my missing values fractionally, right? So now what I have is fractional examples. But just as before, right, fractional examples don't really cause any difficulties. I just say, well, I have 1.7 examples that are red and, and 2.3 that are green and so forth. Okay? So this is the E step, where I compute expectations. And then the M step is the maximization step. This is the step where I find my MAP, or my maximum likelihood parameters, right? This is why we call it maximization, because we're maximizing either the likelihood or the posterior probability. Okay? Notice that because in the E step I filled in my missing values, right? Now I have all the information I need. Sure, it's fractional, but that's a detail. Now I can just do my standard thing of running through the data, computing my counts, right? So because I did the M step before, now I can do the M step, and what I have at the end of the M step is a new model, right? The structure is still the same, but the parameters in general will have changed from my initial ones. And this is the key, right? Is that running through one cycle of this algorithm changes the parameters, okay? And now the question is, but is that change for the better, or is that change for the worse? Or maybe we don't know. If we don't know, are the changes for the worse, then this algorithm does not look very good, right? The key thing about this algorithm, though, is that you can prove that going through one cycle of this always improves the likelihood, or posterior, but let's think of it in terms of likelihood. Or to be very precise, it never decreases it. So when I go through this cycle once, my model gets better, or if it doesn't get better, that means that I've converted and I can stop, okay? And in fact, the history of the M algorithm is very interesting because what actually happened, back in the 60s and 70s was that people came up with different algorithms that, EM was not known then, but there was, for example, an algorithm for training hidden Markov models for speech. And there was an algorithm for learning what are called mixtures of Gaussians that can be used for clustering, and we will see later, and so on. And then there were these very clever statisticians that actually noticed that these algorithms, seem to have something in common. Right? They look superficially different, but they were both dealing with missing information. Right? The common problem that these algorithms were solving is that they were trying to maximize likelihood in the presence of missing information. And they were solving that problem by doing this kind of chicken and egg computation. And so they abstracted from these algorithms this general scheme of how to do things, and that was the M algorithm. And they proved that in this general setting, the likelihood always improves, and when it stops improving, you can basically declare victory and go home. Okay? So this was a very powerful thing to do, right? One of the reasons this work is so influential is that they did not actually invent an algorithm. What they invented was an algorithm schema, right? And then tomorrow people can propose a new version of that schema. I can have a new statistical model, and I can apply EM to that statistical model. It doesn't have to be hidden Markov models or Bayesian networks or mixtures of Gaussians. It's whatever you want. Right? So EM is a very, very useful tool for that reason. It doesn't just apply to one particular class of models. Okay? Now, truth in advertising, there's one very important caveat here about how EM always gives you a better model. Can anybody guess at what that might be? Or, another way to ask this question is, what might the problem be? And let's say it's not overfitting, right? Overfitting is the default answer, and it's certainly a problem, right? But you can deal with overfitting using priors and whatnot, right? So what is the limitation of EM? Can anybody guess?
Local optimizations?
Exactly. EM only converges to a local optimum. In general, the likelihood landscape here. So here's a nice likelihood landscape of the type that we like to see. Here are my parameters. Let's call them W, traditional letter for parameters. And here's my likelihood, let's just call it P of W, short thing, right? And what we want is a landscape that has something like this. There's a global optimum, there are these parameters W0 where the likelihood is maximum, and you can start anywhere, and what the M algorithm will do is, basically walk over where it needs to walk and succeed. Now this is on a good day. Most of the time, including learning Mistress of Gaussians and learning hidden Markov models and learning Bayesian networks, this is not what happens. What happens is more like this. And now life is much tougher, right? Because, if you start over here, right, or let's say you start, between, let's say, here and here, right? Then you will converge to the right thing over there, right? On the other hand, if you start over here, you're going to wind up over there, which is not so great. Okay? So on the one hand, the M is an amazing thing because you do get things, things do get better as you iterate through the E and M steps. On the other hand, you could wind up with a very poor solution if you're not careful. Okay? So EM is an algorithm that there's an element of art to using it. Part of that art is figuring out where to initialize, initializing say here versus initializing say around here versus initializing around there. Another part of it is doing things like, do this multiple times, right? Typically when people use EM, what they do is they do multiple runs with multiple initial points, maybe random ones or some mix of randomness of some, or heuristics that you have for initialization. But you kind of need to do that in order to get a good result a lot of the time. And the other thing is that you never really know at the end of the day whether you learn the best possible model. But usually what you can figure out is that you learn the model that is good enough for your purposes, and at that point you can declare victory. Okay? And another thing that helps us in EM, which is actually not very obvious a priori, but is actually very, very fortunate, is that and we will see this again, for example, in neural networks, is that often what happens in these likelihood landscapes is that there are a lot of peaks and valleys. And they can be quite pronounced, but often you get something like this. This is sometimes called a porcupine curve, because it looks like the hair, like the bristles on a porcupine. And you can see why can you see why this looks very bad, but actually is not so bad? First of all, why is it bad?
Oh, well, why it's maybe not bad?
Go ahead.
Because there's a bunch of optimums, but they're all sort of about the same. So even if you don't get the optimum, you're going to get pretty close.
Exactly. This is a really important thing in a lot of machine learning algorithms. In fact, without that, a lot of machine learning algorithms would not work so well. So, in a way, this looks bad because there are these very narrow bands of convergence, right? There's a lot of local optima, right? This looks very tough, right? Finding the global optimum here is really difficult, right? I mean, in this case, we're in one dimension, but you can see how the high-dimensional version of this problem would be very tough. But the thing is, you don't really care. Because, look, there's this narrow band here, right, that contains most of them. So do I really care whether I get to this local optimum or this one? Nah. They're about equally good, right? This is machine learning. We know we're not going to find exact answers anyway. Okay? So when things have this porcupine shape, actually just getting to a local optimum is probably as good as getting to the global optimum, right? And there's actually, on top of this, another reason why we don't really care whether we get this one or this one. Can you guess what that might be? Again, this is very specific to machine learning, right? If this was some other optimization problem like scheduling or something, you would really want to get the best schedule that you can. But in machine learning, is it really important to get absolutely the highest likelihood model? Yes or no? No. Because?
Because what matters is the class that you're trying to learn or the target function. You're just focusing on the specific instance of the hypothesis that has maximum probability.
Yeah, exactly. Remember, our goal here is not to fit the training data well, right? For that, we could just leave it, sitting there on this cannot do anything. Our goal is to generalize. And if our goal is to generalize, it could actually be that this one actually generalizes better than this one, right? Maybe the non-global optimum is actually the better one, right? This might sound counterintuitive, but actually, looking at it from a machine learning point of view, it makes a lot of sense, right? Yeah. That local optimum is probably just as good for generalization as the global one, or maybe even better, right? So in some sense, you don't have to worry too much about getting the local optimum. Of course, there's some substantially lower peaks, then you want to avoid those, right? Because those probably are a lot worse. So you do need to make multiple attempts and whatnot, but probably at the end of the day, you will get something that is good enough, right? And indeed, EM is used very widely in practice. Right? When you use Siri on the iPhone, I don't know the details, but I'm willing to bet that the EM algorithm was used to learn the model that's doing the speech recognition for you. And you know how Siri works, right? It all goes to the server, so every time you use Siri, you're giving it training data. And there it goes into the EM algorithm, and the better model gets learned, then tomorrow things get better, right? This is the power of being Apple. Everybody uses your products, so it gets better because of that, right? Yeah. It's the network effects of data. Okay, so questions about this? Okay, very good. So, let's see an example. Let's see an example of EM. And by the way, one of the things that you have in your homework is doing another example of EM. Okay? And this is a very, very simple example, carefully contrived to be doable in one slide and converge quickly. In reality, EM does often not converge all that quickly. So this is another thing to be aware of. EM could take a long time to converge. However, if you want to scale up EM, there's something very simple that you can do to make it converge quickly. You know what that is? Just stop after some number of iterations. What usually happens in EM is that there's fast convergence at first. And then getting to that last optimum takes a long, long time. But again, you don't really care, so you can just cut it off after some number of iterations, and that's probably good enough. Okay? However, in this example, things do converge very quickly, and by devious design on our part. So here's our very, very simple example. We have a Bayesian network with 3 Boolean variables, A, B, and C. Okay? And here's our training data. It's not a massive data set. It's just 4 examples. And we have only one missing value, which is this one over here. Okay? So if this question mark, instead of being a question mark, was say a 0, then you can see that computing the parameters of this Bayesian network would be completely straightforward, right? In particular, what are the parameters of this Bayesian network? What are the tables that I need here? What do I need for A? Right, A is a Boolean variable, and it has no parents. So how many parameters am I going to have to learn for it? Just one, right? The probability that A is true, right? That's it. And the probability that A is false is just 1 minus that, right? What about, so this is one of the things that we're going to want to compute. What about for B? What do I need to compute for B? P of B given A, right? So, and how many states of A are there? 2, right? So I need to compute 2 parameters. Probability of B given A and probability of B given not A. And again, the probability of not B follows, okay? And then for C, it's the same thing, except as a function of B, right? So I have 3 tables to compute here, and they're all very small, okay? So let's do this, okay? Let's start by doing our initialization as discussed by ignoring the missing data, okay? So, what is my initial estimate of P of A?
0.75.
0.75, right? There is no missing data as far as A is concerned. Notice that ignoring the missing data is not ignoring the examples that have missing data, right? Because that would mean I would ignore the last example. That would not be a good idea, right? That would reduce my amount of available data and might also bias the results, okay? So I'm ignoring the missing data, but for each table, if for the entry that I'm interested in, I have the data, well, then I will use it, okay? So my initial estimate of P of A is 0.75, right? What is my initial estimate of P of B given A? Well, now we have a problem with missing data, right? Because the missing data really, does affect this, right? So, but let's just ignore that, right? So let's ignore that case. So what is my initial estimate of P of B given A? 0.5, right? Can everybody see why? Well, I have 2 examples, right? These 2, right? Where A is true and I know B, right? And out of those 2 examples, in one of them, B is true. So my probability is 0.5, okay? Everybody agree? Believe it or not, this was one of the hardest steps in this whole thing, okay? Okay, so what is P of B given not A?
1.
1, right? It's 1.0. Again, here I'm not affected by missing data because the missing example is in a case where A is true, right? And here A is, when A is, there's one example where A is false, and for that example I know B, and and then B is 1. So our maximum likelihood estimate of P of B given A is just 1. Okay? Easy one as well. Okay, what about P of C given B? We are affected by the missing data here, right? Because, that example might or might not be relevant for computing P of C given B. We don't know, right? But we're going to ignore it, so what do we get? We get 1 again, right? Why is it 1?
The first and the third examples.
Right, we have 2 examples where B is true, right? And in both of those examples, C is true as well. So P of C given B is 1. Okay? And finally, what is P of C given not B? 0, right? 0.0, because again, there's only one example. And when B is false, in that example, C is false as well. So 0. Okay? So this was our initialization step. And, this is not an ideal model, but if in this case there isn't a lot of missing data, so most of these parameters are probably not that way up, right? Which is why, then running through EM starting from here will probably get you to a good place. As a rule of thumb, and not a surprising one, if you don't have a lot of missing data, EM will probably work well. If you have a lot of missing data, EM doesn't do miracles. Okay? So bear that in mind. Okay? All right, so now let's do the exciting part, which is the E step, right? And then the M step, right? So the E step, in our case, there's only one missing piece of information, right? It's this thing over here. And what we want, remember, we don't want to fill this in with 0 or 1, right? We want to do something a little bit smarter, which is fill it in with the probability that B is 1. Okay? So what I want is the probability that B is 1 given the values of the other variables in that example, right? I do not want to throw away that precious information, right? I know that in this example, A is 1 and C is 0, right? So what I want to do is compute the probability that B is 1 given that A is 1 and C is 0. Okay? So I want to compute P of B given A and not C. Okay? And now this is just a problem of doing inference in the Bayesian network, right? And in general, this could be an expensive thing, right? But in our case, we can actually do it fairly quickly. Right? So in particular, right, we can use the definition of conditional probability. Right? This is a conditional probability that we're computing here. And we know that P of B given A and not C, right, is what? P of A, B, and not C over P of A and not C. Does everybody agree with this? Right? This is just my definition of conditional probability. If you think of, let's think of A and not C as a single variable state. Right? Then it's just saying like P of B given something, right, is just P of B and something over P of something. And this really is just a definition of conditional probability. Okay? Everybody agree with this step? Excellent. So, now, what is P of A, B, and not C? This is where the Bayesian network comes in, right? What is P of A, B, and not C? Let's do that. Let's do that up here, right? So, P of A, B, and not C, according to the Bayesian network, right, is equal to what?
0.
Yeah, absolutely. But let's do this one step at a time. Like, give me the general expression, right, before we fill in the actual values. Because remember, those values are going to keep changing, so we do want to, if we can, do this computation, in the abstract once, and then just use the result, right? There's also a good, opportunity to practice dealing with Bayesian networks, right? So what is P of A, B, not C according to the Bayesian network?
Probability of B given A times the probability of not C given B.
Almost, right? So let me write that down. Probability of B given A, right, times probability of not C given B, right? Is this it? That's right. There was a reason I left that space there, right? We're missing P of A, right? Remember, when in doubt, this is just the chain rule, right? Remember when we saw the product and the sum rule? It all boils down to the product and the sum rule. Inference in Bayesian networks is just applying the sum and the product rule over and over again, hopefully in smart ways, right? So if you just apply the product rule here multiple times, giving the chain rule, you would have P of A, right, times P of B given A, right? That is always the case, times P of not C given BA. right? In general, this would be the case. Right? This expression P of A times P of B given A times P of not C given BA is always true, right? This is just a chain rule. You agree? Why were we able to replace this by this? Conditional independence, yes, but where is it that by looking at this vision now where we can tell that conditional independence holds?
B is the parent of C, so if we know B, we don't need A.
Remember the rule that we had, right? This is a nice little application of it. The rule was that each node is conditionally independent of its non-descendants given its parents, right? So C doesn't have descendants, so we don't have to worry about those, right? So what happens is that C is independent of everybody else, meaning its other ancestors given its parent, which is B, right? I.e., C is independent of A given B, and therefore I can just write this as P of not C given B. This, in a nutshell, is what the Bayesian network buys us. Of course, here, I only omitted one potential parent, but in general, I could be omitting a large number of them, and a correspondingly exponentially large number of things that I would have to estimate. Okay, very good. Well, so now all that remains is to replace these probabilities by their actual values, right? So what is P of A? 0.75, right? And what is P of B given A? 0.5, right? And what is P of not C given B? 0. And therefore the product of all of them is 0. Okay? And so we're not even going to bother to compute P of A not C, right? Because we don't need to. The result's going to be 0. But let's just pretend for a moment that we did have to compute that. How would we do that? Again, this is another nice little exercise in Bayesian network inference, right? Suppose that we really did, in general, this would not have come out 0, right? So we would need to compute the denominator as well as the numerator. So how do we compute P of A and not C? Here, let's do this. So P of A and not C is equal to
times P of B given A. So
let's do this in two steps. First of all, let's not even use the Bayesian network. Actually, here's a hint. You know how I said inference boils down to applying the product and the sum rule? We haven't applied the sum rule yet, right? We've applied the product rule. So maybe it's time for the sum rule to show up, right? So with that hint, how would you do this? What is P of A and not C?
I think there'll be two terms. One for probability of B given A, and the other term probability of not B given A, and then probability of...
I agree, right? So, but when you talk about P of B given A, you're really kind of already bringing the Bayesian network or the chain rule into play. But you're right. So there are two terms, right? One of which involves B, and one of which involves not B, right? The reason why this might stump us at first is that there's no B here, right? The Bayesian network we just saw tells us how to compute probabilities of complete states, right? It gives me probability of A not B, C of A, B not C, all of those things, I can compute using the chain rule, right? And, the independencies that I have in the Bayesian network. But the problem that happens here is that I have to get rid of B. And in fact, it's having to get rid of variables that makes the problem potentially exponentially costly. Because the more variables I have to get rid of, the exponentially more states that I have to sum over. But in this case, there's only two, right? So P of A not C is P of A B C plus, P of A B not C plus what?
P of A not B not C.
P of A not B not C, right? Does everybody agree with this? To say this in English, right, what this is saying is, well, for A and not C to be the case, right, one of two things has to happen. I have to be in one of two worlds. Either A and not C and B, or A and not C and not B, right? One of those two things has to happen. Okay? And now that we have things in this form, now we're back to our old case, right? In fact, this one we already computed, and computing this one would be the same process, except you'd be filling in, a couple of different parameters. Okay? Everybody got this? Okay. So, we're at this point. So we finished the E step. Finish the E step means that I filled in my missing values. And in this case, I get a probability of 0, right? So I can actually just fill this in with 0. Right? I know that this thing is 0 for sure. In general, I would have a fractional number there, like say 0.3, and then I would need to compute fractional counts, but to keep things simple, we're not going to do that here. But remember that, in real applications of VM, that's what's going to happen almost all the time. Okay? So now, I have filled in my missing data. Lo and behold, I have a complete table, right, of my instances and their values. So now I can go and recompute my parameter estimates, my maximum likelihood parameters, using my filled in data. So let's do that. What is the new P of A? Has it changed? Well, that one obviously hasn't changed, right? Because P of A was never affected by the missing information anyway. So this is still 0.75. What is the new P of B given A? 1/3, right? Because there's 3 examples where A is true, and in only one of those is B true, right? One of the ones where it's false is the new one that we just filled in, right? So this is now 0.33, 3333, etc. Okay. What about P of B given not A? That is still 1, right? That hasn't changed. What about P of C given B? Still 1, right? There's 2 cases where B is true and C is true in both of those. What about P of C given not B? Right? Again, our missing information comes into play here. What is this one? It's 0, right? Because I have these 2 cases of not B, right? In both of those cases, C is also false. Okay? So this again is going to be 0. Right? So at the end of the nth step, what I now have is better parameters than I had in the initialization. Right? So I went through one cycle of my algorithm, and now I have better values of the parameters. It's not obvious that they're better, but the theorem that those statisticians proved guarantees to us that things at least did not get worse. Okay? They either got better or we've converged. So in this case, have we converged? Well, we don't know yet, right? Because at least superficially we probably haven't, because the parameters here and the parameters here are different, right? So when have we converged? We have converged when the parameters are not changing, right? If in 2 successive iterations, if in 2 successive m steps I arrive at the same parameters, I know that I've converged, right? Because after that they don't change. What is the other way in which I could detect convergence? Looking at the E step. Right? How can I detect convergence by looking at what happens in the E step? Remember, the E step is where I fill in the missing data. When do I know that I've converged? Yeah, when in 2 successive E steps I get the same filled in parameters. I get the same filled in expectations, right? Because that means that the training data that I'm going to have for learning the parameters is going to be the same in both cases, so the result has to be the same. Okay? So now what we would do is, after having done this same step, we would now go and do another E step. And it's easy to see that it's in this E step, my probability again comes out 0, right? Again, it's because this probability here actually hasn't changed. It's still 0, right? So this new probability is going to be 0 times blah, 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 which is still 0. So by comparing the 2 E steps, right, in both of them, the missing information is filled in with the same values, and therefore I've converged, right? If I run another M step over this, it would just give me the same results over again. So I'm done, okay? And this is how the YAM algorithm works. Questions? All right, very clever idea, very widely used. So, now let us go on to the, actually, as usual, I flashed up the slide and then I'm going to hide it from you. So let's go back to our various problem settings, right? So we just figured out what to do when the network structure is, we just figured out what to do. Excuse me here. We just figured out what to do when some of the data is missing. Okay. But now let's go back to assuming that we have all the data, right? So there's no difficulty there, but the difficulty that I have is that I don't know the structure of the Bayesian network. This is the more interesting problem, right? We don't just want to learn the parameters of the Bayesian network. We want to learn the structure if we can. Right? So how might we do that? Any suggestions? Well, think about it. This is going to be a discrete search type of problem, right? It's like we're trying to learn a structure at this point, right? Parameters, usually we do continuous optimization in one form or another, right? But this is more like learning decision trees and rule sets, right? I'm trying to find what the structure of that Bayesian network is, right? So this is probably going to be some sort of search process, right? Where I search over structures. Right? At any one point in the search process, I have a structure, right? And I can quickly fill in the parameters, right? Because there's no missing data, so one sweep of the data does that for me. And in fact, if we do this cleverly, I don't even need to recompute all the parameters as I change the structure. But how might I do the search for structure? Okay, let's think about this, right? Well, let's see. What do we need to do search? The first thing is we need an initial state, right? If you're trying to learn the structure of a Bayesian network, where might you start? What might be your initial structure?
Everything implies everything.
Everything what?
Everything does everything.
You mean arcs between everybody? That's one option. It might not be a very good one. Why?
Because it's going to be really computationally expensive to figure anything out.
Yeah, I'm going to have some very large tables to estimate that. Right? It's not just computationally expensive, it's going to be unbearable from the point of view of the sample. Right? Some node in there is going to have all the others as its parents. So what's another option? So this is a little bit like forward and backward selection and tree pruning and post pruning, right? In this case, the backward version is not going to be, very good, right? But what's the other option? Yeah. I start with nothing, right? Now, this is a joyfully, efficient Bayesian network to start out with, right? Is you assume everybody's independent. There are no arcs in the network, okay? And then estimating all my parameters is going to be very quick. And then what I'm going to do is I am going to add arcs where the data demands that I add them, and nowhere else, right? Adding arcs is expensive. Remember, the cost of storage and the cost of inference may go up exponentially with the number of arcs that I add. So I want to be pretty conservative about adding arcs. So it's good to start with an empty network and then just refine it. Okay? So how might I refine it? So question 2, right? So I have an empty Bayesian network. So what kind of search operators might I use now? Right? What might you want to do? What is a natural search operator when building up a Bayesian network starting from an empty one?
Some sort of correlation with.
Absolutely right. You want to detect that, say that, let's say, for example, that we were learning the Bayesian network in the example that we just saw, right? So we had A and B and C, right? Empty network. What do you want to do here? For example, that B depends on A, right? So you want to allow yourself to add an arc from A to B. And then maybe you want to allow yourself to add an arc from B to C, right? So what is a good operator to have? Add arc, right? Right? Don't try to be very deep about it. This is very simple, right? Think of it as a graph, right? I'm building up a graph. The graph starts out empty. I want to have some edges in it, right? Assuming there's going to be, some non-trivial, structure to learn, right? My operator can just be add an edge. What should be my, so I have this simple operator, add edge, right? So what I can do is I start out, this is a little bit like learning, decision trees and rule sets, if you think about it, right? Instead of adding antecedents, I'm adding edges. Right? So what might I do? I can look at all the possible edges that I could add, right? And I score each edge, right? And then I pick the best one, add that to my network, and then I repeat and add another edge, right? And little by little, I can learn a very good Bayesian network, if things go well. Right? But there's something very important that I have to be careful here as I add my edges. Something I didn't have to worry about when we were learning decision trees and rule sets. What might that be?
Cycles.
Sorry?
Cycles.
Cycles. Yeah, cycles, right? If I just do this, add edge, there's nothing to prevent me from doing this. And what is a Bayesian network with cycles? It's nothing. It's meaningless. Remember, a Bayesian network is just a clever way to take advantage of the chain rule. The chain rule implies that there's an ordering for the variables and you're putting them into the product using that order. If the graph has cycles, I don't know what that means. I don't know what kind of chain rule application that maps to. Okay? So I have to forbid cycles. So at every step in the algorithm, as I look at adding more edges, I have to exclude the edges that would create cycles. This is very unfortunate because as the network grows, as you can imagine, it becomes expensive to check that this new arc will not create a cycle. But there's no choice. I have to do that. Okay? So next question: how do I evaluate? Right? Let's say I'm trying to decide whether to add an arc from A to B or an arc from C to A. Right? How do I decide which one is better? How should I evaluate my arcs? In some ways, this is the most interesting part of this process because the rest is kind of straightforward ideas, right? How should you evaluate it?
Higher degree of dependence.
Correlation.
Yes, correlation. That is absolutely the right intuition, right? I want to add an arc between A and B. Maybe that should be the first arc that I add if the correlation between A and B is the strongest that I have in my data. Okay? So how might I measure that correlation? Well, one thing that I could do is actually measure the correlation, right? So one approach to building Bayesian networks actually does just that. It measures correlations between the variables, and it puts arcs where there are strong correlations. You can use things like significance tests, right? So like, is this correlation that I'm observing in the data significantly different from what I would observe if there wasn't any? And those arcs I add, otherwise I don't. Okay? But another thing that you can do, which is the most frequently used one, is to just measure the likelihood. Right? Remember, when we were learning, think back to the basic idea of Bayesian learning, right? Or statistical learning, right? Is I'm trying to learn a model, I'm trying to learn a Bayesian network that has the maximum likelihood, right? Or that has the maximum posterior probability, right? And when we were learning the parameters, right, when we were doing EM, right, we pick these values because they're the maximum likelihood values. If I have 100 examples and in 50 of them B is true, right, then the maximum likelihood estimate of the probability of B is 0.5. And that's why I choose 0.5, right? And now we want to apply the same idea, right? We should be consistent, right? This is statistical learning. I still want to maximize my likelihood, right? So what I should do is I try adding each edge to my network, right? And then I measure the likelihood of the resulting network with the maximum likelihood parameters, right? Simple idea, and again, that can be done fairly efficiently. And if you're careful, about caching things and whatnot, you can avoid redundant computation, and it's going to be pretty fast. Okay. So the basic criterion that you can use for this is maximizing likelihood. But do you think that really is a good thing to use? What might the problem with that be? This is where we get to see a deep understanding of machine learning.
Overfitting.
Yeah, overfitting. Brilliant insight. Why might overfitting be a problem if using maximum likelihood for structural learning?
Because you maximize into the training data.
What's the maximum likelihood structure? Right, we can ask that question, like, what is the maximum likelihood structure? Can anybody guess? This is where you really see how bad things can be. The maximum likelihood structure is guaranteed to be the completely connected structure. Others might tie with it, but you can never do better than with a completely connected network. Why is
completely connected? What do you mean by completely connected?
There's an arc from every variable to
every other one.
Yeah. So, but remember, you can't allow edges, right? So what this would mean here is something like this. Let me do it graphically, right? Let me just draw the nodes in a line, right? So what is a completely connected legal Bayesian network, right? Is, let's say, this is x1, x2, etc., xn, right? x1 is a parent of x2, right? And so let's do this the other way, right? So x2 has x1 as a parent, and then x3 has x2 and x1 as a parent, right? And then x4 has all of them, right? And then finally xn, all of the preceding ones. So the idea is that each variable has all the preceding ones as parents. Right? Meaning the Bayesian network didn't buy you anything. This is just your banal application of the chain rule. But this is what you want to avoid like the plague, because inference here is going to be impossible, and also learning is also going to be impossible, unless it's a very small network, right? So my question is, why is this the maximum likelihood, or to be precise, why is this guaranteed to be a maximum likelihood network?
Because any smaller network you could represent like this by putting 0 entries in your tables.
Exactly. So imagine the real network that generated this data, right? The real network that generated this data has some arcs somewhere, but doesn't have arcs in other places, right? And if I'm missing one of those arcs, then I'm in trouble, because there's a dependence that I can't represent, and I lose likelihood because of that, right? There's a correlation, and the variables look like this, but I'm not able to model that. Okay? But if what I do is add spurious arcs, right? Those spurious arcs don't reduce my ability to model what's going on. They just mean that there's going to be duplicate entries in the tables, right? If there's, for example, if there's, let's say that x3, should only depend on x2, but I've also put in x1, right? What that means is I'm going to have the same entries for the table for x1 and not x1 for each value of x2, which is terrible, right? But it's still a maximum likelihood model, right? So, did everybody follow this? So doing maximum likelihood learning for parameter estimation is already problematic, right? This is why we do things like Laplace estimates and M estimates, right? To make sure that small counts don't make things unstable. But for learning structure, it's a much worse idea, right? So learning structure using likelihood is a terrible idea. So what do we use instead of likelihood? Think back to the very beginning of, this part of the class when we started studying, Bayesian learning, right? We saw that maximum likelihood learning is actually a special case of what? MAP, right? You remember the acronym, but can you remember the content? Hey, remember the acronym is the first step, right? So what is MAP learning?
You weight your hypothesis.
Prior probabilities were.
Exactly. I pick my hypothesis that has the greatest what?
Prior.
Not just prior, remember, Bayes' theorem, there's the prior and there's the likelihood, right? And when I do the product of both of them, what do I get? The posterior probability, right? Which is the probability after I see the data, which is a combination of how much I believed in the hypothesis before seeing the data and the likelihood, okay? Well, this seems like a good thing to use here, right? And the way you avoid overfitting is by having, a good prior, right? As always in machine learning, you can't escape the need for some knowledge, right? So what might be a good prior? Or you can also answer the following slightly different question. What do you think is a prior that people commonly use, or a type of prior that people commonly use? Uniform prior, bad idea, because what? Why is that a bad idea? What happens if I'm doing MAP learning with a uniform prior? This becomes equivalent to what? Maximum likelihood, right? So that's probably not the answer. So what might a non-uniform prior be? Let me give you a powerful hint, right? I don't want to learn a Bayesian network with a lot of edges, right? Edges are costly both for learning and for inference, right? So what do I want my prior to do?
Number of edges.
Yeah, I want my prior to prefer networks with fewer edges. Right? The idea here is that I will put in an edge grudgingly if the data tells me it's there. But that means that it has to clearly be there. If it just might be there or not, nah. So what I can do is I can have a penalty on the number of arcs in the network. Or let's say in the number of parameters, some sort of complexity penalty. Right? Let's say an exponential penalty. Right? And so what that means is when I take the log and sum, right? Remember, it's always good to do that. What I have is a constant penalty per edge, right? And I have the log likelihood term. And now what has to happen is that when I'm considering adding an edge, the log likelihood has to increase by more than my edge penalty. If the penalty on my edge is lambda, and the likelihood goes up by less than lambda, then I say, nah, not worth it, not worth the trouble. If the edge penalty is lambda, but the likelihood goes up by more than lambda, well, then I'm willing to pay the price because it's probably a net gain. And of course, by tuning, this lambda parameter, right, I can go all the way from learning a very sparse network to learning in the limit, if my lambda is 0, the maximum likelihood one. Okay? So this lambda is the parameter that you probably want to tune by cross-validation. Okay? Now, this is one option for a prior, and this is the lazy option, and we have lazy tendencies in machine learning, so this is very widely used, right? But what might be another option? Let's say that you actually know stuff about this problem, right? You are trying to learn a network for you're a park ranger, right? And you're trying to learn a vision network to predict forest fires, right? And you've decided that these are the important nodes, right? And you're a park ranger, you know a lot of stuff about forest fires, right? Do you really just want to use a prior that just says you prefer smaller networks? Are you that lazy? Right, what might you do?
Draw one.
Draw one, exactly. This is actually one of the greatest beauties of learning Bayesian networks, is that it provides a wonderful way for you to put in your knowledge. The way you put in your knowledge is you draw a Bayesian network. Now, when we were not learning the structure of the Bayesian network, the problem was that structure that you put in, you were stuck with it forever. And people are often good at kind of figuring out who depends on who, but they're not perfect, right? They can be off, right? They can miss things, they can get things wrong, right? The ideal thing that you want to do is you want to be able to put your knowledge into the initial Bayesian network, right? This is your best shot at what's going to happen in that domain. But then you should allow the data to say like, hey, there's this arc here that's missing. The data tells me that there should be an arc here. I'm going to put it in. Or the data could also say, you put in this arc, but I don't see it. So let me take it out, right? Which means that you need a new operator, right? In addition to having an operator that adds an edge, if you're going to start with a Bayesian network that is not empty, you should also have an operator that deletes an edge. Okay? And then what you can have is a prior distribution that penalizes moving away from the initial network. So now what I can have is a penalty for every arc that is different from the initial network. If I add an arc, I pay lambda, but if I take out an arc, I also pay lambda. So again, the data can let me move away from my prior, the network that I believe in, but again, that data had better be strong, have strong evidence that the arc needs to change. And I can use my lambda to say how confident I am. If I really believe in that prior network, I have a very high penalty on changing edges. If I really don't have a lot of information, it's just like something that I drew quickly and I'm really not sure well, then the lambda can be low and the data can allow me to move away from that fairly easily. But even in that case, starting from that point is probably a very good idea, because again, we're in a very large search space full of local optima, so having a good initialization point that exploits your knowledge can be the difference between success and failure. Okay? So this is what you really should do, is put some thought into drawing your initial Bayesian network, or ask the expert, right? You can interview the expert and you guys together can draw a Bayesian network for the problem, right? This is the kind of thing that people do all the time. And then you go and use some data to refine that. There's one more operator that people often use besides adding an arc and deleting an arc. Can anybody guess what it might be?
Swapping ends.
Yeah. Well, swapping, I'm not sure what you mean by swapping, but here's how I choose to interpret that. It's taking an arc and reversing it. This turns out to be a very useful thing to do, because what often happens is that people put arcs in the right places, but they often put them in the wrong direction. Wrong direction means there isn't necessarily a wrong and the right direction, but they often put them in the direction that makes things harder from the point of view, of making the learning easy and the inference cheap and whatnot. Okay? So, and if you think about it, reversing an arc, right, is just the same thing as deleting one and then adding another one in the opposite direction, right? So why do we need this operator? Why can't we just have add and delete, right? Why is it useful to have reverse? It's actually a...
Less of a penalty, because you've got something there, it's just not the direction.
The problem is that when I take out, remember, these are two variables that are strongly correlated, right? That's why you put an arc between them. What happens if I take out the arc? What happens to the likelihood? it really goes down. Right? Because now I'm saying there is no dependence. And then I put it back in the other direction. But the problem is that to go from this likelihood to this somewhat higher likelihood, I'm going through, an intermediate stage that has a much lower likelihood, and that is bad, right? That is a barrier that's going to prevent you from doing that. So the reverse arc operator is really there to overcome the limitations of this greedy kind of search that we're doing, right? It's going to allow me in one step to jump from one peak to another higher peak without having to go through the valley in between, because the greedy search wouldn't do that. Okay? So at this point, see, we have all the pieces. So here's what we can do when we have a known structure. We have a search process. My initial state can be my empty network if I don't know anything about the domain or I just don't want to bother. Or it can be a prior network, right? That is often called the prior network, is the network that the experts design a priori. And then I have operators like adding, deleting, and reversing arcs. And then my evaluation function should be the posterior probability, not just the likelihood. And again, this posterior probability is going to have a prior probability that's going to penalize you for diverging from the initial network, right? Whether it's a network that you've designed or the empty network, right? If you think about it, this idea of penalizing, adding and removing arcs from the original network, it works just as well if the initial network is empty, right? In that case, it's just a penalty for adding arcs, so that doesn't even have to change. Okay. Now, there are many more variations of learning Bayesian network structure. It's a very active research area, but these are the basic ideas. Right? If you needed to implement a Bayesian network structure learning today, you could do it. Questions? Okay, so finally, what if both problems are present? What if I don't know the structure and I have missing values? Now this is the really hard one. What might you do in that case? Suggestions? Let us first not worry too much about computational efficiency, right? Let's just think of some scheme to do this. Right, we know how to learn with missing data, we use EM. We know how to learn with unknown structure, we do this kind of structure search with add and delete arc and whatnot. So how might we combine the two? What would you do, right? If you had let's suppose this is the final in the class and you have 5 minutes to come up with an algorithm for learning Bayesian networks with unknown structure and missing data. What would you do?
Both back and forth for a while?
Something like that, right? So you have to use some combination of EM and structure search, right? So how might you do that exactly?
By add an arch and then do the EM step until we converge, and then add another arch and see.
Yeah, exactly, right? So if we don't worry about computational cost, there is a fairly straightforward way to solve this, which is I'm doing my structure search, right? Adding arcs, deleting arcs, reversing them and whatnot. At any given point in this search, any one of my candidates, right, is a complete network, right? Now on this network, I need to find my maximum likelihood parameters in order to evaluate how good the network is, right? But now I'm just in the situation of known structure and missing data. So now for each candidate, I can do EM. Right, so for that candidate I do EM, I find its maximum likelihood parameters, and then I pick the best candidate, right? This is a perfectly workable algorithm. The problem, of course, is that this is not going to finish running before you get fired. So what might you do that might be faster? That's the interesting question. In fact, this is not, hey, if you can come up with the answer right now, kudos to you. But it took people a long time to figure out how to do this. And there's this thing called the structural EM algorithm. We're not going to go into its details here, but let me just mention to you that it exists. The structural EM algorithm is actually a very clever idea. Is that instead of putting EM inside of the structure search, right? This is what we just did here, right? We did the structure search, and then inside each step of structure search, we did EM. But this is very expensive, right? Because EM is expensive, and we can't do it at each step of structure search. The idea in structural EM, roughly speaking, is actually to turn things around. I'm going to put the structural learning inside the EM. How might that work? Well, how about this? I start out by doing EM on my initial network, right? And then what I do is I do some number of steps of structural learning, pretending that that filled-in data still applies, right? I have my filled-in data set with my estimates of the missing information, I just do some number of rounds of structural learning on that. Now what happens is that, of course, as I do more rounds, that data starts to be worse and worse. But at least for the first, say, half dozen iterations of this, that data is probably still more or less the same that it would be if you sort of like relearned it, right? So we can do that. I do EM, I do some number of iterations of structural learning, and then I do EM again. And the guy who came up with this algorithm, his name is Nir Friedman. The other thing that he did was actually to prove that if you do this, you still get the kind of convergence guarantees that you got with pure EM. Right? So this is a very smart idea. Right? Having said that, truth in advertising, structural EM, this algorithm is now, 10 years old or something like that. Not very old. EM was invented in 1977, so that qualifies as old by now, right? At least in, internet years. But the structural EM algorithm is about 10 years old or less than 15. But it's still not used that much because even with this trick, doing the combination of structure search and EM is still expensive, particularly if you have a large data set. And if you don't have a large data set, then maybe you don't have enough information to learn a very nice Bayesian network anyway. Okay? So, the story continues. Maybe there'll be better algorithms that people come up with in the future. There's other probabilistic representations that you can use besides Bayesian networks that we haven't talked about here. Right? So there's a lot of different things that you can do. Okay? Questions about Bayesian learning? So in these 3 + 1 hours, we've done a lot of stuff. Right? This, like I said, this is a very large area. We've only hit on the main things, but these are some of the most widely used, most important things in machine learning. Right? There's a lot of stuff out there that runs on Bayesian learning, like for example, spam filters, but that's only one example. Okay? So let's see. How about we take a break right now? Right? It's a little early, but this is a natural break in the lecture. Right? And after we come back, we will do neural networks. Okay, so it's 7:43 right now. So let us reconvene at 7:53. Sound good? All right. On to what is probably the funnest topic in this whole class, and that's neural networks. And the idea in neural networks is to use a very sound engineering principle, which is called reverse engineering the competition. Right? When you're far behind, the competition is a lot better than you are. The thing that you should do is not playlist, copy what they're doing. Right? If you can figure it out. Look under the hood, see how they built their engine and built an engine that's just like that one. And then you can start improving on it. In the case of machine learning, the competition that we're far behind is your brain. Your brain is a crackerjack machine learning algorithm. It really is amazing. Now there's domains for which your brain is not well suited, right? They have a lot of dimensions, and I'm trying to figure out a social network with, 1 billion people in it and whatnot. Well, your brain can only handle so much. But for the things that your brain can handle, like vision and manipulation and navigation and, speech understanding and, language understanding and common sense reasoning, your brain is the greatest learner there is. Okay? So the idea in neural networks is let's reverse engineer the brain, and let's build our machine learning algorithms that way, right? You can see why this might be fun. You can also see why this particular machine learning might be popular with the media. Right? Neural networks get a lot more press than Bayesian learning. It's just not fair, right? But it's just a lot sexier. What can you do, right? It's biology. It has to do with human psychology and behavior and whatnot, and people like it, right? So let's look at that. Right? And again, it's a very large and well-established family of machine learning algorithms, and something that you definitely want to know about. So we're going to start by just looking at the basic ideas in neural network learning. And then the first algorithm that we'll look at is also a very old one. It's the perceptron algorithm, classic neural network approach. It goes back to the 50s. But a lot of the ideas in perceptrons in different forms are still around today, so in many ways it's still current. On the other hand, it also has some very severe limitations. So the next thing that we're going to look at is called gradient descent. Gradient descent is a very, very widely used algorithm for learning, and actually not just for neural networks. Gradient descent is used for all sorts of things. So again, as we did in many other lectures, we're going to learn something here that is not just relevant to neural networks, but is going to be a tool in your toolkit for learning many different things. Okay? But then, the most powerful stuff is learning a perceptron is basically just an imitation of a single neuron. That is not very exciting at the end of the day, right? Your brain is not one neuron. Your brain is about 10 billion of them. Okay? So we want to figure out how to learn those networks that have many layers of networks, so-called multi-layered perceptrons on multi-layered networks. So then we look at those, we'll look at their representation, what it can do and what not, as usual. And then we will look at another famous machine learning algorithm, the backpropagation algorithm. Backpropagation is the most widely used algorithm for learning neural networks. And in some areas, it's still the algorithm of choice. Okay? It's, there's again many variations of it. We're just going to see the basic style of backpropagation, but enough that if you, needed to implement one tomorrow or to use an existing package, you would know how to do that. Okay? So, let us then reverse engineer the competition. Let us look under the hood, which means, slicing the cranium and opening it up and seeing what's under there, right? These days actually can do a lot of things that way. Not with people, right? Because there might be objections to that, but you can do it with mice, you can do it with monkeys, and literally there's people who for a living cut up brains and, take the slices and stain them to see where the neurons, are connected and whatnot. And there's also these things that you can do like fMRI studies and whatnot. So let us see what humans look like as a learning machine, as a learning algorithm, and how they compare with the kinds of things that we use, like, the latest CPU from Intel, right? How does a Pentium compare with a human brain, right? And the first thing that we're going to realize is that they are incredibly different. Even a cluster, your own favorite distributed computing blah blah, is very different from the human brain. And maybe there's a hint in those differences. And we can also see how human and machine learning stack up just in terms of the hardware before we even start thinking of the software. Actually, in the case of the brain, it's often called the wetware, right? Because you can't really call the brain hardware because it's not hard, right? It's kind of squishy and fluid, right? But it's smart, right? It might not look pretty, but that thing works, right? It's what you're learning this class with right now, right? So let's look at neurons, right? The neurons are the cells that your brain is made of, right? Your brain is basically composed of 10 to 100 billion neurons. That's a lot, right? It's a good chunk of you, is the neurons in your brain. What is the switching time of a neuron, right? How fast can a neuron switch? And there's some very interesting analogies between which we will get into shortly, between neurons and computational devices like transistors. Maybe it's not a coincidence, but one of the things that a neuron does is, it switches on and off, just like a transistor in a digital regime does. Okay? But there's a very big difference, which is the following. Transistors, they switch on and off at a speed of gigahertz. Right? That's what you have in your PC. The switching time for a neuron is a joke. It's a joke. It's about 1 millisecond. Meaning a neuron can turn on and off about 1,000 times a second. Compared to a transistor, in an ordinary, run-of-the-mill chip, that can do it about 1 billion times, or several billion these days, right? So this is good news for us, right? This means that right off the bat, we have an advantage over the human brain of, about 1 million, 6 orders of magnitude, right? So, we're, out of the gate, we're looking pretty good, right? Human neurons are pretty darn slow. But now let's look at the next thing, right? The number of neurons. This is an interesting one because it used to be the case, right, for most of the history of machine learning and AI, that we couldn't compete with that. Right? A brain, let's say that we stay with this rough equivalence or analogy between neurons and transistors, which is not entirely fair because a neuron is somewhat more sophisticated than a transistor. But, let's stay with that. How many neurons do you have in the brain versus how many neurons do you have in even a supercomputer, versus how many transistors do you have on a chip, right? It used to be that the number of neurons in the brain was way larger than the number of transistors that you were computing with, right? In the beginning there was 1 transistor, right, and then there was 1,000, and then there was 1,000,000. These days, right, we're actually at the point, we're at this historic crossover point, where we now have more transistors than there are neurons in the brain. Right? You can debate exactly where the crossing point is, but roughly speaking, it's within this decade that the number of transistors that we have on either a processor or multi-core, right? You can slice this any way you want. But bottom line, 10 years ago, there were more neurons than transistors, except for very heavy, supercomputers. And, after this, in the future, we'll have many more transistors than neurons. So this one used to be, a win for the human brain, but these days, it's either a wash or, the transistors are, getting an edge. And of course, the thing is that, the human brain is not evolving, at least not that fast, right? So, with this one, things also look pretty good for machine learning compared with the competition. But now let's look at another one. How many connections does each neuron have? Meaning, how many other neurons is each neuron in the brain connected to on average? Versus how many transistors is each transistor in the chip connected to on average on, say, a Pentium? I don't know the exact number for transistors, but I'm going to guess it's on the order of 10. Right? Connections are very expensive. Okay? You need a topology that works in 2D. These days you even have multiple layers, but you can only do so much, right? So, the number of connections per transistor is pretty low, right? Because it's hard to do, chips with a lot of connections per transistor. Right? So let's call it 10, right? The number of connections per neuron is on the order of 10,000 to 100,000. This is something that no chip can do today. It's completely beyond what we can do. In fact, with semiconductor technology of the type that's available today, or that we can foresee in the future, this is never going to happen. Never. Maybe with other fancier things, with quantum computers or optical computing or who knows, right? Maybe we'll find some way to do this. But right now, we're nowhere close to matching the brain, and we don't see how to match it. And fortunately for us, these connections is where all the action is. In fact, neural networks are often also called connectionist models, because they're all about the connections. And when it comes to connections, the human brain is still winning. The human brain has a lot more connections than any computer. By the way, there's another one, just to digress for a second, which is becoming increasingly relevant, which is, what? Can you think of another, not apropos of machine learning, but can you think of another engineering dimension where the brain just kills computers? Yeah, power consumption. We are now at the point, so here's the thing. If you look at all these dimensions, right? The number of neurons versus transistors is a wash. Computers really lose on the number of connections, but they really win on speed, right? So you put these two things together, right? And what you can do is you can multiplex connections on one line, right? I have only one physical, wire, but that physical wire can do the job of 10,000 by sending the signals one after another, right? It's called a bus, right? Amazing innovation, right? So when you look at the wash in one thing, the win on the other, the loss on the other, you could say that at this point, roughly, in terms of sheer computing power, computers are catching up with brains. And, in another 10 years, they will have left them behind. Does this mean that we no longer have any hardware problems to worry about? Not at all. Because the power consumption of the human brain, for all the amazing stuff that it does, right? Your brain really is a super duper computer, right? And its power consumption is about the same as like one ordinary light bulb. I forget the exact number, but it's on the order of 100 watts. An equivalent computer with the same rough power in terms of number of operations that it can do per second, you know what its power consumption is? You don't want to know. It takes a power station to power it, and then you have to cool it, which takes even more power, right? This is what these data centers are about, right? Think of the power that goes into one of the data centers that companies like Microsoft and Google and Amazon have today, right? That thing is a power monster. And your brain is doing the same thing with 60 watts. Isn't that shocking? So, there's some technology hurdles to be overcome, but for the moment, let's just look at the software side of things, right? So, what happens when you walk down the street and suddenly recognize your grandmother, right? Grandmothers are very popular in neuroscience for some reason. People talk about your grandmother's cell, right? You have a cell that recognizes your grandmother, right? So, this is an important paradigmatic example is, what does it take to recognize your grandmother? And of course, the other thing is that computers can't recognize their grandmothers well because they don't have any. But even if they did, right, they wouldn't be able to do it as well as you do. And the thing is that, like, people can do these experiments. You can recognize, between the time when the image of your grandmother hits your retina and when you say, like, oh, hi, right? This is about 1/10 of a second. In 1/10 of a second, you can take a visual scene, whether it's your grandmother or your office or, the subway station or whatever, and you figure out what's there. And now if you think about it, right, here's the interesting contrast is your neuron can switch 1,000 times per second. And yet in 1/10 of a second, your visual system has done its job. How is that possible, right? You only have about 100 steps. 100 steps of inference. We don't know how to write a program to do that in any number of steps, let alone in 100 steps, right? We have no idea how to do it in 100 steps. So how does the human brain manage this? Well, of course, the answer is massive parallelism. It's 100 steps, but in each one of those 100 steps, there's this, truckload of neurons all getting connections and signals and sending signals and whatnot. So in each one of those steps, there's a lot of stuff happening in parallel. And in fact, it's not a coincidence that neural networks initially became popular in the 80s when parallel processing was a big deal for a while. And then, of course, Moore's law killed parallel processing, for another, 20 years, right? Because, things got faster and parallel processing is hard. These days, of course, parallel processing has come back, in a big way and to stay. Because Moore's law has run out of breath and now we have no choice but to do parallel processing. But neural networks became popular in the 80s partly because they are sort of like a naturally parallel paradigm for processing. Okay? So the whole game here is we're going to do things using connections and using processing of a lot of things at the same time. Now, the actual algorithms that we're going to talk about here, they're sequential, right? But they're really sequential algorithms that are emulating something happening in parallel. So in terms of our mental model of things, right, we can think of things running in parallel. Okay? So, a neural network has many switching units, right? This is what they do. They switch on and off. They're neurons. We're going to see shortly what a neuron is like. And the game that we're going to play is we're going to try to build a mathematical model of how a neuron works. And, there's people who just do that for a living, like, actual neuroscientists. And they build incredibly elaborate models of how neurons work. This is not what we want. Right? We don't want to be faithful to how your neuron does things. If the goal was to cure Alzheimer's or whatever, sure. But our goal here is, to reverse engineer the computation. So we want to have the simplest model of a neuron that could possibly do the job. Okay, so that's what we're going to do. The absolute simplest imaginable model of the neuron. And then we're going to, figure out how to learn and how to connect them up and whatnot. Right? So the second important thing is that these switching units have many interconnections about them. And this is where the learning is going to go. Your memory, to the best of our knowledge, is contained in the strength of the connections between your neurons. If I reset the connections between all your neurons, you would not only suffer from amnesia, you wouldn't know how to do anything anymore. You would go back to crawling. Right? So everything that you are and know is encoded in the strength of the connections between your neurons. And again, people in neuroscience have even largely figured out what are the chemical mechanisms by which this happens and whatnot. There's still a lot more to do, but that's the kind of thing for which you win Nobel Prizes in medicine and whatnot. The next thing is that this is going to be a highly parallel distributed process, right? There's computation happening in many things at once, and then they all communicate, and that's how we manage to get results very quickly, even if the individual units are pretty slow. Okay? And the learning is going to happen by automatically tuning the weights between these units in response to data. And this is the other reason why these models are called connectionist, is that this is where the learning is. It's in the strength of the connections. And so what we're going to do is we're going to have these very simple models of neurons. We're going to hook them up, and we're going to figure out how to tune the weights to remember what you've seen and generalize from it to new cases. Okay, so that's the rough plan here. Okay? Any questions so far? All right. So here's a famous example of neural networks at work. You've all heard of the DARPA Grand Challenge and the self-driving cars, right? There was this team from Stanford that won the competition, right? And that car is now in the Smithsonian and whatnot, right? It's a Volkswagen, right? Which is kind of ironic, but anyway. Right? Now, there's some folks at Carnegie Mellon who are very bitter about this. You know why? Actually, there's two sets of folks at Carnegie Mellon who are bitter about this. They're the ones who came in second, right? But before you even think about those folks, there's another set of folks who actually built what is, as far as I know, the first self-driving car. Right? Before this whole DARPA challenge and whatnot, there was already cars that could drive themselves. They were just not as famous. And this was a project called Alvin that happened at Carnegie Mellon in the, I'm going to say, early 90s. It went on for a while, so, started maybe late 80s, early 90s, mid 90s. Alvin is short for Autonomous Land Vehicle in a Neural Network. Right? It's always fun to have these acronyms, right? You get all this scientific credibility if you can come up with a good acronym. So, what did Alvin do? The first versions of Alvin, and I remember seeing videos of this, they were these trucks, like those bank trucks that shift cash around that are armored and are huge and heavy. That's what Alvin was. It was like one of these trucks filled with hardware. And then you know what Alvin did? This is not a joke. It computed for, half an hour, and then it moved forward a few inches. And then it computed for another half hour and moved forward another few inches. And I was like, oh, I have to start turning. Not very exciting. They made it exciting by speeding up the video, right? Always a good thing to do if your hardware is not quite where you want it to be. Nevertheless, right, this is where things begin, right? They look like a joke with the current hardware. Right? It's like the first laser printer, right? It was huge, it belched smoke, it didn't look serious. But you have to squint at that and see what it's going to become once the hardware has progressed. And indeed, within half a dozen years, Alvin had progressed to being what you see here. This is just, an ordinary car, right? The photo, unfortunately, is a little grainy. There's actually a video of this that you can watch. It's kind of fun, but, the elements of it are here, right? And so that big truck has become an ordinary car, and that big pile of hardware inside it has become a laptop. Right? Do you notice something a little odd about this picture? Something odd and disturbing? The thing that's odd and disturbing is that the driver doesn't have his hands on the wheel. This car is on the freeway. Right? But the hand is off the wheel. In fact, one of the things that this video has is it's the car driving down the highway and the driver's hands are outside. Both of them are, outside the window going like this, right? If I was on that freeway, I might swerve, right? So they were, they had some potential liability issues there, but. So, and the other thing that this car has, right, is this video camera pointing at the road. And that's it. This video camera is connected to the laptop, and then the laptop is actuating the steering wheel. And there's also some, there's the accelerator and like the brake and whatnot. But let's just focus on the key parts of this, right? This is the whole thing, right? And this car actually drove their goal. This is maybe why they did not become famous, right? This is how history gets made or doesn't get made. Their plan, once they had this thing ready, and we'll see in a little bit how they got it ready using machine learning and neural networks, was to have the car drive itself from coast to coast. Right? Coast to coast, with no human help. And they almost succeeded, but there were just 3 or 4 intersections or something where, the human did have to intervene. And therefore, they do not have their place in the Guinness Book, right? Big bummer. But really, if you think about it, if this car can drive coast to coast except for a few things, right? And by the way, the big difficulty for them was actually not your basic driving, which they totally aced with the neural network and then other things that they did after. It was what's called tactical driving. Right? Tactical driving is like, when do I change lanes, and is that car in front of me going to change lanes, right? And then they actually went on to build learning algorithms for that as well. Okay? But the amazing thing is, they have a neural network learning to drive the car. You know how the neural network learned to drive the car? This is like your quintessential machine learning. They just trained the network by having the camera on and having the network record what the driver was doing with the steering wheel as they drove through various kinds of roads and various kinds of lighting and whatnot, right? So the way they put together the training set for this was kind of fun, was by, driving around the country, or, around Pittsburgh probably. This is what they did, yeah.
Did the camera, learn to recognize like stoplights and stuff? Did it?
So, very good. It did not, right? So, what I'm going to show you here is just the basic version of things. The full-blown system recognized a lot of stuff and the tactical driving and whatnot, right? So, but what I would like to impress you with is how well and how, in some sense, easily this thing learned to just do the basic driving, which is, stay on the road and keep going forward, and curve when there's a curve and whatnot, right? And mostly they were, of course, driving on highways, trying to stay away from, urban traffic and whatnot, right? So how did this happen? Here's what they were doing. The first shocking thing that they did, and you have to remember this was the early 90s or the late 80s, was they took the output of the video camera and they down-resolved it to 30 by 32 pixels. Now the DMV wouldn't let you drive if your sight was that bad, right? This is someone who needs really, really thick glasses. But they just wanted to reduce the computational load. So they down-resolved the image to just having here it is. We'll see in a little bit what this image is, right? But this is the number of pixels that you have, right? So you have a driver that can barely see the road, right? But that's the input, right? Each training example is one frame of the video, okay? What is the output? The output is, it's a continuous variable, which is the angle that, the steering wheel was turned to, right? And this was discretized, into like sharp left, medium left, straight ahead, sharp right, soft right, and so on and so forth. Okay, I forget how many they had. Oh, so there's 30. Okay. So the output is basically 30 things, right? 0 is sharp left, 15 is straight ahead, 30 is sharp right. Okay. And then all the neural network learned to do was correlate this input with this output. That's all that it learned to do. Now, the most disturbing part of all of this hasn't come yet. It's not that this is all that they were learning from, and that, the image was down-resolved to a point where, the system was functionally blind if it had been a human. It's that, what size brain this thing had? Maybe this is how people can drive while drunk, right? But the size of the brain of this thing was 4 hidden units. What do I mean by 4 hidden units? Each unit is an emulation of a neuron, as we will see shortly, right? So they have these 30 units, right? One of these units fires when you want to go straight ahead. One of them fires when you want to make a sharp right, and so on and so forth, right? So they had those 30 output units. But the only other part of the neural network was this layer called a hidden layer, because it's neither the input nor the output. It's standing between them, so you can't see it from either the input or the output. And the hidden layer only had 4 neurons. So essentially, this thing had the brain with 4 neurons in it. Compared with your 10 billion. Even a flatworm, right? Which is, the flatworm is famous in neuroscience because it's got a brain with only 300 neurons, and people have actually reverse engineered it exactly. They know exactly how the brain of the flatworm works. Like there's this, Kandel, like this famous neuroscientist who got the Nobel Prize for this. And by the way, even that, people don't actually know how it works. They've got the neural network, but they haven't figured out how that works, right? Because, like, say, if you're trying to reverse engineer television, right, even if you have the circuit in front of you, you don't necessarily understand what it's doing. So, we need some deeper notions. But in any case, compared to that platform, this network is very stupid. It only has 4 neurons in it, and yet it works. How does it work? Right? How can it do this? Right? Think of it for just a second. You have this thing with a very coarse retina, right? The input is often called the retina by analogy with the eye. It has a very coarse retina. It has a very tiny brain. All it did was watch a human driver drive around various highways and country roads and whatnot, and it figured out how to drive. So how do you think it did this? Well, here's the answer. What we have here is, for one of these 4 hidden units, the connections from the input and the connections to the output. And the convention here is that light, meaning close to white, means a strong positive connection. Gray means a weak connection, no connection or a low weight. And black means a strong negative connection. Right? Negative connection means if that input is on, that tends to make that unit be off. Okay? So first of all, can you guess what this unit is responsible for just by looking at its output? What does it do? So these are the strengths of its connections to the output units. Right? So when this unit is firing, what do you think the car does? Turns left, right? Because it's got big weights here and actually negative weights there and kind of gray weights over here, right? So this unit has basically learned to fire when you're supposed to turn left. Okay? And now there's only 4 units, but they actually have continuous output, and if you combine the shades of them, you can get all 30 outputs. Okay? So there's some redundancy built into this, but that's often a good thing in a neural network, just as in your brain. Okay? But here's the most interesting part. Can you figure out by looking at this square how this unit has figured out when you should turn left? What's going on here?
More whites on the lens.
Right, so there's this white stuff here, right? This is the main thing that's happening here, is like there's this band of white and there's this band of black there, right? And what is that band of white doing? It's curving to the left, right? So this thing is just detecting that the road is turning left by looking at the median and the berms. This is actually what this neural network knows how to do. It knows to, detect the median and the edge and the berms, or one of them, right? Again, this is all neural, right? So it's like these things are not necessarily very definite, right? And it's detecting that the median and or the berms are kind of turning left, and therefore the wheel should turn left as well. And this is what it's doing. And it learned to do this by basically just watching somebody drive. Now, once you see what's going on, it actually becomes plausible that you would be able to learn this from data, right? I would not have predicted actually that just by learning this from data, you could actually learn to drive as well as this thing did, but hey, right? If you think about it, that's probably also what you do when you're not paying a lot of attention, right? When you're falling asleep driving, but you don't actually go off the road. The reason is that your conscious mind is not awake, but there's actually part of your brain that is awake. And that, that part of your brain, this low levels, sensory motor processing, it may not be aware of everything in the world, but it probably is aware of things like this. Oh, the road is turning left, so, maybe you should turn left as well. Okay, so this is a famous example of what neural networks can do. Okay, but now, of course, the question that we want to answer is like, how do we actually do this, right? Hopefully at this point it's plausible to you that we could do this, but the rest of this class and part of the next one is going to be how can we actually do this? Okay. Questions? Yeah.
So the output from those units is a continuous output, right? It's not binary. So there could be a lot going on within those units.
But we're going to see, so we're going to start by looking at binary units, and then we're going to see what's good and bad about them. And these things actually have what are called sigmoid units, which is a unit with the output curve is something like this. This is X and this is Y. Right? So, and it's quite remarkable. This is also the transfer curve of a transistor. Right? If you happen to know some electronics, right? And what happens with transistors is that on a digital computer, they operate between here and here. So they jump from 0 to 1 and back. However, the very same types of transistors can be used, at least in some cases, can be used as in the linear region, which is this region here in the middle. And that's what's used in your audio amplifiers and whatnot. Okay? So the interesting thing about the sigmoid curve is that it can both work as a linear unit or as a switching unit, as in a computer, in the same piece of wetware. Okay? So the brain is actually doing a mix of analog and digital computing, and this is part of the reason is that it has this transfer curve. And transistors also have that, which is quite remarkable, but somehow in what we've built so far, we either go purely for the analog or purely for the digital. There's some people, though, who say that we should bring them back. So what is being used here, in this case, and we will see that later, is a continuous output, but is a continuous output of this form, which a lot of the time ends up just being 0, 1. Okay? So that's a good question. More questions? Okay. So, how are we going to do this? Well, first of all, let's look at what a neuron is. right? And then let's look at how we can build a mathematical model of the neuron, right? This is how we reverse engineer the competition. A neuron is a very interesting object. I don't know how familiar you guys are with any of this, maybe a lot, maybe not very, but let's look at it because it's quite interesting. So a neuron, is a nice little cell with a cell body and the cell nucleus, just like other cells in the body. But that's where the similarity ends. A neuron actually, you know what a neuron looks like when you look at it under a microscope? It looks like a tree, like a very, very bushy tree. Like trees, it has a trunk. So this is the cell body. And the trunk is called the axon. It's got like this long, thin projection coming out of it. And then it has roots. They really do look like roots. It's probably even the same, genetic thing that's doing that type of growth, if I had to guess, right? So it has a lot of roots. Does anybody know what these roots are called? They're called dendrites. And then, of course, the tree trunk branches into a lot of branches, right? So here they are. And these branches are also called dendrites. So, this does look kind of like a tree, right? But now here's the next thing, right? Does the brain look like a forest? If it looks like a forest, it's like the biggest nightmare forest you've ever seen. It's like something out of a horror movie. You know how when, our protagonists get lost in a thick, threatening jungle? That thick, threatening jungle is nothing compared to what the brain looks like. You know why? Because the trees are not all, sort of like with their roots on the ground and their branches up in the air. These dendrites connect with the dendrites of other neurons. Right? So where this tree has its branches, another tree has its roots. And this is how you get like these really dense, intricate connections, right? Clearly there's something really powerful going on there. So how does a neuron work? Here's what happens. And by the way, the brain works on electricity. Right? These axons are literally electrical wires. And in fact, they even have, insulation. They have these things that are called myelin sheaths. That's like your copper conductor having, its little plastic, tube around it to keep it insulated. The short-range ones actually don't have it, but the long-range ones have to have it, otherwise the signal gets lost. So what happens in the axons is that the neurons, and now we're getting into the things that we're going to want to model, the neurons basically send bolts of lightning down them. They send like these electrical impulses. The electrical impulses are called action potentials. Because it really is a potential. It's a voltage of, like point something volts that gets shot down the axon. And so, the potential travels along this, and it's not very fast, which is part of why, neurons are not so fast, right? And it goes to the dendrites, right? And then there's this crucial thing that happens, is that where the dendrite from one neuron ends and another one begins, that connection is called a synapse. So a synapse is a connection between an outgoing dendrite from one neuron and an incoming dendrite from another. And synapses are where everything happens. All your memory, all your intelligence, everything is based on what happens in the synapses. There's a gap here. So the transmission across the synapse is actually not electrical, it's chemical. Another reason why it's not so fast. Because what happens is that this signal causes a release of what are called neurotransmitters, which are basically, chemicals. They diffuse over to the other side, again, not blindingly fast. And then on this other side, what happens is that you get a signal that now gets sent to the next neuron. And so what the neuron is doing at each point in time is there are all these signals coming in, right? Some of its dendrites are dormant. The axons, of the other neurons that are connected, that they're not firing, there's nothing happening. But on some of them, there is something happening. But most of the time, you have this chatter at your inputs and you're asleep. But then what happens is that if that chatter gets above a certain threshold, suddenly the neuron flips. It goes from a potential like this to a potential like this. It's a nonlinear process. It's a switching event. It's just like a transistor. It switches from being off to being on. Right? It's not an analog, continuous, discrete, whatever. It's like you're off or you're on. When you're on, there's a flash of electricity going down that axon. Okay? So if the summed input exceeds a threshold, then you fire. This is what a neuron is basically doing. Okay? Now the other very important piece of this is, well, but how strong is the connection? That is the key. This synapse could be weak, medium, or strong. If the synapse is weak, what that means is that when the signal comes in, it creates a signal in the next neuron, but it's probably a weak signal. But if the synapse is strong, then a strong signal coming in also creates a strong signal going out. So some neurons are much more efficient at firing some of their neighbors than others. They are not all equal. And what makes connections be strong or weak? It's your experience. This, according to our best understanding of neurobiology, is where all your learning and memory occur. It's that things that fire together, wire together. This is the famous expression. Fire together, wire together. Meaning, if this neuron made this neuron fire, then their connection gets stronger. How exactly this happens? People have pretty good ideas. Now there's this thing called long-term potentiation. There's still a lot to be understood. But for our purposes, it's pretty clear that this is the mechanism. It's that when two neurons fire together, the connection between them gets stronger. And this is what drives your learning. And if you think about it from a statistical point of view, this makes a lot of sense, right? Because if they fire at the same time, this means that they're correlated, right? Which means that next time that you see one of them firing, then maybe the other one should be firing as well, right? So this is what happens. Okay? So that was your 5 minutes of biology. Any questions about any of this? As you can tell, I'm not an expert in biology, but hey, I just ad-libbed some of it. For our purposes, this is good enough. I did not knowingly say anything incorrect, let me put it that way. Any questions? Okay, very good. So that was the fun part. And now comes the math. Truth in advertising. Neural networks are kind of the machine learning version of a bait and switch. You know what bait and switch is? Have you ever heard that expression? Bait and switch is when your local, whatever, Nordstrom or Macy's says, hey, we have designer jeans on sale. It's a $200 pair of jeans and we're selling it to you for $50 this weekend. Come in this weekend. And you go there, right? You've probably seen this happen, right? To get your designer jeans at $50 and they say like, oh, we've run out of them. But we do have our store brand that normally costs $100 and we'll sell it to you for $40. Now, you would have never left home to go buy that pair of, store brand jeans for $40. You left home to get the designer jeans for $50. But here's the essence of the bait and switch is that once you're there, it's like, well, you don't want to have gone there for nothing, so you buy the store brand for $40. Right? So the designer jeans were the bait, and then the switch is the store brand. Okay? This is actually a very important concept in data mining, by the way. If you want to do data mining applied to retail, you want to know about these things. Right? To design better bait and switch and whatnot, right? Maybe that's evil, but maybe it earns you a living, so we shouldn't judge. And on that theme, we're going to do, I'm telling you, I'm warning you in advance that I'm doing a bait and switch right here. The bait is the biology. This is how the brain works, massive parallelism, connections, synapses, and then the switch is math. Calculus, gradient descent, derivatives. Okay, so at least I'm honest about it. You had your 10 minutes of fun, and now the rest of the class is going to be a lot of math. But hopefully, right, we motivated you for the math, with this introduction. Okay? But this is the irony, right, is that like when you look at machine learning in the press and why neural networks are powerful, it's because of the analog with the biology. But the truth in advertising is that at the end of the day, when you look at current neural network algorithms, there's many ways in which they do not look like what the brain does. In some ways they do, and they are based on notions of how neurons work and whatnot. But when you look, for example, at the structure of the neural networks that people use for machine learning applications today, and the structure of the brain, they look very, very different. And part of the reason is that nobody knows what the structure of the brain is. We're still trying to figure that out, and it's going to take a while. And the other reason is that even if we knew what the structure was, we still wouldn't know how to get it to learn. Nobody in machine learning today actually knows how to make, neural networks with the same depth and extent of connections of the brain and make that work. We know how to make more modest neural networks, maybe more on the level of a tapeworm. So that's what we're going to see here. The good news, though, is that even the brain of a tapeworm is enough to do really good things in the stock market, make you rich, robot control. One of the earliest applications of machine learning, sort of like the modern era, was to finance. And the tool of choice there was backpropagation, one of the elements that we're going to look at here. So even this thing that is a very far cry from what the brain does is already enough to do very, very well on a lot of important problems. And that's why we're going to study it here. Okay? So with that preamble, let us take our first, very simplest model that we can of how a neuron works and see what we can do with that. Okay? So what I'm going to do is I'm going to take that picture of the cell that I just drew and try to turn it into, a nice little set of equations about how neurons work, right? And then we're going to try to see what learning we can do with that, okay? So here's how it goes. You see the summation sign here? This summation sign is the cell body. And these lines here are my dendrites. And these X's are my inputs. They could be inputs from other neurons, or they could just be, the retina, right? Which in our terms means like it's a pixel from your camera, or whatever, attributes you're trying to use for prediction, okay? And then this thing here is the axon. This nonlinearity here is whether there's an action potential or not. So the way we're going to model this is my body, my cell body and dendrites is just going to be a weighted sum of the inputs. Very, very simple. You see, this is sum over all my inputs of the input times its weight. Nothing could be simpler. But you see how this is the parallel of what the dendrites are doing, right? And the strength of the synapse is this weight W, and it's this weight that we're going to try to learn. Our entire action is going to be learning these weights. This is what we're going to be talking about for the next, 3 hours between this week and next. Okay? And then this here is just a nonlinearity. So let's start with the simplest one that we can, and one that, to some degree models fairly accurately what the brain does, which is it's just a step function, right? A Heaviside function for those of you with some electrical engineering background, right? So this just says that the output is 1 if my sum is greater than 0 and minus 1 otherwise. Okay? We could also do this between 0 and 1, but it's more convenient to use minus 1 and 1, and empirically things tend to work better when you have minus 1 and 1 instead of 0 and 1. And there's also, reasonable understanding of why that's the case. So we're going to use minus 1 and 1 here because it's the best, but it could be 0 and 1 as well. Okay? So each of these inputs has a value has a value minus 1 or 1, and then the output also has a value minus 1 or 1. If the summed inputs with their weight, if the weighted sum of the inputs is greater than 0, then we fire. Otherwise, we don't. Okay? Now, should 0 really be the threshold? Actually, no. Right? It's not when the summed input exceeds 0 that you fire. But this is where another little trick comes in, which is the following. You see this unit here, x0, this input, x0 is always set to 1. Right? The others can vary, but x0 is forever set to 1. Which means that the weight W0 acts as, it acts as a threshold. Right, so I can, and this is going to be very convenient for us as we'll see, is that I don't actually have to worry about a threshold. The threshold is just the weight of this unit that is always on. And the reason that's very convenient is that it now allows me to express this weighted sum and the threshold as just a dot product and the threshold of 0. So this is good because now we can bring in, all our linear algebra that we know, and then we're going to do calculus over this and whatnot, right? But if you think about it, at the end of the day, what I'm doing here can just be summarized as the following. I do the dot product of my weight vector and my input vector. Everybody here remember what dot product is? If you don't, now's the time. It's a simple thing, but if you don't understand it, the rest of this is going to be confusing, right? So the dot product I write as w dot x, and w and x are vectors, and this is just a compact way of writing this thing that I had up here, okay? So w0, x0, except since x0 is always 1, I can get rid of it, right? That's the convenient part. Plus w1, x1, plus w1, xn. I'm just going to write compactly as w vector dot product x vector. Okay? And when that's greater than 0, we fire, meaning the output is 1. When that is less than 0, we don't fire, meaning the output is minus 1. Okay? That's it. This is our model of a neuron. This is the simplest model that will work because we need two key things to make this interesting. We need the nonlinearity. Right? At the end of the day, even if we're just trying to build a classifier, right, this thing has to decide whether it's your grandmother or not. Right? And we also need learnable weights. Right? If the weights are learnable, then, you know, if there are no weights, right, or if they're fixed, then we don't know how to learn. In fact, the first model of a neuron, very famous thing, was proposed in 1943 by two people called McCulloch and Pitts. It was a professor at MIT and his student. And, you know, they proposed the first, you know, you might call computational or mathematical model of a neuron. Nobody had done that before. People had studied neuroanatomy and physiology and whatnot, but they proposed the first model. This model did not have learnable weights. However, this model, this is something that most people don't know, was the world's first finite state machine. The thing that they actually defined as a model of the brain, you know, as a bunch of connected neurons, was the first finite state machine. And in fact, the finite state machines that are basically used to design every, you know, microprocessor these days, they are direct descendants of the finite state machine that these guys designed. So they invented finite state machines to model what the brain does, and today, you know, they are what's inside every computer. Coincidence? Probably not. In fact, the early computers were called electronic brains, because they really were brains. Now we've actually forgotten that. But, you know, when I want to annoy my colleagues in other subfields of computer science, I tell them that it's not AI that's a subfield of computer science, it's computer science that's a subfield of AI. Of course, you know, if you're in systems or, you know, networking or theory, you might not like to hear this, but, you know, there is some truth to it. Every little, you know, like, every gate in the computer is in some sense a rough model of a neuron. And again, we're going to see shortly how exactly the mapping happens between, say, an AND gate or an AND gate and the neuron. The big thing that they don't have, though, is the learnable weights. The learnable weights were introduced by a guy called Frank Rosenblatt in the 1950s, so roughly 10, 15 years later. And then he got really excited. He wrote this book called Perceptrons, very famous book, and he basically said, I've solved AI. I know how to build brains. I got it all figured out. I mean, there were a few more technical reasons why he said that. I'm not being entirely fair. But, you know, he got very, very excited. And then people discovered that there were a lot of very basic things that this couldn't do. And then for a while, neural networks died. There was this neural network winter. During the 70s, nobody was doing neural networks. There were a few diehards that kept at them. And then in the 80s, they exploded again when people figured out how to overcome some of the problems that had been pointed out before. And this really has to do with this issue of going from a single neuron, which Rosenblatt figured out how to do, how to learn with a single neuron, but that's very limited, to figuring out how to learn whole networks of them. And this is what multi-layer perceptrons are, and this is what the backpropagation algorithm does. Okay? But we're going to have to build up to that by starting with a simpler algorithm. Okay? And, you know, truth in advertising, for a lot of things, that simple algorithm is actually good enough. So, as usual, you should try that first before you go on to more complicated things like backprop. Okay? Questions so far? All right, so we have our model of a single neuron. Rosenblatt called this a perceptron because he was mainly using it for perception. It was a model of what, you know, the visual cortex did when it, you know, recognizes digits and whatnot. But now let us ask for this the same question that we've always been asking, which is, what can it represent, right? Before we worry about learning, let's see what this can represent, right? So what can a perceptron represent and what can it not represent, okay? So for example, let's say that, you know, starting with very simple things, let's say that the function that I'm trying to learn is just the AND of two inputs, right? Can the perceptron learn this? And the way to answer this question, right, is to figure out if there is a threshold and a set of weights that implements an AND, right? So what I want is a threshold and a set of weights, and, you know, you can think of the threshold as being minus weight 0, right? I want a threshold and a set of weights such that when both of my inputs are -1, the output is -1, right? When one of them is -1, the other one is 1, the output is still 1 because this is an AND, and it's only when both of them are 1 that you get the output being 1. Do you think you can do this with a perceptron? Or no? Right, remember, what the perceptron does is it accumulates weight, and once that passes the threshold, it says, yeah. So can we do an AND with that?
Yes.
Yeah, actually, it's very natural, right? So what we need, let's say we just make both of the weights 1, right? Let's not even worry about that, right? So both of the weights are 1. So now what is the threshold that works? And, to create this effect? Exactly. You need a threshold such that when one of them is, so when one input is -1 and the other one is 1, right? The sum of those is 0, right? So my threshold has to be above 0, right? Otherwise I would fire even when one of them was on or even when none of them was on. Okay? But now what happens if both of them are on? Then my value is 2, right? So when my sum input is 2, this thing has to be firing, right? So it can't fire when the summed input is 0, and it has to fire when the summed output is 2, right? So what values can it have? What can the threshold be? Well, actually it can be anything between 0 and 2, right? If you use a greater than or equal to convention, right, then it could actually be 2. But, let's just play it safe and make it 1, right? So if all of my weights are 1, if both of my weights are 1 and the threshold is 1, I've just implemented an AND using a perceptron, right? So a neuron can be an AND gate. What about an OR gate? Can a neuron be an OR gate?
Set the threshold to 1/2.
Exactly. It's that easy, right? All you have to do to make it an OR is lower the threshold. And in fact, now you can even do a lot richer things between, remember our good old friends, the M of N concepts? Right? You can implement an M of N concept with a neuron very easily. Notice the following: implementing an M of N concept with logic gates is actually very hard because you get an exponential number of terms, right? It's 3 out of 5. Well, you need to have terms for all the different 3 inputs that could be the ones that make you, be true at the output. With a neuron, that's actually easy, right? To implement an M of N concept, all that you have to do is put the threshold at M and give everybody a weight of 1. And now on top of that, you can even learn weights for these things, right? So in terms of representational power, the perceptron is roughly equivalent to something like naive Bayes. In fact, it's even better in some ways that we needn't worry about for now. Okay? So, hey, for one silly little unit like that, it's pretty impressive. But now, okay, this is the happy part of the story. What about something, can you think of something simple that a perceptron cannot learn? Here's a hint for you. Remember when I said, here's a function that's very hard for decision trees to learn, but it's going to be hard for other things as well? So if you want to know a machine learning person, bring this up. If you want to know a neural network person, this is golden. So what is that function? XOR, or parity, right? You go to a neural network aficionado, you mention XOR, and they start foaming at the mouth. So here's an XOR, right? Actually, let me do, let's say this is, -1, 1, x1, right? And 1, -1, x2, right? And actually, let me make these bigger so they're more legible, right? So my 2 pluses, right, are when the XOR is 1, right? Because one of them is on and the other one is off. And my minuses are when, the XOR is false, right? What is the problem with trying to learn this with a perceptron? Actually, let me contrast that with learning an AND, right? So here's my AND. In my AND, what happens is that these guys are all minuses, and I have a plus there, right? You agree? And let's put the OR here as well, right? What happens in an OR is that these guys are all pluses, and this one here is a minus, okay? So here's a nice machine learning problem for you, right? You have 2 positive examples of what you can learn, and 1 negative example of what you can't, and I want you to induce the rule for what is learnable and not learnable by a perceptron.
Draw a line that splits them into 2 groups.
Exactly. In these 2 cases, there's a straight line that splits them. And in this case, there isn't. You need 2 straight lines. And the perceptron can only do 1. Why can the perceptron only do 1 straight line? Can you tell me why? By looking at the map. But let's not worry about the threshold for just a second. Look at this function, right? This is a function, right? What kind of function is it? It's a linear function, right? And the frontier between positive and negative is going to be where this linear function is equal to 0, right? So it's a line. So a perceptron can only represent straight lines. Now it's better than the decision tree in some ways because the line can be in any direction, right? If you tweak the weights, the line will swing to any position that you want. But it's still just a straight line. So you cannot represent things as simple as an XOR. Now why exactly Rosenblatt got so excited, I'm not entirely sure. But then somebody had to point this out to him. I mean, in fairness to Rosenblatt, he was, if you look at his model of a perceptron, was that there would be some other inputs to it, they didn't come directly from the retina. So there was some machinery, in here that did some stuff, and then this got learned. So if that machinery was doing the right thing, then by learning some weights, then you have an XOR. But come on, this is a bit of a cop-out. I want to learn my XOR whole. I don't want to just learn, one part of it if you already give me the others. And the perceptron cannot do that. So more generally, right here we were in 2 dimensions and we had a line. More generally, when we were in n dimensions, which of course is an interesting case, what the perceptron can learn is hyperplanes. So if there's a hyperplane that separates your positive from your negative examples, the perceptron is a good candidate for that. If there isn't a hyperplane, if the surface is much more complicated, then perceptron is probably not a good idea. In particular, if you have something like an XOR, or more generally something with sort of like multiple separate islands of positive examples in a sea of negative or vice versa, the perceptron isn't going to give you that. Multi-layer perceptrons on backprop can at least in principle learn things like that, and then we will see examples of that and how it works. But for the moment, let's just stay with a simpler case and see, and use that, not just in its own right, but also to build up some of the ideas. Okay? And the perceptron is indeed a beautifully simple algorithm. Right? That's the other thing that's kind of exciting about it, is that it's very simple, and yet Rosenblatt was able to prove something interesting about it, which, as we saw in the case of nearest neighbor, can be very important. So there is the perceptron representation. That's what it can learn and what it can't learn. But now, how do we learn those weights? Right? This is the key question. How do we learn those weights? Well, here it is. It's just these 2 very simple formulas. And the first one almost doesn't say anything. So the way this works is as follows, right? This is very inspired by how people learn. I'm going to present the examples to you, one after another, right? And then what happens is that, so I initialize my weights to some small random values, like say your brain at birth, hypothetically, right? There aren't any strong connections there yet because, the baby hasn't seen any correlations yet, so you have small random connections. So the weights are like maybe values between -1 and 1, set uniformly or something like that. And then what you do is every time you see an example, the weight changes by some delta W, right? So what I do is my weight Wi, so this is the ith weight, the weight for the ith input. Remember, this is just one neuron. The weight for the ith input changes by delta Wi. Okay, Wi becomes Wi plus delta Wi. Okay, very simple idea, right? Oh, almost all neural network learning has this flavor and other things besides. And now, what is the delta Wi? Here's what the delta Wi is. It's a product of 3 things. The first thing, this is the Greek letter eta. I don't know why it became the conventional letter for this, but it is called the learning rate. The learning rate is basically something that decides the size of steps that you're learning with. If eta is large, right, you can make big changes in the weights in response to an example. Okay? If the eta is low, then you learn in small increments. Okay? So can anybody suggest what the advantage of a large eta might be? Why might I want to have eta be large?
Faster?
Yeah, faster learning, right? I make big jumps, I learn quickly. But what is the danger in that?
You could overshoot the right answer.
Yeah, I could overshoot the right answer and things could, crap out very quickly. So in practice, what people use is fairly small etas. And by the way, small eta means 0.1. After 50 years of research, we have this very important piece of information to impart to you. Try 0.1. 0.1 tends to work pretty well. And actually, you're saying like, oh, come on, why does 0.1 work well? Can anybody hazard a guess? Maybe it's too early for that. Maybe we can revisit this question later. But there's a reason why we actually, so we can see why we don't want it to be too large, right? And also why we don't want it to be too small, right? And you can leave this as a background process in your mind as we go through these things. Why might something like 0.1 be in the right ballpark, as opposed to 10 or or 0.01 or something? Okay? All right. So, but this is my learning rate. But now let's look at the other two pieces. One of these pieces is just my input. For that example, xi, right, is the value of 1 pixel in your retina. And in this very simple setting, we're just assuming that your pixels are just black and white, right? We're not even dealing with, gray levels yet, or color, right? So this is just -1 or 1, okay? So far, so good, right? What you're learning should be a function of your input, right? But now here's the next thing, right? This is where the action really happens. T is my target value. This is what the perceptron should be outputting. If you're trying to learn to recognize your grandmother, and this is a picture of your grandmother, the target value is +1. If it's not a picture of your grandmother, it's a picture of your uncle or something, then the target value is -1. Okay? So this is your training signal. It's the true class of the example. Okay? It's right here. And O is what the current perceptron is outputting for this image. Okay? So if currently if the neuron is firing, right, the output is 1. If the neuron is not firing, the output is -1. Okay? So this is my learning rule. Okay? So let's just ignore the learning rate for a second, right? We've already seen what it does. And so here's my question to you. What is going on here? Can you figure out why this rule makes sense? And, this is just a beautiful thing that Frank Rosenblatt pulled out of his head. Right? What is going on here? Why is my delta W T minus O times Xi?
You're changing the weights based on whether the pixels predict the right class or they don't, but nothing more than that, I guess.
No, exactly. It's that simple. But yet, it's very smart. So notice the following thing. What happens if the perceptron is currently outputting the right thing? Right? This is your grandmother, and it says it is your grandmother. What is T minus O?
0.
It's 0, right? And what happens if it's not your grandmother, and the neuron says it's not your grandmother? What is T minus O? It's -1 minus -1, right? So this is very hard math this late in the evening, right? So it's -1 plus 1, right? So it's 0 again. So translating this into English, what this means is that if the perceptron is making the right prediction, right, why mess with it, right? Think about it. If you're able to, at some point, run through all the examples, right, and for each one of the perceptron is making the right prediction, then you've learned what there is to learn, right? So this is an example of something that is very common in machine learning, which is error-driven learning. And again, that's some evidence that your brain does that. Error-driven learning means, don't go fixing what ain't broke. Is you only learn when there's an error. If there's no error, don't mess with it, and maybe it'll be okay, right? All right, so but what happens when there's an error, right? So now this is the interesting part. What happens if it is your grandmother and the perceptron says it's not your grandmother? Then what is the value of T minus O? T is +1, right? And what is O? -1, right? So T minus O is? 2. I was lying. This is the hardest question you're going to get tonight. Okay? So now what this means is that there's going to be a learning signal, right? But what is that learning signal going to be? Well, this is where my Xi comes in, right? After all, what I'm trying to do is predict whether this is your grandmother as a function of the pixel values, right? So what happens if Xi happens to be +1? So this pixel is on, right? Then what is the product of all this? It's 2, right? And so what this means that your delta weight is going to be what? Positive, right? Why does this make sense? Right? Why do I want to increase the weight of Xi? This is really what this whole thing hinges on. Why is it that in this case I want the weight of Xi to go up?
To show a bit
true, you want to basically increase the sum so that it goes over the threshold.
Exactly. Right? The way I'm going to get this thing to fire is by increasing the weight of the things that are on. Right? The other ones don't help me. In fact, they hurt. Right? So what I want to do, if I want to get above threshold, is increase the weight of the positive things. Right? So all the units that are on, I want to increase their weights. Maybe not too much, right? Because I don't want to, just jump too much and overfit and maybe diverge. Right? What happens if this guy is -1? Right? -1 means it's tending, it's tending to keep things below threshold, right? It's lowering the sum, right? What I want to do to that guy? I want to silence him, right? This guy's keeping me from firing, right? So if the output should be +1, but this input is -1, right? Then its weight needs to go down, right? Conversely, and now you see how this works, right? Now suppose that, I was in the opposite situation where the target is -1, this is not your grandmother, but the neuron is firing, right? Then I get -2, right? And now what happens is that the ones that are positive, their weight wants to go down because, this thing, the sum, is above threshold and it shouldn't be, right? I want to reduce that sum until it's below threshold so the neuron doesn't fire and doesn't say this is your grandmother when it really isn't her, right? So how do I do that? Well, there's really only two ways to do that. One is to decrease the weight of the things that are on, and the other one is to increase the weight of the things that are off or tending to inhibit this neuron. Okay? And this is your perceptron learning algorithm, right? I mean, it really is very simple, right? Literally, you can implement this thing in just a few lines of code. Questions? So hopefully this gave you the intuition, but this is not the end of the story. If this was all that Rosenblatt had done, he wouldn't have gotten excited and nobody else would have gotten excited. Because just because you have a rule that makes sense doesn't mean that this is actually going to work, right? And what is an obvious way in which this process could fail? Right, I see an example, I increase some of the weights, and then I see another example, but now they decrease again, right? Nothing in here guarantees that this thing is ever going to converge, right? For all I know, it's just going to, think of this as the hyperplane, right? That separates a grandmother from not grandmother. This hyperplane is just going to fluctuate forever and you're not going to learn anything, right? It's going to jump over here because this was a grandmother and then it jumps over there and, nothing interesting is happening. What Rosenblatt did that got him very excited was that he proved that this thing will converge to the right frontier provided that two conditions are met. Let me actually start with the second one. This is that the learning rate is sufficiently small. And this is a natural condition, right? Because if the learning rate is, suppose that the learning rate was very large, right? What that means is that I want to move the hyperplane, let's say like my grandmother is over here, so I need my hyperplane to get over there, right? So I want to push it in this direction. But if my learning rate is very large, I will push it way over there, right? So I'm going to end up with something that was worse than what I started with, right? So the learning rate has to be small. And in fact, Rosenblatt's proof requires that the weight be infinitesimally small. Which is a little unfortunate, right? Because if the weight is infinitesimally small, then the learning is not going to happen before the tiger ate you and whatnot, right? But anyway, it's a proof, right? And in practice, what happens is that you can usually find a sufficiently small value that things converge, and that's not so small that the learning is very slow. So that's one natural condition. But here's the other one. The other one, which is also not surprising, is that the training data has to be linearly separable. And notice what we're saying here. We're not just saying that the concept has to be a hyperplane. That in a way has to be expected, is to be expected, right? Because if the line dividing grandmother from not grandmother was, say, a parabola, right? How are you ever going to approximate this with a hyperplane? You're not, right? So what's going to happen is that the hyperplane is going to keep fluctuating, trying to be close to one part of the parabola or another, depending on the examples that it's seeing, right? So, okay, this is just a representational limitation of the perceptron, right? In some sense, we haven't really lost too much compared to just, what it can represent. But it's actually a lot worse than that. The reason it's a lot worse than that is that notice that what I'm saying here is not that the concept has to be linear. It's that the training data has to be linearly separable, meaning I can't have any noise. Let's suppose that, the true concept really was a straight line, right? So this can be learned by the perceptron, right? But then what I have is here I have a lot of positive examples, and so on, right? And here I have a lot of negative examples. So far so good, right? But then there's a little piece of noise. There's a little positive example here. Right? I mean, any good machine learning algorithm had better be robust with respect to things like this, let alone your brain, right? Your brain is the king of, being robust with respect to noise, right? But what's going to happen if I have an example like this? Right? Think of the perceptron training algorithm at work, right? Let's say it's getting pretty close to this frontier, right? But then this example comes along. So what is the delta weight going to do? It's going to shift this guy over here, right? Which is good, right? Because it's going in the direction of getting that example right. But guess what happens at that point? A bunch of guys are now misclassified, right? In trying to move the line to be closer to the positive example, that happens to be noise, I suddenly have now misclassified a bunch of negative examples. But okay, but then, when their turn comes, right, that'll move the perceptron right back. And so on and so on and so on. So all it takes is one little noisy example to prevent the perceptron from converging. So this is fun, but it's not very robust. Now, there's much more sophisticated versions of perceptron learning that try to combat this problem, right? There's also things that you can do that are actually not that bad, like I'm just going to stop the learning after n iterations, right? After n iterations, the thing is probably oscillating in the right range, so I'm just going to stop that right there, I'm going to take that. But, at this point, this doesn't have any guarantees, it doesn't look very pretty, and most of all, it kind of raises the question, can't I do better than that? There has to be a better way of doing things than that. Okay? And this is where our next important... any questions about this perceptron convergence theorem? I'm not going to prove that here, but, it's actually slightly more intricate proof than you might think at first sight, but it's something you can find in some of the textbooks. But, so the perceptron is important both because it gave rise to a lot of, more sophisticated algorithms, in particular support vector machines, one of the most, most recent, most sophisticated, most crackerjack machine learning techniques. One way to look at it is as a kind of very powerful version of the perceptron, right? So some of the ideas in the perceptron are still alive and well today. But, as far as neural networks are concerned, we're now going to do something quite different. And this is gradient descent. So we're still going to learn this, hyperplane, right? It's still just a perceptron, but we're going to train it in a different way. This different way is important for two reasons. One is that, as we will see, this is a much more robust way to learn than the perceptron training algorithm. But even more importantly, this is the way that actually generalizes to multilayered perceptrons with many neurons and many layers. So this is, this is very important. Okay? So what is gradient descent? Has anybody here heard of gradient descent? Raise your hand. Okay, so actually several of you have. Very good. For those of you, this will be partly review. For the others, this will be something quite worth learning about. So in order to do gradient descent learning, let us start by slightly simplifying our problem and taking away the nonlinearity. Right. What I'm going to do is I'm going to take out this step function. Okay? And just let my perceptron be the weighted sum of the inputs, right? Something even simpler. Okay? And I'm just going to try to train that, right? I have my inputs, and then the output is either +1 or -1, so we can think of this as a linear regression problem, right? We saw last time, how to do linear regression by least squares and whatnot, right? Well, let's approach this in that way, right? So let's, try to do classification just by reducing it to, linear regression where the outputs are, +1 and -1, okay? And if you think about it, right, last time we saw how the least squares criterion derived from maximizing likelihood, but we never actually saw, well, then how do we find it, right? How do we find the values of the coefficients that minimize my sum of squares? Okay? So now let us look at one way of doing that, right? And that way is gradient descent. Okay? So my output is this linear function of the inputs, W0 plus W1 x1 plus etc. plus Wn xn. And what we want to do, as we saw last week, is we want to find the weights that minimize the squared error, right? These are the weights that are going to put the output of the neuron as close as possible to +1 for the examples where it really is +1, and to -1 where it is -1. And the whole idea here is, well, maybe we can't do this perfectly, but we'll predict 0.8, right? So what we're going to do is that at the end of the day, after we've learned things like this, to make a class prediction, we're just going to say, well, if it's above 0, it's probably a +1, and if it's below, it's probably -1, right? Reasonable thing to do, okay? So let's do things this way. So how do I minimize this? And so we've alluded to this a couple of times, right? We mentioned gradient descent, upper probability, and space learning, but this is where we're really going to see what gradient descent is, right? When we have a set of continuous parameters to optimize, in this case the weights of the neuron, gradient descent is sort of like the simplest first technique that you can use, okay? And actually for a lot of things, gradient descent, despite its simplicity, is quite competitive. And it's also, efficient in many ways if you do it right and whatnot. So what's the idea in gradient descent? Here's the idea. Let's suppose, to keep things simple, that I just have two weights, W0 and W1. Okay? So I can think of the weight plane, right? Think of this room, and every point on the floor of this room is a pair of weights, right? 0.75, 1.2, or whatever. Okay? And now my error is a function of the weights, right? So, if I use, X and Y to represent my weights, now I can use the Z axis to represent my error. Okay? And now, what kind of function of the weights is the error? The very nice thing for us here is that if you squint at these two equations, you realize that the error is just a quadratic function of the weights, right? Why is the error a quadratic function of the weights? It's a quadratic, so first of all, so this error is, ignoring this half for just a second, which is there for convenience. It's the sum over all my data points, right? D, as usual, is my training set, of the difference between the true value, right? This is your grandmother or not, and the value that's output by the perceptron squared, okay? Now, but this is a constant, right? The true value is a constant, right? It just comes from the training set. So this is a quadratic function of the output, right? Of the output of the perceptron. And the output of the perceptron is a linear function of the weights, right? By design. So what I have is a quadratic function of a linear function of the weights, therefore what I have is a quadratic function of the weights, right? And a quadratic function is a beautiful thing when you have to do continuous optimization. A quadratic function is the simplest thing that you can do any non-trivial optimization for, right? If the function that you're trying to optimize is a straight line, well, then you either go to -infinity or +infinity, right? Let's say you're trying to minimize this function. Well, just go to -infinity. Not very interesting. The simplest interesting function that you can try to optimize is a parabola, right? Everything else is more complicated. In particular, the parabola has this golden property for learning purposes that it only has a global optimum, right? There's only one bump here. There aren't you don't have this kind of complication going on, okay? And that's what we have here. It's, a hyperparabola. Right? It's a parabola projected down to every subset of the weights. Okay? And so our goal, right, if this is my weight and this is my error, is to find this point. This is what gradient descent is going to be for, right? Or in 2 dimensions, right? What I have is this, paraboloid of revolution is the technical term, right? It's kind of like a parabola in 3D, right? It's this surface, right? And I'm trying to come to this minimum here. The problem, of course, is that in the beginning I don't know where it is, right? So let's just say I start with my initial couple of fairly small weights, right? Or whatever, like I start at some point here, right? Let's say that these are my initial weights, okay? Corresponding to these initial weights, there's an initial value of the error, right? This is the sum of squared errors when I run the perceptron, my training data with those initial weight values, okay? And now the million-dollar question is, how do I figure out which way to go? Right? I want to take a step in the right direction. In this case, I could do linear algebra and matrix inversion and whatnot, and figure out what the solution was. That is an option. But actually, for large-scale problems, gradient descent can actually be better than a method like that, which is roughly cubic in the size of the problem. Okay. So how do we figure out which is the right direction to go?
Which way the slope is steepest?
Exactly. Right. I mean, you don't want to go that way, right? Because the error is going up in that direction. In these directions, right, the weight isn't going up, but it's not really going down either, so it's not going to help you, right? Think about this. Like the problem here is like this: is like somebody just put you, on the slope of a mountain, and you want to find your way to the valley, right? And there's a very thick fog, right? So you can't see anything. But you can see which way the ground is sloping under you, right? So if you want to get to the valley, what do? Right? You take the steepest direction and you go that way, right? Other things being equal, that's what's most likely to get to the valley soonest, right? And indeed, this is often called steepest descent, right? Or gradient descent. Okay, we will see shortly what gradient means. Okay? So that's what we're going to do. We're going to take a step in the direction of steepest descent. And then we're at a new point, we measure the new error, and then we take another step in the direction of steepest descent. Okay? The new direction of steepest descent. And when does this end? When do I know that I'm done?
When all your neighboring points are higher up than you.
Exactly. When I've gotten to the point where every step that I try to take is uphill, then I know that I'm done. Now, in general, you could be stuck in a local optimum, right? But in this case, we know that it's the global optimum, so this really works. Okay? So this is what we're going to do, or at least this is the geometric picture of what we're going to do, right? Now comes the mathematical version. Right, so any questions about this so far? This is a very important intuition, or at least, you want to be able to visualize what we're going to be doing before we get into the gory details of the calculus, which are actually not that gory. Okay, so how many people here know what the gradient is? I see a few hesitant yeses, right? You're not so good news. You're not expected to know what the gradient is, right? We will do your 5-minute review of multidimensional calculus right here, or maybe maybe next week. Okay, but let me just tell you what the gradient is, so you can dream about it in the meantime, right? The gradient of a function is represented by this sign, which is an upside down delta, often called del or nabla. And the gradient of a function is just of a function of many variables, right? So E, the error, is a function of many variables. The weights, W1, W2, etc., is just a vector with the same dimensionality as the input variables, right? So if I have n weights, my gradient is going to have n components. Each component of the gradient is the partial derivative of the gradient with respect to that weight. Okay? What is the partial derivative? Is if I keep all the other weights constant, right? Now my error is just a function of this one weight. Okay? And now this has a derivative, right? And that's what this partial derivative is. Okay? So what I need to do to compute the gradient is use my good old rules of calculus to compute the derivative of the gradient, to compute the derivative of the error with respect to each of the weights. And then I glom all of these into a vector, and that's my gradient. So if I have 100 weights, my gradient is just 100 numbers. A large number means that the function is varying a lot with this weight at this point, right? And so what that means is that I want to go in the opposite of that direction a lot. A low value of the gradient means that the function is changing only a little bit, so maybe I want to go in a little bit in that direction, but not that much. Okay? So this is the idea. Now my training rule is just going to be that my delta W, contrast this with the perceptron rule, is going to be minus my learning rate times the gradient, right? The gradient tells me what direction I want to go in, and the learning rate tells me how big of a jump I make. And the same considerations as before apply. The learning rate should not be too large nor too small. Now, final question, why is there this negative sign here?
You're descending, so
yeah, because I'm descending. Otherwise, I would be ascending, right? The positive sign would mean I'm going up the gradient, but I don't want to go uphill. I want to go downhill, and that's why this minus sign is. Okay? So if you don't want to think about the gradient, you can just think in terms of derivatives. What happens is that the delta in a particular weight is just minus the learning rate times the derivative with respect to that weight. Okay? And next time we'll see what these derivatives are. We'll see the full perceptron algorithm, and then we'll see the multi-layer perceptron and what needs to change to be able to do things with naive Bayes. Okay? And in the meantime, have fun with naive Bayes and span filtering. All right, everybody, welcome back. Let's get started. Today is the day that you find out how your brain works. Unfortunately, we're not quite there yet. But next best thing, we'll find out how backpropagation works. And in order to do that, first we have to see how gradient descent works for a perceptron before we go on to the more complex case of multi-layer perceptrons. So as a brief reminder, here's where we left off last time. Here's the model that we're trying to learn for the moment. right? Remember, a neuron is a linear combination of its inputs, right? A weight times each of the inputs, passed through a step function, but we took out the step function to make things simpler. And now all we have is a linear regression. The output is W0 plus W1 times X1, etc., etc. Okay? And we want to learn the weights that minimize the sum of the squared errors. So it's a linear regression, right? So the sum over all the examples in the data set D, in the training set, of the target value, TD, minus the value that is output by the perceptron, i.e. this one, squared. Okay? So if we can make these all very small, that means that we have a very good fit to the data and we probably learned a good model. Okay? Now how do we do this using gradient descent? Remember this diagram? Right? This plane is my weights, and here I just have two weights for simplicity, but in reality I actually have millions. And this is my error as a function of the weights, and it's a parabolic surface. Okay? It's very smoothly. It has only one global optimum, very nice thing, right? And we start out with some random, initial weights, let's say right here, right? And so this is our initial error, and we want to get over there to the minimum, okay? And the way we're going to do that is by finding which is the direction of steepest descent here. Let's say it's this, right? And then we take that step, take a small step in that direction, and then we do the same thing again. And so little by little, we finally wind up at the minimum, at which point all steps are up, right? And we stop. Okay?
Yeah. Is it true that these always have global minimums? I thought there was possible to get to local.
No, absolutely. So in general, a function might have lots of local optima, and in fact, that's what's going to be the big problem in backpropagation when we have multi-layer perceptrons. But for now, we're just dealing with a single perceptron where, remember, the output is a linear function of the weights, and the error is a quadratic function of the output. So the error is a quadratic function of the weights, meaning it's a parabola, meaning it only has one optimum. Okay? So how are we going to find this direction of steepest descent? Right? This is where the calculus comes in. Right? That direction is the direction of the gradient. And what is the gradient? The gradient is just a vector, and each component of that vector is the derivative of the error, the partial derivative of the error, with respect to one of the weights. Okay? And the way you find the partial derivative is you keep all the other weights constant, and then you use your good old rules of calculus, which is what we're going to do next. Okay? So this is what we're going to try to do. And then our training rule is just that my change in weights is minus, remember minus because we want to go down in the gradient, not up, eta, which is the learning rate, that determines how big of a step we take, times the gradient. Okay? Or if you look at this one component at a time, like we did for the perceptron training rule, the change in one weight is just minus eta times the derivative of the error with respect to that weight. Okay? So the bottom line is, we need to figure out what this derivative is, and once we've done that, we know how to learn perceptron using gradient descent. Okay? Any questions so far? All right, so let's do that. Haven't you missed calculus? Remember those good old days of college when you had calculus to take? And you thought you were free of it forever, but now it comes back to haunt you in machine learning and other things too. But the good news is the calculus that we need for this is not that, painful. So let's do it, right? So I want to compute the partial derivative of the error with respect to the ith weight. Okay? So here's my expression of the error, right? Please interrupt me at any point if you have questions, or you're not, or you're missing a step. Okay? We're actually going to do this here for two reasons. One is, it's a nice exercise in its own right, but another one, maybe even a more important one, is that we're laying the groundwork for backpropagation. To understand backpropagation, you have to understand this first. That in some ways is the bigger reason for looking at this. Okay? So let's start with this simple case. Okay? So the derivative of a sum, right, is the sum of the derivatives, right? So I can push my dwy inside here. Okay? Everybody agree? Okay, very good. And now remember, what we have here is a quadratic function, right? And we're going to use the chain rule of differentiation. Can anybody remind me what that is? My calculus is rusty too, so I need help here. What's the chain rule of differentiation? It says that, let's do that here in the corner. d dx of f of g of x right, of a function of x is
d of f of g of x with respect to d of g of x times
very good.
d of g of x with respect to d of x.
Yep. Everybody agree? Or anybody disagree? If you don't remember, you don't disagree, right? It's the safety of amnesia. Okay, right, so let's apply that here, right? So my f, right, is td minus od squared, right? And then my g is td minus od, right? And what's the derivative of x squared? 2x. And that is the devious reason why we put this half here, right? You might have been wondering why we divided the sum of squares by 2, right? Why is that factor of half there? It's not needed. It's there on purpose so that it will cancel with this 2 to make the final expression simple. Okay? So here is 2, right, times the function, right? This is the df dg, right? Now dg dx is the derivative of td minus od with respect to wy. Okay? So now, what is that? Let's see, step 1. Let's replace od, which is the output of the perceptron on the dth example, right, by its expression. Okay, everybody with me so far? The expression of od, remember, in a very compact form is just the dot product of the weight vector and the input vector, right? So all that we did from here to here was replace od by the dot product of the weight vector and xt. Okay? Xt itself being a vector of, some number of components. Okay? Okay, very good. So now what is this expression? Can anybody tell me? So it's the derivative with respect to wy of td minus this dot product. Okay? So what's the answer here? First of all, what's going to happen to td? What's d dwy of td? 0, right? It's a constant. Now here's the more interesting part, right? What's d dwy of w dot product x? Right?
Depends on whether the w is the...
Remember, right? Let's actually go back and look at our expression, right? This is our expression, right here. Right? And I want to find the derivative with respect to wy. Like, for example, let's suppose that I wanted the derivative with respect to w1, right? What would that be?
Just x of 1.
Just x1, right? Everybody agree? And so, and what would be the derivative with respect to xn, with respect to w1? Just gave it away.
xn.
Xn, right? So in general, the derivative with respect to xi is, to wy is? Except for one small detail, which is what? This minus sign here, right? So it's going to be minus xi. Okay? Everybody agree? And hey, this is our expression. That was easy, right? So what is the derivative of the air with respect to a weight? It's the sum over all the examples of the difference between the target value for the example and the output of the perceptron in the example times minus the value of the corresponding feature in the example. Okay? Simple enough. And this is how we're going to train perceptrons using gradient descent. So we're going to do the same general type of idea. So as before. So we initialize all our weights to some small random values. There's a lot of magic in neural networks in initializing with small random values. We will see later why that might be the case. And then we do the following until we converge, right? Meaning the weights aren't changing by more than 10 to the minus 4 or something. Okay? Here's what I do. I initialize my delta wy. This is the amount by which I'm going to change the weight in this iteration. I initialize it to 0. And then I run through the training examples. I input the example to the perceptron, right? Present it at the input and, get the output, right? And then what I do is I compute my delta weight using the expression that I just saw, right? And then finally, I add up all these delta weights, and then at the end of each sweep through the examples, I change my weights by that amount. Yeah.
In a perceptron, there are a number of inputs.
Mm-hmm.
And then there's this one threshold input that comes out from Does the threshold input follow the same training rule as the rest of the weights?
Yep, it does. So let's look at that as an exercise, right? So you see this W0 here? This is what you're asking.
One times the threshold. Right?
Yeah, so this what we're going to do is we're going to pretend, because this makes it a nice dot product, right? We pretend that there's an input x0 that happens to always be set to 1, right? That's correct. And so that also tells you what the gradient is going to be with, what the partial derivative with respect to this W0 is going to be, right? It's going to be minus x0 blah blah, which is just minus 1. Other questions? Okay, so we have here a very nice little method for learning perceptrons. And it's an alternate method. So anybody have questions about any of this? So let's compare our two methods, right? We have two methods here for learning perceptrons. One is Rosenbrat's famous original perceptron training algorithm, and the other one, which came a little bit later, is gradient descent. Okay? So let's see. The perceptron training rule is nice. There's a theorem that says it converges to the right thing, but only if the training examples are linearly separable and my learning rate is very small. In fact, infinitesimally small for the proof to go through. Okay? Now, what happens with gradient descent, right? With the gradient descent is actually much better, right? First of all, with gradient descent, notice that we are guaranteed to converge to the minimum error whether or not the data is linearly separable. There could be any amount of noise that you want. The frontier might not even be a straight line, but we'll always do the best that we can. This is much, much better than what we had before. If you go back to this figure here, right, what happens is that if you're lucky, the minimum here is sitting on this plane, right? And the best, error is 0. On the other hand, if you're not that lucky and this thing is floating somewhere above that plane, right? You'll still get the minimum error that you can. It won't be 0, but it's much better than oscillating forever like the perceptron training algorithm does, right? So this is a big advantage of gradient descent, and one that we're going to hold on to as we go forward, right? However, we still have the same condition that the learning rate has to be small, right? You see why the learning rate has to be small again? Let's go back to this picture, right? If the learning rate is too large, let's suppose that I had a very big learning rate, then when I take this step here, right, this step here, instead of walking me only over here, it might actually overreach. In fact, on a bad day, if my step is too large, and we really at the outset don't necessarily know what it should be, I might take so let's project this all on the plane here, right? I want to take a step in this direction, right? And ideally, actually, I wouldn't take such a small step. I would take a bigger step and land right over here, right? And in fact, if I overshoot by a little bit, that's not so bad, right? Because then I'm here, and what happens is that I zigzag until I basically converge to where I need to be, okay? The big problem is if my step is way too big and then I overshoot so much that I actually wind up at a higher error point than I started, okay? So here's one way to look at this. Here's my error surface, right? Now with just one weight, and this is the error, right? I start out here, and ideally, I would like to make a jump to here, right? I'm okay with actually making a jump to here because that will zigzag to the answer. What could go wrong, right, is if the following happens. I start out here, and I make a jump in the wrong direction, but I take it so far that I go over there, right? Notice I'm actually going in the right direction, but I'm just going too far, but I've actually made my error worse. And then when I do the same thing in the opposite direction, I basically spiral out of control. This is what you want to avoid, right? This is a catastrophe, right? It ends with non being output by your computer, okay? So we are willing to take a step that's too short and, take some number of steps to get there in order to avoid this. And what exactly number you should use is a deep mystery of nature, and the answer is 0.1. Well, the answer is not 0.1, but, you could use it as a starting point. It's worked for a lot of people. So, but the bottom line is we still have this issue of the learning rate, right? We have this big advantage that we are not tolerant with respect to noise, and we're tolerant with respect to the, decision surface not even being a straight line or a hyperplane, okay? But now, let's look at this for a second. What exactly is the difference between these two algorithms, right? Gradient descent is much, much better, right? But let's look at the expressions, let's just this lay on the side. Let's compare the expressions for the weight updates in the two cases, right? So the weight update here is learning rate times t minus o times x hat, right? Hold that in your working memory, right? As we rapidly flip back to our good old perceptron training rule, and the weight update there is the learning rate times t minus o times the value of the feature. So what is the difference between these two?
O.
O is the difference? Why is O the difference? So first of all, they look exactly the same, right? It's exactly the same expression. Somebody must be pulling the wool over your eyes, right? What is going on here, right? These algorithms are so different, but yet they look the same. So the difference is O. Why is the difference O?
I read this chapter a while ago, and that's all I remember.
Wow, you get kudos. You get 3 points for honesty.
Yeah.
Right? Hey, that's not bad, right? Having an inkling of the answer is usually the most important thing, right? The bad thing is when you have no inkling of the answer, right? So why is O the difference? You're absolutely on the right track, right? But why is O the difference?
My guess is that, if there's a single perceptron, it's either above the threshold or below, and so there's only two values. But with gradient descent, it's a combination of more than one vector.
Exactly. So you've got both the basic idea right, and also why this works from a machine learning point of view. So here's the big difference, right? Is that in the perceptron we had this step function. So my output of the perceptron, my O, was either +1 or -1, right? It's a null or none thing. You're either above the threshold or below, right? The big thing, the sneaky little thing actually that we did when we went to gradient descent is that we took out the step function. As a result of which, this is now a smooth function, right? So my O before was +1 or -1. My O now is a real number, right? So that is a big difference. And that is a very big difference for their learning. You know why? Because we have a signal. This is the key thing about the gradient descent idea, is that the gradient is your learning signal. It's the scent that you can follow to get to where you want to go, right? In the perceptron algorithm with nonlinearity, you know that you're above the threshold, but you don't know where. You could be very close, you could be very far. You don't know what the contribution of the different weights is, right? Here, you always know how much changing each weight will help or hurt, right? You have a continuous surface that leads from the badlands of wrong answers to the good place of good answers. So the fact that we took out the nonlinearity makes a huge difference, right? It makes things much easier to learn. Did everybody follow this? Small difference, big implications. At the same time, this was kind of a cheat, because what we're really trying to do here is not, so we optimized something, but we didn't optimize what we really want to optimize. What we really want to optimize is the number of errors that you make. This is a classification problem at the end of the day. It's not linear regression. We just disguised it as linear regression. So that was a little bit of a cheat there, but it's at the end of the day, it's a big improvement. Questions? Okay, so that's perceptron training rule versus gradient descent. Let me just mention one more thing before we go on to backprop, and this is an important thing as well. It's the difference between batch and incremental gradient descent. What we've talked about so far is batch gradient descent, which means that you look at all your examples, you compute your gradient, or same thing. The same thing is going to apply when we do backprop, right? You compute your gradient and then you update by that gradient. Okay. This is actually the algorithm that we have here. Let's look at it again, right? What happens is that I ran through all the examples, adding my deltas to the big delta, and then at the end of the day, I apply my big delta, which is a sum over all the examples, to the weights. Okay. And this is what our guarantees and our treatment is about. Okay. However, what people usually use in practice is incremental gradient descent. Let's see what incremental gradient descent is and why it might be better. Okay? And the difference is actually very, very simple, is that I don't wait until I've seen all the examples to update my weights. I just update the weights after each example, right? You could speculate that this is a little bit like learning live versus learning in your sleep, right? Presumably, presumably, or in reality, right? You're learning. The weights in your neurons are actually changing during the day. Okay? The analog of batch is, you store all of that up, and then at night you sleep, and then the weight learning happens. Maybe some of both is happening. In any case, this can actually work very well for learning. So number one, which one do you think is going to be faster, batch or incremental? Right, which one do you think is going to get to the optimum weights faster?
Batch probably.
Batch because?
Seems like you may be moving in wrong directions based on a few training examples.
So you're actually right about, so your justification is correct, but the answer is wrong. Hey, not bad, right? You get half credit, or maybe even more, right? So the problem that you just pointed to is a very real one, but let's hold off on it for just a second, right? Incremental gradient descent is usually a lot faster because you're doing many more updates, right? Let's suppose that I have, 100,000 examples. I have to go through those 100,000 examples before I even change the weights. Probably, even after a few examples, it was already clear that I need to change the weights in this direction, so change it right away. This is why incremental often converges a lot faster, okay? Because it's just doing more updates, right? It's doing updates, n times faster, where, n is the number of examples. Nevertheless, you pointed to a very good example, which is, what happened to our guarantees, right? Are we guaranteed to converge to an optimum? We actually aren't anymore, right? Because now we're zigzagging. Now, there's a stochastic component to the movement of the weight vector, right? Before, the weight vector was just going straight to the goal. Now, the weight vector is jumping around. And this could be a problem. In fact, in learning a simple perceptron, it's usually never a problem. In learning a more complex thing, it could throw you off into a bad direction. However, this is where the second important thing comes in. Usually that noise part, instead of being hurtful, is actually helpful. Can anybody guess why the noise might be helpful? Right, you can see that the steps that we're taking are like the right steps with some noise added to it, right? You can look at it that way, right? So why would it be a good idea to add noise to the gradient direction? In the plane perceptron, that's not going to make a difference, but in backprop, it often improves things. Why might that be the case?
Avoid local optima sometimes.
Exactly, it helps me to avoid local optima, right? So suppose that I have something like this, right? And I want to get over here, but I'm converging towards here, right? But if I'm doing this with noise, it's like my ball rolling down the hill is bouncing, right? And if I let the ball bounce, I actually give myself some chances of getting over that little hump and into the right optimum, okay? So the downside of incremental is that you have no guarantees anymore, so if you're of a theoretical mind, that may disturb you. However, if you're really of a theoretical mind, you'll try to come up with guarantees for that case, and people have, certainly. But, on a practical level, it will probably give you faster learning and a better result. So, incremental is often the method of choice. Incremental is often also called stochastic, precisely because it's like having noise, yeah.
Do you have to worry less about the learning rate in incremental? Because
you don't have to worry less, but you have to set it differently. Right? It's the same trade-off as before, but obviously the ideal value of the learning rate for batch and for incremental are going to be different. Right? For incremental, it's going to depend on the number of examples and so on. Okay? If you take, here's a nice thing to do, right? You have your batch algorithm, you're making incremental, and you get the same update. There's a good chance that you'll diverge. Okay? So you need to set it, separately. More questions? Okay, very good. So, but now let's get to the really interesting part, which is networks of multiple layers with many different neurons, right? That's what your brain is like. It's not one neuron, right? One neuron is not that exciting, right? So here's a real example. So remember, we saw that perceptrons could only learn hyperplanes. Now we're going to learn much more powerful things. For example, here's a speech recognition problem, right? Traditional application of neural networks. My inputs are the two formant frequencies. So your voice has a frequency spectrum, and the formants are the peaks in that spectrum. You know, like when you say ah or oh, right? You know, you look at the spectrum. Often there's one peak and then there's another one and so forth. Okay, and F1 and F2 are the two first peaks. Okay, and so what I want to do is I want to see if I can predict what word you're saying as a function of just these two. Of course, in general, there's going to be more things, but the advantage of having just these two is that we can actually see it graphically, and you know these are usually the two most informative features. Okay, so here's my backprop, right? My two inputs are F1 and F2. And now notice it has a hidden layer, right? Just like the car driving network that we saw before, right? It has a hidden layer, and then it has an output layer for each possible word that you might be pronouncing. And you know, what you would like to do is, if you're saying head, the unit for head lights up, meaning it has a high value or close to 1, and all the other units, you know, stay close to 0 or even to -1. Okay. And notice that this is a pretty hard task because it's head, hid, hood, and hood, right? Not easy. You know, a perceptron isn't going to solve this particular problem. So here's actually the solution that backpropagation found. And you know, like the marks are hard to see, but basically each of these marks is a different word. Like, so for example, you know, this is an instance of the word head and so on and so forth. Okay? So these dots are your data. Very hard to separate. But backprop actually was able to produce these frontiers. For example, for one of the words, this is the region. For another of the ones, this is the region. Right? Very complex nonlinear frontiers, right? Something pretty fancy is now going on here. Okay? If you try to separate this with lines, you know, you'd be hosed, basically. Okay? So the big question is, how can we do this? And this question actually has a very interesting history, because what happened is back in the 60s, when neural networks were first a big deal, there was also this other symbolic approach to AI, where people didn't do learning so much. And they were very jealous of all the attention that the neural network folks were getting. Attention and money from the funding agencies like DARPA and whatnot. And then there were these two guys from the symbolic camp, right? And you know, the symbolic camp is things like decision trees and rule sets, and remember the whole, you know, deduction, resolution, things like that. This is what these kind of people tended to do. Two of these guys, Marvin Minsky and Seymour Papert, wrote a famous book called Perceptrons, which was the biggest hatchet job ever done in the history of computer science. It was a very good book, you know, it was very rigorous, full of, you know, theorems and well worked out examples and whatnot. And basically what that book showed was a whole host of things that, really trivial things that the perceptron couldn't learn. One of them was the famous XOR, but there were many others. And basically what happened is that after all the hype that Frank Rosenblatt had been putting out about perceptrons, this was a real downer. And now, and you know, and Minsky and Papert speculated that, you know, like, you know, they understood the problem. They said, well, if you were able to put together networks of these units, right, then obviously you would be able to learn complex functions. But nobody knows how to learn them. That was the problem. And their thing stood for 15 years. There was a neural network winter during which neural networks were completely discredited, and only a few diehards continued to work on them with no funding. But then there was a neural network renaissance circa 1980, mid-80s. Motivated by a couple of different things, but this, you know, backprop was probably the single biggest thing that made neural networks take off again. So backprop was an answer to this problem. So now what is the problem, right? Let's see what the problem is. Let's look at the two algorithms that we have right now. The first one is our good old, you know, basic perceptron training rule. It's not clear at all how to generalize that rule to a situation where you have many neurons and you have hidden layers. Because calculus can help you, right? There's that discontinuity, right? And so information doesn't propagate over the discontinuity, right? You don't know. The whole problem is that when a mistake is being made, I actually don't know whose fault it is, right? I'm getting this guy wrong. It's firing when it shouldn't. Well, whose fault is it, right? I don't know if it's, you know, like, look, there's weights going from here to here, but then there's also weights going from here to here, right? And now I have this credit assignment problem, right? There's so many different ways in which you could get the right answer and the wrong answer. I don't know what to do. Okay, so no one actually has ever figured out how to generalize the perceptron training rule to multilayer perceptrons. Of course, that's why we studied gradient descent, right? Now with gradient descent, you don't have that problem. right? With gradient descent, you actually do have a signal, right? But now, more subtle problem. What is wrong with just, oops. Oh, here we are. What is wrong with just letting my neuron be a linear function? Right, this is what we did for gradient descent, right? We just turned it into a linear function. We took away the step function, right? And everything worked out for one neuron. But what is the problem of constructing a network of these things?
Still is it linear?
It's still going to be linear. A network of linear functions, right? This is very easy math, right? Let's suppose that, I replaced each of these guys by a linear function of the inputs, right? Linear function, right? Well, a linear function inside a linear function, apply the distributive law, and it's still a linear function. So the problem with this is that it doesn't buy you anything, right? The whole point of learning networks with multiple layers is that now you can learn richer things, but in terms of representational power, if those individual units are linear units, building a network actually doesn't buy you anything. Okay, so that doesn't work either. So what can we do? Any suggestions? Let's pretend you're back in 1968 and you're Frank Rosenblatt and you're really desperate to overcome the criticisms of Minsky and Tappert. What can you say? So step function doesn't work, right? This is what we've seen so far. Plain linear unit doesn't work either. So what might we use?
Nonlinear.
You need a nonlinear function, absolutely, right? It has to be nonlinear, right? Because if it's linear, nothing gained. But it must satisfy a very important requirement, which is?
Monotonicity. It needs to be monotonic.
Actually, it does not need to be monotonic. Remember when you looked at radial basis functions? The function that was actually not monotonic, it was a function like this.
It needs to be continuous.
Yes, we're on the right path. Even more than continuous. Remember, we're going to want to apply gradient descent to it. Therefore,
one global optima, ideally.
Oh yeah, sure, we'd love that, but that'd be nice to have. But we're willing to give up on that.
Differentiable?
Differentiable, exactly. This is the problem with the step function. It's not differentiable, right? So things basically go haywire. So this is what we need. We need a nonlinear differentiable function. In fact, that is all we need. The backprop algorithm that we're going to see here works with any nonlinear differentiable function. It has to be differentiable, or we don't know how to do, gradient descent, and backprop is really just a form of gradient descent at the end of the day, right? But apart from that, there are no requirements. Now, of course, some will work better than others, and the two most popular ones are the radial basis function, where basically what happens is that, I put these localized bell-shaped curves at individual points in the input. For some things that works pretty well. But the most popular version, not surprisingly, because this is inspired by the brain, is a sigmoid function. Our good old sigmoid, right? This is what the firing rate of the neuron looks like as a function of its some input. Right? Remember, you might be thinking, well, how is this inspired by the brain, right? In the brain, you either have an action potential going down the axon or not, so it's digital, right? The way people squint at it and look and make it look continuous, and this is a plausible way to look at it, is that you just look at the frequency of the action potential. And so what happens is that if there's no input, then the frequency is very low. It's actually not zero. Neurons just fire at random every now and then. And then as I get more input, right, the action potentials start to happen quicker, and then quicker. But finally, there's a maximum rate at which the neuron can fire, and that's when you've reached this part here, right? So the frequency of firing of the neuron as a function of its summed input actually does look roughly like a sigmoid. It's a noisy sigmoid, but we can approximate it with a sigmoid. Okay? So we're going to use a sigmoid because, hey, it's biologically plausible. This is a popular phrase in neural networks. And, it also is a good building block for what we want to do. Okay? If you think about it, the sigmoid is really just a smooth version of the step function. Right? the step function doesn't work well, like, let's smooth out the edges so that it's differentiable everywhere, but still remains a nonlinear function. Okay? So this is the answer. But now I have a question for you. Why didn't Minsky and Papert see this answer, right? It's not rocket science. What was their problem? Can anybody guess?
Confirmation bias?
Mm-hmm.
Just psychology, confirmation bias. They wanted it to fail, right? They were from the other camp.
You're absolutely right. That is 90% of it. But what's the other 10%? What is the technical point on which that confirmation bias stands?
Gradient descent discovered at that point.
Yeah, I mean, gradient descent is just calculus, right? Which was invented by Isaac Newton, right? So, and Leibniz. So that itself was not the big problem. The big problem was actually the following thing, is that this was the big problem. They were like, yeah, you can put nonlinearities here, but then you don't have a global optimum anymore, so you don't have any guarantees about the result. And again, people often get very stuck on having guarantees. And back then computers weren't very powerful. Unless you had guarantees, you weren't willing to trust it. And they were like, well, at that point you can't say anything, so, remember, this was a book of mathematics, right? And if you're a mathematician, you squint at this and it all looks very questionable to you, yeah.
So what does the threshold weight mean on a sigmoid now? Because before, if it was the step function, if you're above the threshold, then you're 1. If you're below the threshold, then you're -1. What does it mean?
Yeah, good question. Here's what the threshold is. The threshold basically decides where this guy is going to be on the x-axis. So here's a threshold of 0. Right? Remember, the threshold is the value of x at which you switch. Right? So a threshold of 0 means that the switch point is at 0. Right? A threshold of whatever x0 means that the switch point is at x0.
Okay.
Right? So by varying, so I have my sigmoid function, right? And what varying the threshold does is it slides it around the x-axis. Okay? And the threshold is learnable too, and we're going to keep doing the same trick of hiding it all under the dot product. Okay? So the big shift that happened between 1968 and 1983 was actually that people were now willing to deal with this. Partly because by this were now the 80s, and there were these very powerful computers called DEC-VAX. Have you heard of the VAX? And PDP. Literally, this is what they were using for these experiments. They were kind of silly by today's standards, but nevertheless, what they were able to see was things like the porcupine curve. That, you have a lot of local optimum, but they're usually pretty good, so, we'll be satisfied with one of them. But it was actually like a big cultural shift that had to happen. There's a lot of people in applied math and engineering that still want to be in this case, in a lot of areas. But, in machine learning, we're willing to deal with this. In fact, even in machine learning, there's still people who only want to work in this case, but there's also people who who are willing to work in this case. And in fact, what the biggest joke in all of this is that there were these guys, David Wilmerhart and his colleagues who introduced backprop in 1980 something. And then it became a very famous algorithm. And then, somebody found out that there was this guy in economics at MIT in 1979 who had come up with the algorithm before and published it. It's just that, the computer scientists didn't know about it. Right? And this is very typical in the history of science. And then they discovered somebody else who had done it before. And the best part is, there was somebody who had published in a control theory journal the year before the perceptron book came out, the backpropagation algorithm. So when Minsky and Papert wrote their thing saying like, well, this is never going to work, there was already an algorithm. Isn't this amazing? Remember the saying, one afternoon in the library could save you a month in the lab, or 30 years of research in the real world. Okay. So and maybe somebody will discover that Aristotle invented backprop. Right? Who knows? Maybe someone will read one of his books and go like, yeah, this was really backprop described in a different way. Yeah.
I'm confused about the x. The graph here is like as if you had one x value, right?
Mm-hmm.
Wouldn't it? Doesn't the weight alter the?
No. Remember this graph here. So okay, let's not go into this, right? So here's what I'm doing, right? This is my
I'm sorry, I'm looking at the bottom two they drew,
Mhm.
and answering the what W0 stands for.
Yeah, but this shouldn't just. It's not just one x. It's
Okay.
it's what I'm gonna call net here. It's the weighted sum of the x's. So here I was just looking at the sigmoid, y as a function of x, right? A generic x. But what our x is going to be in a neural network is sum of wyxi. Okay? So I have all my inputs, could be very many. Remember, each of your neurons has on average 10,000 inputs. I multiply them by their weights, and then I have a single real value. And that's the single real value that I'm going to put through the sigmoid.
Okay.
Okay? Okay, very good. So remember, this is just the same picture that we had before, except that the step function was replaced by this. Okay? And I'm going to call the input, this is going to be very important for us, I'm going to call that linear function just the weighted sum of the inputs net. Okay? And then my output O is just the sigmoid applied to net. And I'm going to represent the sigmoid by sigma, as here. So this, the output is sigmoid of net. Okay? So there's the value before the nonlinearity and after. Right? And here's the sigmoid function. It has this shape. It's 1 over 1 plus e to the minus x. People often also use the hyperbolic tangent function, which basically does the same job. It has the same shape, except, it goes between minus 1 and 1 instead of going between 0 and 1. I mean, again, you could use one or the other. Okay? But the sigmoid is very convenient for us. One of the reasons why it's convenient is that its derivative, which we're going to be seeing, all over the map, obviously, because there's one for every neuron, has a very nice form. So if you do the exercise of, getting out your good old rules of calculus and differentiating this with respect to x, you will then see that it can be expressed very nicely in the following form. The derivative of sigma with respect to x is just sigma times 1 minus sigma. So, as a preview, what's going to happen is that we're going to have our big, chain rule of the output as a function of the input, and then every time there's one of these sigmoids, we just need to put in a factor like this. Not a big deal. Okay. Questions so far? All right. So, let's do this in 2 steps. We already know how to do gradient descent for a linear unit. Okay, so the first step is figuring out how to do it for a single sigmoid unit. So this is still just one perceptron, except that it's a perceptron that now has the sigmoid instead of having nothing. Okay? And then at that point, we are finally ready for backprop. We're going to see how we do this on networks with many layers of neurons. Right? So one way to look at this is, after we've done this part, we will know what the derivative of the error is with respect to a weight at the output unit. Right? Because if you take the hidden layer as fixed, right, finally you just have, output units, and at this point we will know how to do things for those. But then the really interesting problem comes, what is the derivative of the error with respect to the weights in the hidden units, right? Because that error, is passing through the units that are not hidden, okay? And by the way, this, we're going to do this, with one hidden layer in mind, because that's what people use 99% of the time. But in principle, this could apply to any number of layers. All right, so let's do it. Any questions so far?
Just about what you just said. Is there ever a reason to have multiple layers within units?
Wonderful question, and the reason is, the answer is absolutely yes. Networks with more more layers are much more powerful than networks with fewer layers. In the following sense. So we will see later when we talk about the representational power of the perceptron that actually, if you give me if your function is always finite, and actually let's just take the Boolean case, simplest case. You can here's an exercise to the reader. Figure out how to represent any Boolean function using a neural network with only 2 layers. Can you think of how to do that? There's actually a very simple answer, right? And I'll even give you a hint. First, convert your function to CNF or DNF. Okay, pick one. Let's say we pick DNF. Okay, so now your function is in DNF, right? How do you represent this using a neural network with 2 layers?
A layer for AND and layer for OR.
Yeah, right. remember we saw last time how you can represent an AND using a single perceptron and how you can represent a NOR, right? So what do we have at DNF as well? I need a neuron for each of the ANDs, right? And then I need a neuron for the big OR, and we're done. So, by this then you might think, well, what is the point of having more layers, right? I already have everything I need. Well, here's the key difference, is that functions that take an exponential number of neurons with 2 layers might take only a linear number of units with more layers. In fact, our good old friend or our good old enemy, the parity function, if the number of layers that you have is even 1 minus the number of inputs, you need an exponential number. But if the number of layers is equal to the number of inputs, then you only need the linear number. I will leave this as an exercise, right? You might actually sort of like already have an inkling of where this is going to come out. But look at the difference, right? By having very deep networks, I actually took the complexity of representing my function that I want to learn from exponential to linear. And of course, it's not just the complexity of representing it, it's the time to compute with it, and it's having samples to learn and whatnot. Okay? So in general, having deeper networks is a very desirable thing to have. Also, look at your brain, right? If your brain was just 1 layer, you wouldn't be taking this class, right? Even the flatworm has more than 1 layer, right? There's nature, doesn't do anything with networks with just 1 layer. Okay? In fairness, networks with 1 layer, as I mentioned before, can be used for lots of things like, predicting stock fluctuations and foreign exchange and things like that. But, definitely networks with more than 1 hidden layer are more powerful. Okay? Other questions? Okay, so let's do this. So let's repeat the thing that we did before for the linear unit, but with our new nonlinearity added, right? And let's see what changes. It's actually not that much, okay? So remember, I want to compute the derivative of the error with respect to each of the weights, right? We have a single neuron, it has a sigmoid at the output, okay? So here's the same thing as before. The derivative of the sum is the sum of the derivatives. So far, so good. And now I apply my chain rule, right? And here I have it, right? It's 2 times blah times the derivative of blah. And these guys cancel. Same thing as before, right? But now let's get to, the more interesting part, okay? So remember, dwy of td minus od, right? This part goes away, right? Because t is the target value, it's a constant, right? But now what I have is the derivative of the output with respect to the weight, right? Before this was easy, right? It was just the corresponding feature because it was a linear function, right? But now there's a sigmoid there in the middle, okay? So what I actually have is a composition of 2 functions, right? The linear sum, right? And the sigmoid, so I can apply the chain rule, right? Backprop is all about the chain rule, really, right? So I can decompose my derivative of the output with respect to the weight into a product of 2 things. The derivative of the output with respect to net, remember net was what I called the weighted sum, times the derivative of net with respect to the weight. Right, everybody agree? Okay, very good. And now we're almost done actually. Right, because we know that the derivative of the output with respect to net is just the derivative of the sigmoid, right? Which is O times 1 minus O, right? So this is just the derivative of the sigmoid. And the other one, of course, is just the derivative of the linear function, which is just, xid. Right? So d is the data point and I is the feature. Okay? So now all we have is the product of these 2 things. Right? So bottom line, what is my new derivative compared to what I had when I just had the linear unit? It's exactly the same thing, except that there's now this additional factor of OD times 1 minus D, and that is just the derivative of the sigmoid. Okay? No big deal. Right. Any questions? Right. So far, so good. Now, let's do a clever little trick. We're going to call delta K minus the partial derivative of the error with respect to net K. Why am I doing this? Because this is actually the error signal that we're going to back propagate. What we're going to compute is successive of these derivatives going backward from the output. In fact, that's why this is called back propagation, because what I'm going to do is, when I'm given a new example, first I propagate it forward through the network to the output, and then I compute the derivative of the error at the output, and then I back propagate it 1 layer and 2 layers and as many layers as I need to. And the thing that I'm going to be back propagating is the delta case. So what I'm going to get, to do backprop is a function for the delta k's in one layer. Sorry, is an expression for the delta k's in one layer as a function for the delta k's in the higher layer. Okay, so the ones at the output we already know how to compute, right? Those are just, plain units, sigmoids, right, that we just saw how to do. And then from those we compute the first deltas, right? And then from the deltas we compute the deltas for the back until we've gone through all the layers, right? And in an error with just one hidden layer, which is what people typically use, I just have to do that once actually. Okay? So, calling this delta k, let's see what delta E with respect to net J is for a neuron, right, that's in the hidden layer. Okay? So this looks like a bunch of ugly math, but as you'll see, it's fairly straightforward. And this is really where the action of the backpropagation algorithm is, right? We are now ready to compute the derivative of the error with respect to a weight of a hidden unit. So, going back to this figure, right? We already know how to compute the derivative of the error with respect to these weights, right? The weights of the output units. Okay. And notice that in general, in this case, and in the car driving case and whatnot, there's multiple output units, right? So my total error is going to be the sum of the errors for each of the units, right? How many errors am I making on, what is my error on head plus what's my error on head, and so on and so forth. Okay. So we already know how to compute the derivative with respect to these units because they're just sigma units at the output, right? Easy street. What we're going to do now that's new, and it's the trickiest part of all of this, is computing the derivative with respect to these weights. Right? The weights of the inputs in the hidden units that are one step removed from the output. And the fact that they're one step removed is what makes things complicated. Okay? So this is what we're going to do now. So how are we going to do this? Mm-hmm.
In the delta k, what is k? K is the number of the kth output unit, or
it's the number of the unit. So for each unit, we're going to have, for each unit k, we're going to have a delta k. I mean, more general, think of this as the following. Units are indexed by whatever, right? By the layer and by the unit, right? And we're going to have a delta with exactly the same indices. Actually, sorry, yeah. This is going to be for each weight. You'll see shortly. Right? So, yeah. Okay, so how are we going to do this? I want to compute the derivative of the error at the output with respect to this guy, right? Step one, sum rule, right? Sum rule just says that the derivative of a sum is the sum of the derivatives, right? So the derivative of the total weight with respect to this guy is, first of all, it's going to be a sum of the derivatives of the errors of each one of these. You agree? Right? Naturally, right? That didn't arise, with these units because, at the output units, only one output depended on each of the weights, right? So there was no question of summing over all of them, right? The error with this guy, for example, the error here does not depend on this weight, right? So there was no sum rule to apply there. But now, the error is going to depend on this guy. This is the first key idea, through this guy, and this guy, and this guy, and this guy. You see? So what are these guys? These are the weights from this unit to all the output units. Okay? So I'm going to need to sum over those. Step one. Okay? Everybody got this? This is the first key idea. Right? This guy has an effect on the output error through each one of these. Okay? Sum rule. Second step, of course, is the chain rule. Right? Now we have a sum over these paths, right? One path, two paths, etc. In each of those paths, now I'm going to apply the chain rule. But now this is a much more complicated application of the chain rule because notice what's going through this chain, right? There's the sigmoid at the output. And then there's the weight from the hidden unit to the output. And then there's the sigmoid of the hidden unit. And then there's the weight going into the hidden unit, right? And this is what, can start to get, difficult to follow, right? But the thing about backprop is that backprop makes this all very clean. And it also makes it all very efficient. The thing that backprop is going to do is that I'm not going to compute the derivative with respect to each of these guys separately because that would be very slow. Remember, I can have thousands or millions of weights. I'm going to use the derivatives that I computed to then compute the other derivatives as a function of those, and then this is all going to happen very fast. At least one step of this is going to be fast. It might take many steps, but that's a different problem. You had a question?
And then But and that's just to train the connection between F1 and that first hidden unit on the left.
Yeah, remember, the whole purpose of backprop is that we just want to do the same thing that we were doing before, which is to compute the gradient of the error with respect to every single one of these weights. This is what backprop is for. Backprop is for computing the gradient. And then once I have the gradient with respect to each of the weights, either at the output layer or in the hidden layer or wherever, right? Then I do the same thing as before. I multiply by the learning rate and I subtract from the weight. Okay? So everything really stays the same. It's just this critical thing of knowing how to do this across multiple layers. Does that answer your question? More questions? Okay, so let's see how we do this. So here's my sum over all the outputs. Okay? Remember, these are the units that this unit is outputting to. Okay? So this is the sum. And here's my chain rule. My chain rule is breaking this into two parts. The first part is the derivative of the final error with respect to net k. Right? This is where net k becomes important, where our delta k's are going to show up. And the second part is the derivative of net k with respect to net j. Notice in this very simple application of the chain rule is really where all the action is, right? Notice the following. So I'm now looking, going back to this diagram, right? Rachel, let me just draw it here. So here are my outputs, right? And here's my hidden unit. I have weights going into the hidden unit, right? And then I have weights going from the hidden unit to the outputs, right? K is ranging over these, okay? Summing over those, right? But what I'm trying to do is compute the derivative with respect to one of these guys. Okay? I'm going to break that up into two pieces. The first piece is the derivative of the error with respect to net k. Right? Net k is the unit in the next layer. I hypothetically have already done this. Because it's either an output unit or because I did it in a previous stage of the backprop process. Okay? So this is kind of recursive in that way, right? So this guy I'm going to assume that I already have. In fact, this is what I called minus delta k. That's why that's why the delta k's are the thing that we play with. Okay. So this guy by definition is delta k, and when I get to this point, I have already computed it, right? When I get to the point of trying to compute the derivative with respect to this guy, I'm assuming that I've already computed the derivative with respect to these guys and so forth. Okay. And then the next part, right, which is where things get more interesting, is the derivative of net k with respect to net j. Because I'm really interested in unit j at this point, right? It's just that the effect of the unit j is through the unit k, right? So this is where kind of the interesting new action is. It's the derivative of net k with respect to net j. Yeah?
What's net j again?
So remember, k ranges over these guys, j ranges over these guys.
But you're only computing one of them.
No, exactly. But I'm going to show you how to do this for any one of them, and then you know how to do it for all of them.
So why is net j a component of that when?
No. So look at it this way, right? We applied the sum rule over these guys, right? But now let's look at one of those paths, right? It has a j part and it has a k part. Right?
But, why is j a net when it's only one of the things that's connecting the input to the hidden unit?
No. So remember, maybe I didn't say this very clearly, right? Look back to this diagram, right? There's net. Here it wasn't indexed, right? Net is just the weighted sum of inputs at this neuron, right? And now I'm just using j and k to range over neurons, right? So. Actually, maybe I know what the confusion is. Is that we're interested in the weights, right? But these are really weights of certain units. Okay? So here's my unit k, right? And here is my unit j, right? And then I'm actually, going to index over the weights going into that unit, right? So you have to keep this thing straight. There's a lot of indices, right? This is often what happens once things get, multiple layers and whatnot. There's indices over the neurons, right? And then there's indices over the inputs to the neurons, right? But you have to remember that the input to those neurons are in turn other neurons, okay? So, there's actually more than one way to do this notation, but the important thing to keep straight is that I'm interested in the variation of the error as a function of this weight. This is what I'm computing here, okay? But this weight, let me just finish, makes itself felt through this weight. Okay? And so K is ranging over things in this layer, and J is ranging over things in this layer. Okay, so K is the output layer, and or more generally the layer, the next layer up, and J is my current layer. Okay? You still seem a little puzzled. Why don't we go through the rest of this, and then we'll see if you still have a question. Okay? Okay, so now I'm interested in the derivative of net K with respect to net J. Right? And so now the question is, what is that? Well, if you think about this, we already saw how to do this when we were looking at doing it for a single neuron, right? This neuron happens to be inside the network instead of being at the output, but we already know how this goes, right? How does it go? D net K, D net J, in turn, can be decomposed using the chain rule into two things, right? D net K, D sigma, D OJ, right? This is the derivative of net K with respect to the output of my neuron in this layer, times the derivative of that output with respect to net, which is before the sigmoid. Okay? This is just what we did before, except now it's for a different neuron. It's for a neuron here instead of a neuron there. Okay? And now we know what these are, right? This guy is just the weight, as before, right? What weight specifically I'm interested in here? Notice, this D net K D OJ is WKJ. WKJ, this is really the important thing about the indices, right? This is what you have to have straight. It's like WKJ is the weight from unit J to unit K. Okay? So I have J here and I have K here, and I'm interested in the weight from J to K. And you see why, right? Because this guy is making itself felt through this guy, right? So I need to put that in my chain, and here it is. Okay? Everybody got this? This is a key step. And now the other part, of course, DOK D net J is just my derivative of the sigmoid. Okay? Everybody with me? You might want to go through this at home, step by step, getting the indices straight and applying the chain rule and whatnot. But at this point, what you should get is the basic idea of how my derivatives get computed in a hidden layer as a function of the derivatives that I've already computed at the next layer and my sigmoids, or the derivatives of the sigmoids. Notice that what happens in general is that my network is a DAG, right? The way I handle my DAG in computing the gradient is I use the sum rule to decompose it into, and the DAG is kind of a difficult thing, right? But I use my sum rule to decompose it into separate paths, right? My error is going to be a sum over paths, right? And then each path I use the chain rule. Right? So if you think about it this way, and you know how to do the differentiation for a single sigmoid unit, the rest follows. Okay? All right, so at this point we basically have what we need, right? This is my expression for the derivative with respect to net J, which is my new delta J, right? Remember, my goal is to compute my delta J because that's what I now want to use in the following layer if there is one. If there isn't one, then I just stop here. Okay? So what is this going to be? It's going to be OJ times 1 minus OJ, right? This comes from the sigmoid, times the sum over the outputs of delta K times WKJ, which if you think about it, this is actually fairly intuitive, right? Obviously, this term is going to be there because I had to pass through a sigmoid, right? So that has to be there. And the rest is a sum, right, over the units that I'm outputting to of the corresponding weights from me to them times their errors, right? So if you actually ignore the calculus and just look at the expression that you get, it actually makes a lot of sense. If you think in terms of the chain rule and the sum rule. Okay? Notice the sum rule is coming into play in the fact that I am summing over the outputs. Okay? Questions? Again, I don't expect you to have sort of like followed every step of this in 5 minutes. It's kind of not something you can do online. But hopefully you have the idea, and now you can sort of like try doing this by yourself. Okay? And then if you have questions, you can come back to us. And then there'll be a nice little exercise to test your understanding of this in the homework. We're going to ask you to do the same thing with a slightly more complicated function, in particular a function where we've added a penalty on the weights to avoid overfitting. We're going to get to that in a little bit. Okay? Questions? This was the hardest part of today's class, and now we're over it. And you can begin that long slide into, well, no, not yet. Okay, so What's the backpropagation algorithm, right? Let's put all of this together, right? The backpropagation algorithm goes as follows. As usual, I initialize my weights to small random numbers, okay? The usual thing. And then I do the following until convergence. Notice how similar this is to the previous, just training one neuron. And then I go through each training example, right? So we're going to look at the batch version here, but again, you could do this with an incremental version or, stochastic gradient, as it's called. And then first I do a forward pass. I input my new example to the network and I compute, the values of things going forward until I have, my O value at the output, okay? And then at the output, I compute my delta K, which is just, the delta, the expression for the gradient for a single sigmoid unit, okay? And then I do this for the hidden units, right, using the expression that we just saw, right? And then finally, right, what I do is I add this up for the examples, and I do my update, okay? In incremental mode, I just do the update right after each example. In batch mode, I sum this up for all the examples. I have a big delta weight, and then I do all the deltas, all the weight updates at once. Okay, and that's backprop for you. Questions? Okay, backprop, famous algorithm. Here's a few important points to notice about backprop. First of all, notice that we're doing gradient descent over the entire vector. So, let me try to press on, right, in the interest of time. We're doing gradient descent over the entire vector of weights. So we are solving here this credit assignment problem. And how did we solve the credit assignment problem, right? How did we figure out, how some weight deep in the network is responsible for the output? It's by computing the derivatives. Right? The way we assign credit or blame to a particular weight is, you contributed in these different ways, right? And then through those different paths, and I sum all of that up, and that's my contribution. So at the end of the day, whoever's making a big contribution whenever errors are being made is going to get dinged a lot, meaning my gradient has a big component in that weight, and that weight's going to change a lot. Okay? Another thing to notice is that nothing that we've done here actually depends on even having layers. It could be an arbitrary DAG. And in fact, for some specific applications, people hand engineer networks with a certain shape. Like, for example, a good example of this is character recognition. People have hand-designed networks for character recognition that actually have many layers. And backprop still works. The only thing that backprop requires is that I cannot try to compute the derivative with respect to a weight until I've computed it with respect to the weights of the units that this one outputs to. Right? That's all I have to do. So the general way in which I do backprop is I start at the output, right? I compute the derivatives with respect to those weights, and so on until I get to the input. Okay? So as long as I do my bookkeeping, properly, this is not an issue. Okay? Also notice that, as I mentioned before, it doesn't have to be a sigmoid. Sigmoids are popular and they're like neurons, but they could really be any function that you want, as long as it's nonlinear and differentiable. Okay? Now the next point, we've already touched on this, but it's a very important one, is that we don't find a global optimum anymore. Right? A lot of people have objections to this, but in practice, a lot of the time you can find a good optimum, particularly if you run things multiple times. As always, when you have many local optima, like for example in EM, a good solution is just run it multiple times, initializing with different initial random weight vectors. The beauty of this is that linearly increasing the number of tries exponentially improves your chances of getting to the global optimum. Because in order to not get to the global optimum, you have to fail on every one of your attempts, right? And the probability of failing on all of them goes exponentially down with the number that you have. So doing this multiple times is, a very simple thing that can be very effective. But there's a big problem in all of this, is that this is slow. And doing it multiple times is going to be even slower. Why is it slow? Right? The backpropagation process itself is quite quick, right? The forward pass is quick, and the backward pass of computing the derivatives is also quick. But the problem with this is slow is actually an unfortunate combination of a number of things. One is that I really have to be careful with my learning rate now, because now I'm in a complicated nonlinear surface and things can blow up in my face at any time. So I need a learning rate that's basically going to work everywhere. So if this learning rate doesn't blow up anywhere, when the values are steep, it's going to be very slow when the values are shallow. And then, I typically have to do many passes through the examples before this converges. And in fact, a single pass through the examples is called an epoch, which I find very revealing, right? That people call this an epoch, because it kind of tells you how long it takes. And then you might need, like 100 or 1,000 epochs for things to converge. Well, 1,000 epochs is a long time, right? It's more than mankind has existed, longer than civilization has existed. Okay? I mean, these days we have faster computers, but this is still an issue. Therefore, we should ask ourselves the question, what can we do about it? Right? You could go ahead and just implement backprop the way I've described here, but even on today's computers, doing it on more than toy problems would, be painful and maybe just too slow for you to get results. Because the other problem with backprop is that things are very sensitive with respect to various parameters, including learning rate and initialization, and you have to try things many times. And then each time is slow, right? So this is a deadly combination. So if you compare, for example, backprop with decision trees, which was a very popular comparison circa 1990, because people from the symbolic side of AI, now they were doing machine learning, but it was with things like decision trees and rule sets. And people from the neural side were doing backprop. And everyone thought that their method was best. And then along came the Bayesians, and they said, we're going to teach everybody a lesson, but then they didn't, right? So everybody learned to be modest and learned that their method wasn't always the best. But here's a rule of thumb. Usually, if you're willing to put in the time, at the end of the day, you can get a more accurate classifier with backprop than with a decision tree learning. Which is not surprising, right? Because if you think about it, you can embed a decision tree in backprop, right? A decision tree is a bunch of rules, and a bunch of rules is just, a DNF, right? And we know how you include a DNF in a multi-layer perceptron, right? So the representation is more flexible, right? And it has all these gradual degrees of freedom that I can adjust, right? So if you're willing to put in the work, you can probably get somewhat better accuracy with backprop than with decision tree learning. But it's a lot of extra work. With decision trees, as you already have some experience, you can kind of get this thing working in a fairly short amount of time. And, you can probably get useful results without too much parameter tweaking. And, like the clickstream mining example that we gave is actually a very hard one. That's actually, a tough data set to learn on, but it's a real data set. And a lot of problems, you get pretty good results with decision trees, with not much work. So, on the other hand, if you're a credit, if you're a bank and you really want to minimize the number of defaults on your clients, right? It's worth paying a team of 20 people to, use backprop for a year, right? And this is not a fake example, right? Some of these, Fair Isaac and whatnot, I don't know what all algorithms they use, but they've certainly used things like that, neural networks in the past. And, decision trees are also popular for that. So, what can we do to make neural network learning faster? And here's a very nice, very simple idea. And by the way, there's many fancier ideas that we're not going to go into here. Some of them involve going to higher order types of optimization instead of gradient descent using what are called Newton methods and conjugate gradients. So let me just, give you a pointer that those exist. But this is really getting into sort of like your, heavy-duty numerical optimization, which, a lot of us as computer scientists who prefer discrete things, that might not be a pleasant experience. So what can you do that's a lot simpler? You can do what is called momentum. You can add a momentum term to the thing that to your delta weights, to your weight updates. And the idea in momentum is actually a very intuitive one. And here's what the idea is. Actually, let me do this in two ways first. If we think of optimization as letting a ball roll down the hill, right? So here's my happy case, right? My ball starts here, right? And gravity just makes it, descend to the bottom, right? This is a happy instance of gradient descent, okay? But notice that in the algorithm that we've seen so far, the ball rolls down the hill at a constant speed, right? And the speed is basically the learning rate. In fact, it actually starts to get slower as my gradient gets smaller, but roughly speaking, it's constant, okay? Now, this is not how a real ball rolls downhill. A real ball rolls downhill much faster because it accelerates as it goes down the hill. It gains momentum, right? As our, good old friend Isaac Newton figured out, right? So if you want things to get faster, maybe, emulating this thing of things gaining momentum in the real world might be a good thing to do, right? And by the way, momentum might also help you with another problem, which is what?
Global minimum.
Yeah, right? You actually get to kill two birds with one stone. If the ball gains momentum as it runs downhill, it might have enough momentum to jump over that hump and actually wind up at the real optimum. Okay? Here's a slightly more technical way to look at this, right? Let's think back to that parabolic surface, right? And let me now draw it looking down, right? So this little dot here is my optimum, and then these lines are lines of equal value of E. They are equi-error lines, okay? And this is my happy case, where they all look like circles. Because what happens is, let's say I start out here, right? And where does my gradient point? In the direction of steepest descent, which is this direction, which is exactly the direction that I need to go, right? So if I take a step of exactly the right size, which admittedly I can't guess, but a step of the right size in this direction actually gets me to the goal, right? And even if instead of one step I have to take 10, well, that's not so bad, right? This is the happy case. You know what the unhappy case is? The unhappy case is and unfortunately the unhappy case is the frequent one. This here is exceedingly rare. The unhappy case is the case that looks like this. Here's my optimum, but then what my surface really looks like is these very elongated ellipses. It's a valley, right? This is like, there's a mountain on this side and there's a mountain on this side, and my error surface is a valley between the two mountains. Why is this an unhappy case for me? Because let's say I start out here. You know what direction my gradient points in? Well, imagine yourself, right? You're on the mountain looking at the valley, right? And the bottom of the valley is way over there. But the direction of steepest descent is, almost straight down, right? So the direction of steepest descent here goes like this. You see, because things are descending much more steeply in this direction than in this direction, right? There's a little component in that direction, right? Notice I didn't dot the arrow completely straight. I drew a little bit like this, right? But for the most part, you're actually going across the valley towards the other slope. That ain't what you want to do. And now look at what happens, right? Let's say I take a big step, right? Well, big mistake. I take a big step, I'm actually going uphill, okay? Let's say I take a small step, right? Well, maybe in the beginning I get close, I actually go down to the floor of the valley, right? And let's say I'm now in the floor of the valley, right? But typically what happens is that I didn't get exactly to the bottom of the floor of the valley. I overshot by a little bit, which sounds pretty harmless, but here's why it's not, right? The floor of the valley was like this, right? I overshot by just a little bit. So now what I'm going to do? I'm going to do another step of gradient descent, right? Which means that I jump back over here. Right, so you see what's going to happen? I am making progress, but what I'm doing is that instead of going straight to the goal, I'm zigzagging all the way to the goal. Ouch. This is going to take a really long time. What I wanted to do is go bam, bam, bam in 3 steps, but this could be 100 steps, this ellipse here is not very elongated compared to some of the ellipses that you get. Right? The ratio of this dimension to this dimension could be in the hundreds or thousands. So it's this annoying little zigzag that I want to get rid of. Right? So now did everybody follow this? This is actually this innocent little diagram is what makes life hell for people who use neural networks. This is what causes a lot of CPU and human time to be spent, or caused back in the 80s, because now we have ways to deal with this which are not perfect but are a lot better. So what does momentum do here, right? If my ball now think about it, like you have mountains and a valley, and you let the ball roll downhill, right? And now what happens when the ball rolls downhill is that the jumps keep getting bigger and bigger in the right direction. This is the thing, is that the motion of the ball, right, is going to be a combination of two things. One is a sine wave going up and down, the slopes on both sides, right? But there you're not gaining momentum, right? Because you go up the slope, you stop, you go back down, right? So that motion is slow. Here, that's all the motion we have. But in the meantime, there's another component to your motion, which is the motion that's actually going downhill. That one you're continuously accelerating because you are making some progress. So what happens is that you start out with this small zigzag, but then it gets wider and wider until you're making, basically progress down the valley to the goal, exactly what you wanted. Okay? Of course, you have to be careful not to overshoot on that side, but hopefully, you also have some leeway there. Okay? So does everybody, do you get this intuition? Okay, very good. So now, as usual, after the intuition, let's see the math. And the math is not that complicated. All we have to do is so here's my delta weight, right? I'm going to change the weights by this much. And this is what I had before, right? My learning rate times the delta, etc., etc. And now what I'm going to have is an alpha. Unfortunately, this is another term, another parameter that I'm going to have to fit experimentally. But this is my momentum coefficient times the previous change in weight. This is just like velocity and acceleration, right? So notice what this is going to do is that as long as my delta weights are in the same direction, right, they keep getting bigger. Because this one gets added to the next one, and then that gets added to the next one. It was already bigger, so the next one is even bigger, right? So as long as these things keep having the same sign, meaning I'm going down the valley, they keep getting bigger. However, if they have different signs, then this guy is actually decreasing the speed of my learning, right? It's making for a smaller step, right? If the previous step was in the opposite direction, now I'm doubtful as whether I really should keep going so fast, and then I slow down. So basically what it does is this speeds you up in directions where you're consistently going, in one way, and it slows it down in directions where you would zigzag, which means that eventually, you're basically just going in the right direction. Okay? This is a very simple change to make to your code, and it's very effective. If you try for fun just implementing backprop with and without this, you'll be amazed. And as I said, you can do much more complicated things like, quasi-Newton methods and whatnot, but those are much more complicated. Questions? All right. So the next issue, of course, is, but this was all about, minimizing your error on the training examples, right? How do I know that this is going to generalize well? I don't. So in backprop, as in multi-layer perceptrons, as in everything else, we're going to have to worry about overfitting avoidance. When all I had was one perceptron, overfitting avoidance was not a big deal because it's hard to overfit that much with just a hyperplane. Okay. So we will look at that. An important point, right, particularly relevant to things like the stock market, is once training can be very slow and require a lot of tuning and varying things and whatnot. But once you're done training, this thing is very fast to apply. Not quite as fast as a decision tree, but still, right? A forward pass through, particularly in things like finance, the typical network that people end up using, and I think is still used today a lot, although they don't tell me their secrets, is a network with only one hidden layer and a small number of neurons in the hidden layer. So applying that is a fraction of a second, which is good because if you take a fraction of a second more than your competitor, they bought low and you bought high. Okay, so speed here is really important. Not a very good domain for, say, instance-based learning. Okay. Questions, thoughts about any of this?
I have a question about the momentum.
Sure.
So the reason we are applying this is because the error contours are an ellipse and not a circle, right? Or closer to an ellipse rather than a circle, right? So what if we normalize the feature values so that all the features are roughly in the same range? Does that help or?
So great question. If I understood it correctly, what you're saying is why don't I turn this into this and then my life is easy? Is that what you're saying?
Yes.
Absolutely, brilliant idea. This is actually what the second order methods are all about at some level. But unfortunately, right, so in 2D, right, this is obvious, right? I shrink this feature, now I'm in this happy situation. But now what you have to realize is that we're doing this optimization in, spaces of dimension 1,000 or even 1,000,000, right? It's not that uncommon to have 1,000,000 weights, right? So at that point, what exactly you need to do is not very obvious, but it's really what, there's this thing called preconditioning that is basically just doing that. Things become very difficult for the fall. Here's the issue, right, is that This ellipse is actually not the really bad case. The really bad, let's say that this is, my axis W1, and this is my axis W2, right? This is not the really pathological case. Here's what the pathological case is. It's when my ellipse is like this. And then what you're suggesting doesn't really help anymore. You see what the problem is? Is that now what I need to do is I need to shrink along this direction. But this direction, right, in order to get to more of a circle. But this direction is no longer the direction of any of the inputs, or of any of the weights in this optimization problem. Right? So what I need to do is I need to find the directions along which I need to shrink. And this is where these second order methods kick into gear. Okay? It's often not obvious, particularly when if you think of this as being an ellipse in 1,000 dimensions, well, now this is getting pretty hard to do. But nevertheless, there's algorithms for doing that. The bigger problem, though, right, is that if this, right now, right, what we're looking at here is just, this would happen with also just, a single perceptron with a quadratic surface, right? The real problem comes when, I'm in a real, space of a multi-layer perceptron, and there what you have is like, well, it looks like this and like that, and like, all hell breaks loose, right? What exactly do you shrink there? Well, nothing is going to work everywhere because some things need to be shrunk in one place and need to be, extended in the other. So then it becomes very hard. This is, very good question. So there's another question here. You have it?
Are these covered in either of the books, or are they too deep?
Are these what?
Covered. The
second order optimization methods are not covered in Mitchell. There's other books where they're covered. I'd be happy to give you pointers to that. There's also packages out there that do this. Like you can buy numerical recipes in C, which I recommend, and they have some of these routines. But the thing is that a lot of them do not scale to the size of problems that we're dealing with here, right? People who do optimization, they keep getting better in the number of inputs that they can do this with, but we're looking at really, really high-dimensional problems here most of the time. And, like, in all fairness, just to spend 1 minute on this, there are many people who say, and these are people who I trust because they're pretty good at this, that nothing beats stochastic gradient. Batch gradient descent, that's good for introduction purposes, but not really what you want to use. But there are many people who say that the stochastic algorithm can't be beaten even by the best second order methods. And you might be wondering why, right? Since the second order methods are so much better at doing this, finding what direction to go and where to shrink and whatnot, and like not doing the zigzagging, right? The reason is that stochastic methods, you can do updates after each example. The second order methods that come from numerical optimization, they can't tolerate noise. They only work in batch mode. These methods rely on techniques, and I'm not going to go into the details here, that if there's even a little bit of noise as you get in stochastic gradient descent, they could go completely haywire. They're for optimizing things that you know exactly. So applying those methods, batch mode versus doing gradient stochastic, many people say that stochastic is still the best. There's also people who say that the second order methods are the best, so you should know about both. But the stochastic gradient methods are a lot simpler, so I'll definitely start there. And there's things, often what happens is that things like, a momentum term, or doing what's called preconditioning in cases where the value is aligned with the axis, they often buy you most of what you need to get. So, more questions?
How do you initialize the weights to start with? Like any tricks there?
Okay, so this is another very good question, after which we will take a break. Let us look at that issue for just a second. Why is it a good idea? So I've been saying to you, initialize with small random weights, right? And what do I mean by small? So first of all, why random weights, right? Why not? Here's an interesting question for you to test your understanding. Let's go back to this picture. Can anybody tell me why I had better initialize my weights at random and not all with the same value? This is a common rookie mistake. I made it myself when I first implemented backprop for a grad course, all those years ago when I was young.
It's a flat plane, then you don't have any gradient.
No. It doesn't have to be a flat plane, right?
That's
And think of a linear function, right, where all the coefficients are the same. It's just at 45 degrees to every axis. We're going to worry about that problem in just a second, but that's not the one we're dealing with right now. What goes wrong if I initialize all my weights to the same thing? And it goes really wrong.
All the neurons learn by the same offsets that keep being the same.
Exactly. That was not a problem when we were learning, a single perceptor. But notice, like, suppose that all the weights in all of these neurons are the same, right? All the weights going into them and going out. The gradient signal is going to be exactly the same for all of them, right? So I'm going to do the same updates for all of them, meaning I'm going to have the same values at the end of the day, right? So this whole network with 100 hidden units is really equivalent to a network with just one hidden unit. Right? So randomness is essential here. We need something that will make the weights go in different directions. Okay? We're actually going to see a nice little example, later today of what happens when you run backprop, and you'll see some of the interesting stuff that happens. So number one, they need to be random. Okay? But number two, why should they be small? Why not make them large? All right? That's the next question. Oops. Why not make them large, right? And let me give you a hint just by drawing a figure here. And let's suppose that my threshold is 0, right? Just to keep life simple, right? And let's suppose that my input is just 1, my xi is just 1, and I'm only worrying about one weight, right? What's going to happen here if my weight is small or large?
Small actually puts you on that curve. If you've got large weights, you basically end up with that positive one or negative one, and not going to give you much of a difference.
Right. So if I have a large weight, with a large weight, my input, right? I could call that x, but let me call it u or something, right? And this is sigma of u, right? And u is w times x, and since x is 1, it's just w, right? So this is just my w, right? If my w is right, let's leave the x here, which can be plus 1 or minus 1, okay? So you see what's going to happen, right? Is that if the weight is large, I'm going to be either here or here. And you know what this looks like if I'm only flipping from here to here? It looks like this. My sigmoid has turned into a step function. If my weights are large, I'm host. I don't have a training signal anymore because I'm in the flat part here. And the whole point of this being a sigmoid is that this thing is not horizontal. It has a little slope. And it's by following that slope that I get to the point where things get more interesting. Okay? So if I start out with large weights, I'm in the digital switching region, and I don't want that. And and then there's like these problems with underflow, and not having enough resolution in your floats. Nightmare. What happens if my weights are small? What region am I operating in? Instead of between here and here, right? I'm now switching, when my input is plus 1 versus minus 1, between here and here, right? This is much better, because you know what a sigmoid looks like when you zoom in? When you zoom into a sigmoid, it just becomes a good old linear function with a certain slope. That depends on the weights. Why is this nice? Well, things are well behaved in linear land. Remember, in linear land, there's only one global optimum when you pass it through the quadratic error, right? So what happens is that I start out linear, which is good for kind of getting my bearings, right? I'm the gradient descent algorithm, and I'm trying to optimize the weights. In the beginning, life is simple. Everything is linear, right? So I first learn a linear function, for which the hidden units basically don't contribute, but at least at that point, I'm in the ballpark. I've captured the linear component of my problem. And for things like finance, this is exactly what you want to do. You're basically trying to capture how, for example, a certain stock responds to things in the market. There's this notion of beta, which is the slope of a line. And now what the backprop does is it lets that line become nonlinear. And this is how I beat the competition, because the line isn't linear. But it starts out as linear, right? And then what happens as my weights increase, right? So because typically that's what's going to happen. They start out small, right? They're too small for this to be interesting, and so they increase. Is that my range starts to go into the interesting nonlinear region hopefully without going too much over there. In fact, it will never go over there because at some point it's gotten as far as it makes sense to go. Okay? So starting out with small weights, and people discover this at their expense by trying a lot of things and then failing. Starting out with small weights is actually a very nice way to make sure that things go to the right place. In fact, if you do, for example, the exercise of trying to learn XOR, notice, a perceptron can't learn XOR, but backpop in principle can learn XOR, and for the neural network people, this was a big deal, right? They wanted to shove this back in the face of Minsky and Papert, who, by the way, are still alive, and say, see, we can learn XOR now. Unfortunately, when they first tried to learn XOR, they didn't. Nothing good happened, right? Because XOR is still a tricky thing to learn. But if you start it with small random weights, chances are you'll get there. If you start with large weights, things just misbehave. Okay? All right, questions about this? Very good. Let's take a break. After the break, we'll finish neural networks and talk about model ensembles. It's 8:10, so let's continue at 8:20. All right, let's get going again. Compared to things like decision trees and rule sets, neural networks have another very big disadvantage, probably even the biggest disadvantage, which is that they are very hard to understand. Remember when in the first week I said, well, we really want our models to be comprehensible because, first of all, your customers probably will not accept your model if it's not comprehensible. I actually know of several cases where people built a perfectly good neural network for some purpose, but it was never used. Because the managers were like, I don't know why I should believe this thing. I don't understand what it's doing. And the engineer couldn't explain it either. Whereas with a set of rules, well, you're going to get no credit because of this and this and that reason. And with neural networks, you look at those weights and you have no idea what's going on. The other problem, of course, is that to make things better, right, in the cycle of machine learning, you need to understand what the model is doing so that you know how to change it. And neural networks are very opaque. Okay. Now, there are some happy cases, like, for example, the car driving network that we saw last time is an example where if you squint at the weights, you can actually figure out what's going on. But usually, it's not that easy. However, and people have even done things like develop algorithms for extracting rules from neural networks, right? I try to learn a very good neural network, and then I try to see what are the rules that the network is approximately encoding. Okay? But another thing that you can do, which is what we're going to do here, is you can try to understand what's going on. Right? It takes a certain amount of effort, but if the model is accurate, then maybe it's worth the trouble. So what I'm going to use here, to help us understand a little bit better what's going on inside the network, right? We have this big, vector of weights, lots of layers, and the gradient descent procedure, and what is this going to produce at the end, right? Let's try to get some intuition for that. And the example that I'm going to use for that is something that's very famous in neural network land, which is called an autoencoder. Here's a simple autoencoder, and this is going to be all Boolean for simplicity. I have 8 inputs, okay, which could be set in the following way. One of them is set to 1, and the others are set to 0. Okay? So only one. So the rule here is that only one of the inputs can be on, right? So there's inputs 1 to 8, and if one is on, the others are off, and so forth. Okay. And then I have my hidden layer with only 3 units. Okay. And then my output layer has 8 units. And my desired output, remember in backprop, you're trying to learn how to map the input to the output, right? The desired output is the same as the input. What I want is that when this guy is on in the input, this guy should be on in the output, and the others should be off, and so forth. Okay? What might the use of this be? It may seem silly at first sight, right? Why am I learning a network to produce what I already have, right? But what might be the use of this?
Encoding if you have a channel that you have to squeeze through.
Compression, right? Either for communication purposes or for storage on disk or whatnot, right? The advantage of this is that in the hidden layer, I only have 3 units, right? So I went from 8 bits to 3.